youtube.cv. Okay. Right, what's setting? Okay, Twitch. Go to create the dashboard. Go to stream manager. I think I'm online. Yeah, I'm online. Okay. I'm online. For some reason. Doesn't really help me. Does this work now? Hello? Not to my knowledge. No. Um, now this. GG. GG. Still cities GG. Let me see. Okay. It's in game. Game. Now this should be fine. Allahu. Okay. Hello. Okay. How? Mm. Okay, let me just go to the motions. Go to Google. View your channel. Okay. And solving physics. This is beating AI to solving physics with fanboys and so on. Am I hearable? Game. Can I have a game? Can I have game? Okay. We'll soon hear if the thing is working. Mixer OBS Studio is mic. Hello. Boop. Boop. Okay. Okay, now I'm hearable. I can hear myself multiple times, so I'll mute myself. If anything is wrong with the audio, please do just tell me. This we will close. OBS we will open. And live chat, everything is fine. Everything is fine. We continue on with the Newton's second law problem solving. Let's go.
Of using Newton's second law in problem solving. In this example, we'll figure out why riding in an elevator can give you a weird sensation of weightlessness or extra weight depending on which way you're accelerating. So let's say there's a person standing on a scale in the elevator that's accelerating upwards with some acceleration a. So we want to know what the scale reads. First, we need to really understand what the scale measures. The number that it gives you is related to the normal force that you are exerting on the scale. So this is a Newton's third law pair force to the normal force that the scale exerts on you. So if we can figure out the normal force on the person from the scale, we'll know what the scale should read. Now let's set up our coordinate system. I'm going to assign the upward direction to be positive y, and since the only forces in this problem are acting vertically, I don't need to define another direction. I'll pick the system to be the person. Now I'll think about what we know and what we don't. Since that person is standing in the elevator, not jumping, not moving otherwise, they must be accelerating upwards with acceleration a, the acceleration of the elevator. I also know the mass of the person, so now I have one side of Newton's second law. Now I need to think about what vertical forces are acting on the person. First, there's the gravitational force pulling the person down. This gravitational force does not depend on the acceleration of the elevator because the gravitational interaction is just between the person and the earth, so the force is minus mg. Finally, I have the normal force that's holding the person up. This is the normal force from the interaction between the person and the scale, and so this is the unknown quantity that I'd like to know. Let's look at Newton's second law. On the left, I have Fn, the normal force that I'm interested in, minus mg, the gravitational pull from the earth. And on the right, I have m, the person's mass, times a, the acceleration of the elevator, and therefore the person. Notice that when the elevator is accelerating, the normal force and the gravitational force do not have the same magnitude. That is, they don't cancel out. So now I can solve for Fn, and I can find that it's just m times the quantity a plus g. Have you ever noticed that at the bottom of an elevator ride when you're accelerating upward, you feel heavier? And at the top when you're decelerating, you often feel lighter? You can see that if I change a to minus a in this example, that I'll get the normal force is equal to m times g minus a. And this explains that feeling of lightness. It's always good to check that your answers match physical intuition. And I encourage you to go and play with elevators and other physical phenomena around you while you're going through this course to see if your answers make physical sense.
They do.
This week, we will consider the special case of circular motion, a case where we know that the motion is exactly constrained to have a circular geometry. This will consist of two parts. First, we will consider the kinematics of circular motion. How do we describe the trajectory, velocity, and acceleration of a particle undergoing circular motion? We will consider both the simple case of uniform circular motion, where the object moves with constant speed, and also non-uniform circular motion, where the object is speeding up and or slowing down as a function of time. We will see that a Cartesian coordinate system proves awkward for describing circular motion, and instead we will introduce the so-called polar coordinate system in terms of a radius vector from the origin and its position angle, which provides a much more elegant description for circular motion. We will then examine the dynamics of circular motion using Newton's second law to understand what sorts of forces are required in order to cause circular motion in both the uniform and non-uniform cases. This will be the first of several examples we will see in this course of constrained motion. In this case, the constraint is that the object moves in a circular path.
Physical problems in which a body undergoes motion about a central point. And when that happens, there's a natural coordinate system to describe that motion, which in two dimensions is polar coordinates. So let's consider the orbit of an object. For instance, the best example is a circular orbit. We have a circular orbit of an object. There is a central point, which we'll call P. Now, given this type of motion with an object, it naturally makes sense to choose a coordinate system called polar coordinates. The way that coordinate system works is as follows. First off, we need to choose a reference angle, and so we'll choose a horizontal line, and we'll draw a ray, and we'll show a direction of increasing reference angle theta. In this example, theta will go from 0 to 2 pi. Along with the reference angle, we have a distance from the central point, and that distance we'll refer to as r. So the coordinates of our point are r and theta. Now the variable r is always greater than r and can go to infinity, greater than 0. So this is our polar coordinate system. When you have a coordinate system, remember, at every point in space, there has to be unit vectors. So at this point right here, how do we choose unit vectors for polar coordinates? We always choose the unit vectors to point in the increasing direction of the coordinate. Take the r coordinate. That increases radially outward. So our unit vectors here will have a r hat pointing radially outward. What about the theta direction, tangential to the circle in this particular case? Because theta is increasing in this direction, we choose our tangential unit vector, which we're going to call theta hat, which is at right angles to r hat, to point in the direction of increasing theta. And so at this point, we now have a set of unit vectors. Now one has to be very careful in polar coordinates for the following reason. Suppose that you're at another point over here. Now, because we have two different points, let's just give some names to these points. We'll call this S1 and this point S2. And the unit vectors over here were R1 and theta 1. When we're at the point S2, we have to choose unit vectors exactly the same way. R hat 2 points in the direction of increasing r, and theta hat 2 points in the direction of increasing theta. So what we see in polar coordinates is that r hat 1 is not equal to r hat 2. Why are they not equal? They both are unit vectors, so they both have the same magnitude, but they point in opposite directions. in the same way that theta hat 1 is not equal to theta hat 2. So unlike Cartesian coordinates, in which at every single point had the same unit vectors, in polar coordinates, the unit vectors depend on where you are in space, and that will make our analysis of polar coordinates a little bit more complicated.
Makes sense.
When we're looking at polar coordinates, one of the important issues is to understand the unit vectors. Let's describe our coordinate system again. We have a point where there's an object, and at this point, we have a pair of unit vectors, r hat and theta hat. Now, those unit vectors will change depending on where you are in space. We now want to address the question, how do I compare polar coordinates and Cartesian coordinates? In Cartesian coordinates, at this point here, we would have, let's say we choose a Cartesian plus x and plus y. Then we would have a unit vector I hat and j hat. And how are these vectors related? Remember our angle theta. So we have the angle theta here and the angle theta there. And now I would like to apply simple vector decomposition to r hat and theta hat and express each of these unit vectors in terms of the unit vectors I hat and j hat. Let's begin with r hat. As you can see in the diagram, r hat has a horizontal component and a vertical component. So what we have is r hat. It's a unit vector, so its length is 1. Its horizontal component is adjacent to the angle, so that's cosine of theta I hat plus sine of theta j hat. The vertical component is opposite the angle. In a similar fashion, theta hat, well, theta hat has a component in the negative I hat direction, which is opposite the angle, and it has a component in the positive j hat direction, which is adjacent to the angle. So we have minus sine theta j I hat plus cosine theta j hat. And that's how we can decompose our unit vectors r hat and theta hat in terms of Cartesian coordinates. Now, why is this significant? Because if we're describing the motion of an object, for instance, an object that's going around a circle, then our polar coordinate theta is a function of time. And so these unit vectors are actually changing in direction. We saw that before. Over here, r hat and theta hat point in different directions. So what we actually have as functions of time is r hat of t equals cosine theta of t I hat. Now the unit vectors don't change in Cartesian coordinates. At every single point, you have the same Cartesian unit vectors. And so this vector is time dependent. Now the significance of that is our first important vector in kinematics is the position vector. The position vector is a vector that goes from the origin to where the object is. We'll call that r of t. So this position vector, r of t, can be expressed as a length, r, and its direction is in the r hat direction, which is a function of time. So we have r cosine theta t I hat plus r sine theta t j hat. Now, we can now define the velocity of this object, where the velocity is the derivative of the position vector. When you differentiate, remember r is a constant, so we get r. Now, what is the derivative with respect to time of cosine theta t? Because the argument of theta is a function of t, we need to use a chain rule. So the derivative is minus sine theta t d theta dt I hat, and the derivative of the sine is cosine theta of t d theta dt j hat. Now, notice that I can pull out the common term d theta dt, so I have r d theta dt, and I have minus sine theta t I hat plus cosine theta of t j hat. And if you'll notice, this is exactly the unit vector theta hat. So we can write our velocity vector for this object that's moving in a circle as r d theta dt theta hat. When we write a vector like this, it's pointing tangentially, the theta hat direction, and this part is the component. So often we can use a notation d theta hat, where d theta is the component r d theta dt. Now, this component can be positive or negative or 0. For example, if d theta dt is positive, what does that mean? That means that our angle theta is increasing, so the object is moving the way I indicate with my finger. If d theta dt is 0, then the angle is not changing, so the object is at rest. And finally, if d theta dt is negative, then the angle theta is decreasing, and so the object is moving in this direction. So this is our velocity for a circular motion expressed in polar coordinates.
Okay. Makes sense. Makes perfect sense.
Now we'd like to talk about angular velocity. So for a particle traveling in a circle, we've seen that the velocity can be written as r d theta dt in the theta hat direction. And we've also seen that d theta dt can be positive, in which case theta is increasing, and so the particle is traveling around the circle in this direction. You can call that the counterclockwise direction. We've also seen that d theta dt can be negative, in which case the angle is decreasing, so the particle is traveling around the circle in this direction, which we could call clockwise. Let's now look at rotation in an arbitrary plane. So if I have a plane like this, and I have some particle traveling in a circle like this, and I have some observer that's above the plane, looking down on this plane, then it will see this rotation as being in the counterclockwise direction, whereas if I have another observer down here, and they're looking up at this plane, they'll see the motion as being clockwise. And so you can see we have a need for the more formal definition for the rotation of this. And so what we're going to do is use the right-hand rule to define a direction that tells you both the direction, it defines the plane, and it also tells you what the positive direction of rotation is for that plane. So the way we'll do this right-hand rule is we'll take our right hand, we'll curl our fingers in the direction of the rotation, and our thumb will point in the direction of that positive, the positive direction that we're defining. So in this case, I'm going to have an arrow like this. I'll call it n hat to indicate that it's the normal unit vector to that plane. All right, let's come back to this example now, where the plane of the motion is this plane of the board. And let's look at our two cases again. So in the case of d theta dt positive, our circle looks something like this. And you can see that if I use my right-hand rule, the plane, the vector that I've defined is out of the board. And I'm going to use this symbol, a circle with a dot, to indicate this direction of out of the board. In our other case, for d theta dt less than 0, our particle is traveling in this direction. And so you can see by my right-hand rule that now that direction that I've defined is into the board. And for that, I'm going to draw this as an X in a circle. So these are symbols that you'll see throughout the rest of the course, the out of the board and into the board symbols. And so now let's look back at our coordinate system that we've defined. We have an r hat direction and a theta hat direction. And in this coordinate system, there's a third direction that's defined, which is the k hat direction, which you can see is out of the board. And so now I'm going to define what we actually call the angular velocity as omega. I'm going to write that as d theta dt Now, in the k-hat direction in this case, it could be in an arbitrary n-hat direction depending on what your plane of motion is. In this case, I'm going to call it in the k-hat direction. And now you can see that these signs are going to line up with these directions. So omega as d theta dt k-hat, when d theta dt is positive, k-hat is in the same direction as this unit normal that we've defined that defines both the plane of the motion and the direction of the motion. And when d theta dt is negative, I have that omega is in the negative k-hat direction, which is exactly this direction here that we've defined as being the motion for this plane. And so this is how we define angular velocity. So we can define the d theta dt to be the component of the angular velocity, omega z, because it's in the k-hat direction. And we can also define the angular speed, which we write as just omega, as being the absolute value of this angular velocity omega. So that is, in other words, it's just the absolute value of d theta dt. So when a particle is undergoing circular motion, it has a velocity that you can describe, which is the tangential motion around the circle. And it also has an angular velocity, which we define as being in a direction that's perpendicular to that direction of rotation, and it's defined by the right-hand rule. And now that we have defined this omega z, the component of the angular velocity, we can rewrite the velocity as just being equal to r times omega z, still in that theta hat direction. And so this is another way that we can write the velocity and connect it back to the angular velocity.
When we analyzed how the position vector changed, we know that the velocity for circular motion is given by the radius times the rate that the angle is changing, and it points tangential to the circle. So let's draw a few characteristic arrows to show that. At this point, we'll draw these pictures with d theta dt positive. So the velocity points like that, it points like this, points like that, and these are all the velocity vectors at different times. Notice that if we consider the special case in which d theta dt is a constant, in that instance, the magnitude of the velocity v is given by r magnitude of d theta dt, and that is also a constant. But the velocity vector is changing direction. And we know by definition that the acceleration is the derivative of the velocity. And so what we see here is where we have a vector that's constant in magnitude but changing direction. And we now want to calculate the derivative in this special case. We refer to this case as uniform circular motion. So the special case is often called uniform circular motion. Okay, how do we calculate the derivative of the velocity? Well, recall that the velocity vector r d theta dt, those are all constants. Because it's in the theta hat direction, once again, we'll decompose theta hat into its Cartesian components. You see it has a minus I hat component and a plus j hat component. The I hat component is opposite the angle, so we have minus sine theta of t I hat plus cosine theta of t j hat. So when I differentiate the velocity in time, this piece is constant, so I'm only again applying the chain rule to these two functions. So I have r d theta dt, and I differentiate sine, I get cosine with the minus sign. So I have minus cosine theta. I'll keep the function of t just so that you can see that. D theta dt I hat. Over here, the derivative of cosine is minus sine d theta dt. That's the chain rule. Sine of theta dt, d theta dt, j hat. And now I have this common d theta dt term, and I can pull it out, and I'll square it. Now, whether d theta dt is positive or negative, the square is always positive, so this quantity is always positive. And inside, I'm also going to pull the minus sign out, and I have cosine theta of t I hat plus sine theta of t j hat. Now, what we have here is the unit vector r hat t. R hat has a cosine adjacent in the I hat direction, and a sine component in the j hat direction. So our acceleration for a particle that's moving in a circle, we found that when it's moving at a constant rate of d theta dt, and let's recall what we meant by theta of t, and here's our particle, and we introduced our polar coordinates r hat and theta hat, then we found that the velocity was r d theta dt theta hat. And so let's assume that this quantity is positive, in which case the velocity is pointing in the positive theta hat direction, and that means that everywhere in the circle, the velocity is tangential to the circle, and the magnitude is a constant. So for this case of uniform circular motion, we calculated that the acceleration was equal to minus r d theta dt quantity squared r hat, which means that at every point, the acceleration vector is pointing towards the center. Now, we can write that acceleration vector as a component a of r hat, where this component is given by r times d theta dt squared. It's always negative because when you square this quantity, that's always a positive quantity. The minus sign, just to remember, that means that the acceleration is pointing inward. Now, how can we think about that? Well, if we look at the velocity vector, what's happening here is the velocity is not changing magnitude, but changing direction. And if you compare 2 points, and let's just pick 2 arbitrary points, so let's remove this acceleration for a moment, and consider 2 arbitrary points, say at time t1 and t2. So our velocity vectors are tangent, the length of these vectors are the same, and if we move them tail to tail, dt2, and take the difference, delta v, where delta v is equal to d of t2 minus d of t1, then we can get an understanding why the acceleration is pointing inward, because recall that acceleration by definition is a limit as delta t goes to 0. That means as this point approaches that point of the change in velocity over time. And so when we look at this limit, as we shrink down our time interval between t2 and t1, then this vector will point towards the center of the circle. And that's why the direction of A is in the minus r hat direction. Again, let's just recall that this is the case for what we call uniform circular motion, which is defined by the condition that d theta dt is a constant. Now let's consider the case where an object is undergoing circular motion, but in this motion, let's again introduce our polar coordinate system, r hat and theta hat. We now want to consider the case where d theta dt is not constant. And what does that mean? That means that if d theta dt is positive, for instance, the object is speeding up in this direction, or if d theta dt is negative, the object is slowing down in this direction. That's one type of case. So in this instant, we always know that there's a radial component at any instant given by minus r d theta dt squared. But because it's speeding up and slowing down, there is now a non-zero tangential component to the acceleration. And let's see where that comes from. So again, if we write our velocity vector as r d theta dt theta hat, this is the product of two terms. And because it's a product of two terms, we need the product rule from calculus in when we take a derivative. So the derivative will be the derivative of the first term times the second term, plus the first term times the derivative of the second term. Now, we've already analyzed this piece, and this was precisely minus r d theta dt quantity squared r hat. That was always the non-zero radial acceleration. But now let's analyze this piece separately. R for our circular motion is a constant. So it's only d theta dt that is no longer constant, so we simply take a second derivative. And so we get r times d squared theta dt squared theta hat. And that is our acceleration. Notice that it has two components. We'll write the first component, a theta, that's its tangential component, theta hat, plus the radial component, ar, that's again the component, and because this is a vector, r hat, where the a theta is now the second derivative of d theta squared dt squared, and just to remind you that ar is minus ar d theta dt squared. So when d squared theta dt squared is positive, it means d theta dt is increasing. And so if this object is going in this clockwise direction, we call that speeding up. In a similar fashion, it's easy to understand that when d squared theta dt squared is negative, then d theta dt is decreasing. And so it can be slowing down. Or if it slows down and stops, it can start to move in the other direction. So again, the acceleration has two components, a tangential component, and that depends on the type of circular motion we're talking about, whether d theta dt is constant or not. It always has a non-zero inward radial component, given by the component minus r d theta dt squared, regardless of whether it's speeding up or slowing down. Now we'd like to discuss angular acceleration for circular motion. So suppose we have our angle theta, radius r, and r hat and theta hat. Recall that we described the angular velocity as the derivative of d theta dt, and we made this perpendicular to our right-handed coordinate system, direction k hat. Now let's differentiate that to get our concept of angular acceleration. So alpha is the second derivative, d theta dt squared k hat, and this quantity is what we call angular acceleration. Now we'll describe the component alpha z as d squared theta dt squared, so it's the second derivative of the angle. And also, if we wrote this as omega z k hat, we can write that as the derivative of d omega z dt as well. So this is the component. And now, in circular motion, the quantities of omega and alpha z are very much like the linear quantities of the x component of velocity and the x component of the acceleration. And again, when we've chosen a reference frame, let's look at what various components mean. Let's begin with the case 1, where omega z is positive. So when omega z is positive, that tells us that the angle d theta dt is increasing, and that corresponds to counterclockwise motion. Now, given that case, let's look at what happens when alpha z is positive. Remember, that's the statement that d omega dt is positive, that omega z is increasing. So if an object is moving with positive component of omega z, and the angular acceleration component is positive, that corresponds to increasing. The linear example, if you had one-dimensional motion, I hat, you had dx positive, and ax positive, corresponds to an object increasing in its speed in the x direction. That's our first case. Now let's look at the second example, when alpha z is less than 0. So now the derivative of the omega z dt is negative. What that corresponds to, remember, omega z is the z component of the angular speed, and if that's slowing down, then with alpha z less than 0, the object is slowing down. So in our linear case, if we had ax less than 0, this is the classic example of braking. The object is moving in the x direction and slowing down. Now, let's look at case 2, where this is always a little bit complicated for circular motion, where omega z is less than 0. In that case, the object is moving in the clockwise direction, because the angle theta is decreasing, corresponding to clockwise motion. So in that case, once again, let's consider the two examples. Well, the first example is a positive component of angular acceleration. Now, this is the one that can be a little bit confusing. The object is moving clockwise, but it has a positive alpha z, which will correspond to slowing the object down. And if the alpha z remains positive, it will actually come to rest and then reverse its motion and start to speed up. So this is the case where the omega dz is increasing, and that's our first case. So something like that could correspond to if we plotted omega z, and we had an object that starts off with a negative omega z and increases. Notice that the slope here, which is alpha z positive, corresponds to a positive angular acceleration component, and the object slows down as omega gets closer to 0, stops, and now has a positive omega z corresponding to motion in counterclockwise direction. For our linear case, this corresponds to, again, with I hat, our object moving to the left, the x negative, and if x is positive, it breaks in this direction, which means it's slowing down, and then eventually, if alpha x, ax stays positive, it continues in that direction. Now, our final case, and I'll put it down here, B, is this is again where omega z negative and alpha z negative. It's always helpful to see this immediately with the graph. Omega z is negative. Here, alpha z, which is the slope, is also negative. This corresponds to an object moving in the clockwise direction, and actually its speed is increasing because alpha z is negative. So it's going faster and faster in the clockwise direction, even though alpha z is negative. And for our linear case, again, this corresponds to an object moving in the negative x direction, and ax is negative. It's moving faster in the negative x direction. And so these are the cases of how we analyze the various components, the various cases for angular acceleration and angular velocity. In kinematics, if we know acceleration, which we generally can get from Newton's second law, then we'd like to integrate the acceleration to get velocity and position. How does that work for circular motion? Well, when you think about circular motion, and you think about the tangential direction, then that, in some sense, is a one-dimensional motion. And so what we'll see is that the tangential description of this motion can be integrated to get the tangential velocity and position, just in a similar way that we did with linear motion, where if we were given the acceleration, we integrated velocity and position. So let's look at a particular example. Suppose we're given that the tangential component of the acceleration is given by some simple polynomial, a minus bt. Now, in this case, the acceleration is certainly non-constant. What we like to do, remember, this is equal to r d squared theta dt squared. So if we integrate the tangential component of the acceleration with some variable from t prime going from some initial value, which we can call 0, to some final value, then that will give us the change in the tangential velocity. So for this case, the theta of t is equal to v theta t naught plus the integral of a minus b t prime dt prime. Now, we needed an integration variable because recall that our functional dependence is the upper limit of the integral. We saw that in one-dimensional kinematics, so we're going from some t naught 0 to some prime t prime. Well, this integral is now, we'll write this v theta naught, where again t naught we're calling 0, and when we do this integral, a minus b t prime dt prime, that's an integral from 0 to t prime equals t prime equals 0. This integral is not hard to do. We get a of t minus 1/2 b of t squared, and there's that constant initial term. And so the velocity at time t, or the tangential component of velocity, is given by that expression. In exactly the same fashion, the angle, how much angle does this go through? Well, we have to be careful there. So if we want to do the arc length, s of t, we have to multiply the angle by the radius, and that is just the integral of the tangential component of the velocity from t prime equals 0 to time t prime t. And so in this example, we have a slightly complicated integral v naught dt prime, 0 to t. I'm going to drop, well, I'll write it in t prime, plus the integrals a t prime minus 1/2 b t prime squared. I didn't need to split this up, but I'm splitting it up anyway. And I have really 1, 2, 3 integrals to do, and what I get is v theta naught t. The result of the first integral, the result of the second integral is 1/2 a t squared, and the result of the third integral is minus 1/6 b t cubed. And that gives me, this I have to be a little careful on this side, it's how much has the arc length changed as we go from time 0 to time t. So that's the change in arc length. And that's a typical example of where we're getting tangential acceleration. We integrate it to get the tangential velocity, and then when we integrate the tangential velocity, we're getting the change in arc length around the circle.
Okay, makes sense.
Let's examine again an object that's undergoing circular motion, and we'll choose our polar coordinates, r hat, theta hat. We'll make it cylindrical with a k hat. Now that we've completed our kinematic description of the motion, now let's see how we apply Newton's second law to circular motion.
Hello,
Well,
Stephanie.
when we write Newton's second law as F
Sanzo.
equals ma, that, remember, we can divide these two sides. This side, the how, is a geometric description of the motion, and this side is the y, and this is the dynamics of the motion. And the dynamics come from analyzing forces that are acting on this object. So when we're applying this mathematically to circular
I'm
motion,
great.
F equals
How
ma,
are
this is
you?
a vector equation. And so what we need to do is think about each component separately. Sometimes I can just distinguish the components that I'm talking about over here. And so we have that the radial component of the forces, and that comes from an analysis of the dynamics, the physics of the problem, and this side is mass times the radial component of the acceleration, ar. Now these are very different things, and it's by the second law that we're equating in quantity these two components. Now if we wrote that equation this side out in a little bit more
Good.
detail, we'll
That's
save
good.
ourselves a little space when we handle the tangential direction. The forces come from an analysis of free body force diagrams, and over here we know the acceleration is always inward, and I'll choose to write this as r omega squared. And so this will be our starting point for
Currently,
analyzing
we're
the
doing
radial
mechanics.
motion for an object that's undergoing circular motion. Now
So,
remember, there could be a
classical
tangential motion
physics.
too, and in the tangential direction, the tangential forces are equal to ma tangential, and as we saw, this is again the second law,
See,
equating two different things. We have that we
Newton's
can write
second
tangential
law
force
and
as
circular
r t
motion.
squared theta dt squared, and sometimes we've been writing that as r.
I
alpha z.
already passed
But
this,
this
but
equation here
I want
is what we're going to apply
more
for the
in-depth
tangential forces.
knowledge.
If the
And
tangential forces are 0, then
I'm
there's
going
no angular, there's no
up
tangential acceleration.
until
We know
I
that
learn
for circular motion,
everything.
the radial forces can never be 0 because this term is always non-zero and points radially inward. And now we'll look at a variety of examples applying Newton's second law to circular motion.
Okay.
Let's consider the motion of a car on a circular track, and the track is frictionless, and it's also banked. So this is the overhead view of our circular track. It has a radius r, and here's our car moving at a constant velocity. Now, from the side view, when we want to look at that banked turn, let's draw a side view. So here's our side view, and the car is moving with velocity into the plane of the figure. Now, this surface here is frictionless, and what we'd like to do is find out what speed the car can move such that it doesn't slide up or down the inclined plane. So how should we analyze that? Well, our approach will be to apply Newton's second laws. Now, what's very important to realize is this is circular motion. And for circular motion, we know that the car is accelerating towards the center of the circle. Now, from the side view, towards the center of the circle is in this direction, so the car is accelerating radially inward. And that will guide how we choose our coordinate system, and so we can then write our free body force diagram. So let's begin with the analysis. So we don't need to see the overhead view anymore.
Sometimes
that,
I
and then we
do.
start drawing. This is what we can refer to
I
as
will
our acceleration
probably
diagram. And now let's draw
play
the force diagrams on the car. As our force of system. So here's our
Elden
speed.
Ring
Because the
or
acceleration
something.
was inward, we're going to choose a radially outward coordinate and a vertical
Eventually.
coordinate. notice that this is different than just a
But
mass on
now
a
I'm
fixed inclined
studying.
plane, where
Yeah.
we use unit vectors up and down the inclined plane. The reason we choose our unit vectors like that, to emphasize it again, is we already know this is constrained motion, it's circular motion. Now, what are the forces on the car? Well, there's the normal force, the plane on the car, and the gravitational force. Now here, whenever you're doing problems like this, remember that the trig is crucial to get these angles right, so that's V, and that's V, and that's our free body force diagram. And now we can write down Newton's second law. So we'll start out with our usual approach, and we have two directions that we have to consider. So in the radial direction, there's an inward component of the normal force, like that, and that's opposite the angle, so it's pointing opposite our direction. So we have minus n sine phi. The gravitational force is only in the negative k direction, and we know that the acceleration is inward, and so there's a minus sign. We have the mass, and the constraint for circular motion is that that's v squared
Thank
over
you.
r,
Thank you
where
very
r,
much.
because the radius of that circle is going to be thought of as the central point. Now for the k hat direction, we have a component
Enjoy
of the normal force
physics.
that's pointing
It's
up.
beautiful.
Just like
Trust
that.
me.
That's adjacent to the angle, so we have plus n cosine phi, and we have the gravitational force downward minus mg. And as far as the vertical direction goes, because the car is going in a circle, there's no acceleration up or down in the vertical direction. Again, that's a constraint in this problem. That's equal to 0. So in this problem, this is the side that we know, and we're trying to figure out up to the speed v. Now, how do we analyze this problem? Well, you can see that if I write my two equations as n sine phi equals mv squared over r, and n cosine phi equals mg, we have two equations. We have two unknowns v and n. Many times people just solve for n and try to find the equation and then substitute in, but you're also allowed to divide two equations, and that's much easier. The masses cancel, and we get the relationship that tan phi is v squared over rg, and so we have our result that the speed that the car can travel on a frictionless inclined plane and maintain uniform circular motion is exactly the square root of rg tan phi. And that's how we analyze the motion of this car in a bank turn. What we would now like to think about is what would happen if you're traveling faster or slower than the speed. So suppose we have v prime bigger than the speed.
Hello,
Now,
Thomas.
what that means is that the car is going faster, and the new
I'm
equilibrium,
not that
if
intelligent.
you asked what would the radius be, such that traveling at v prime, the car undergoes circular motion, v prime would be equal to r prime g tan phi. And so in order to go at this speed, you have to go at a greater radius. Now, what does that mean? Well, that means that if the car is traveling at v, so it's in this circular motion, and now the driver increases the speed to v prime, the car will start to slide up the inclined plane. Remember, it's frictionless, until it reaches as it starts to slide up the inclined plane, it will get to this new radius r prime, but because the car will have a little inertia, it will overshoot that speed, that radius, and then it will start to come back down the inclined plane, and it will oscillate about that point. It won't be sinusoidal oscillations, but there'll be a periodic oscillation about this new radius, r prime. The same thing, too, if we have v double prime less than v, then v double prime is equal to r double prime g tan phi. Now remember,
Serbia.
this double prime is not two derivatives, I'm just using that as a notation.
I'm from Serbia.
So if the car is going along at speed v and slows down, what will happen is the new equilibrium radius is smaller. So the car slides down the inclined plane until it gets to r double prime. It turns out that it will overshoot that a little bit and then start to move up. And again, it will oscillate around this new equilibrium length. So on a frictionless inclined plane, if you go faster than speed, the car slides up. If you go
Well,
slower than
it's
speed,
not
the car
such a
slides
nice
down.
place, but it's okay. Okay, now we have
The Little Princess asteroid B612 is being orbited by a small body. It has a mass m, and it goes around this asteroid B612 that has a mass m1. Now, we should add a coordinate system. We always know that r hat goes radially outward. And we know from universal law of gravitation that we have mutual attraction between these bodies, and actually that's going to point inward. And because we're having orbital motion here, so circular motion, the acceleration, the radial component of the acceleration will also point inward.
yeah,
We need to consider all of that for our F equals ma analysis that we are going to do now, because the little prince wants to know how far this little body is away from his asteroid. Okay, so we have the gravitational universal law here, minus g m m1 over the distance squared. So the distance here between the two planets, r, which is what we want to calculate. And then we have over here, for circular motion, the description of mr omega squared. Now, the little prince can't measure omega, but the little prince has a little time clock. So what he can measure is the period from here until he sees the body again. And that is 2 pi over omega. So we can add that in here, mr 4 pi squared over t squared. And well, this m here will cancel out, and now we have to solve this for r. What we're going to see, oh, and of course we have a minus sign here because in the life of the planet, the little prince, of course, gravitational, the acceleration is not going outwards, it's going inward. So we better give this a minus here and here as well, and we will actually see that.
This is
then
not
cancels
my
out
first
against this one,
stream.
and
I
we're gonna solve this for r, so we get r cubed,
You can
actually.
go on YouTube and see
and then we
I
have
streamed
g
very
m1,
interesting things. Like I'm gonna
over
stop
4.
this now to show you. So I streamed a stream of gaming, and I streamed a stream of making every dinosaur a femboy. So you can see. I tried making them all femboys. All of them femboys. That's the stream. It's kind of funny. And I've streamed some other stuff. I'll probably stream game development as well. Here we have my current Ray Marching game development. So this is a fractal, and it's being consumed by that, and it's going up and down, and it's 1000 FPS currently. Maybe I'm doing it too much, and it's doing a load on this. I'll close it just for that. But yeah, but now I'm doing physics, and I'll be doing physics for a lot. Approximately 200 days worth of doing physics. I want to become the best physicist ever. You can watch that on my YouTube channel if you want. If you want a more in-depth look into what I'm doing, what I've done, and so on. To catch more technical and creative content. Yeah. I also recommend that. These streams are kind of boring. I'm going through a lot of like math and stuff, and then I am doing problems. I guess that's the fun part, because you will see me fail a lot. But yeah, I can just go to my YouTube channel. I do not look at what the fuck is here. The YouTube channel. I can God damn. God damn. Okay. Videos. I can recommend you this video, the Asmongold Bolt video. If you know something about Eurovision, I recommend you this. Then this one is the classic. I made a Dogecoin robot. I literally did make a Dogecoin robot. And otherwise, well, these are good. This one is unwatchable. Do not watch this one. I'm gonna delete it soon. But this is about Dark Souls and the end of the universe, and so on. It follows the journey of me as well, and my god, because I'm not Mizantrash. This is Mizantrash. If the camera can catch it, this is Mizantrash. Okay. Returning to physics.
Pi squared, and here we have a t squared. And we can also just write that as gm1 4 pi squared t squared, and then we have the third root. So you might have seen this equation here. This is actually Kepler's law. It describes the motion of the planets around the sun. Well, it really only does it if the motions are fairly circular. For elliptical orbits, it is not such a good approximation, although Kepler derived it like that quite a while ago, and that was really an astonishing result. So here we have this again, that the cube of the distance between two objects is proportional to the square of the period of the orbiting time. Now the little prince wants to know...
Oh, thank you very much. I mean, that does mean a lot. Let me change my vape fluid, and you can talk while I do that. Strawberry could do the job. Strawberry is good. Trust me, I'm a weirdo. You will never know whom I support and whom I don't support. You'll never know many things, but you'll know a lot of things as well. Okay. Yeah, suggest anything. I am open to suggestions, no matter how insane they are. Look at this. Remember Miyazaki? This is Miyazaki. I made him. My beautiful Miyazaki. Okay. What else do I have to show you? I have the coin of Mizantrash. One side is me, as you can see, and the other side is Mizantrash. Now suggest. Well, because I filled my vape fluid. eye-catchy and glowy stream more. Yeah. So Fanboy Dinosaurs is that. Like Fanboy Dinosaurs is that. I'm supposed to hire an editor this month. From my paycheck. Basically, I'm gonna hire an editor, and they will edit my streams into very tiny little 5-minute clips of good content. You can always give suggestions. That's nice, but I'm kind of already building a brand around weirdness, so I cannot really do that. I'm sorry, but I appreciate it very much. Now I gotta continue. So no, sorry, but you do video editing. Do you do stream video editing? Like I could send you a stream and you cut off the pieces, make it fun, and add some insanity. Not for this video, but I'll show you for what. Um, um, yeah, like a montage, I guess, but a bit more insane for my channel, I guess, with bright colors flashing in and out. We can talk about that. Add me on Discord, I guess. It's just Mise en Trash. I'll add you right now. And we can talk about. Yeah, sure. We first find it. Yeah, it's Mise en Trash. Okay. Okay, here you go. And we can talk there. See if we get each other. I'm waiting for the message request, or add friends, whatever you are. Did you type it right? Mise en Trash, yeah. Okay, Stephanie. I'm gonna wave. Food ague. Okay. Probably shouldn't do this on stream, but who cares? It's a stream. Nobody watches, but I will.
How fast this little body is going around, and well, we can just do the F equals ma analysis again, but use a different option here for the description of the circular motion. So we are going to get minus gm1 over r squared equals minus mv squared over r, and Here, 1R cancels, and this M cancels.
Let me see what you sent me. Can't really check this out now, but I will after stream. Okay? Info. Use appreciations, followers, Twitter. Great. Bro. Work. Gaming rooms. Banners, logos. I don't see any video stuff. Monthly.
Cancels, and that goes to plus. If we solve this for v, we get v equals gm1 over r and the square root of that. And so now the little prince knows how fast this object is going, given the radius here that we've calculated over there with Kepler's laws.
Yeah.
The little prince has really come to like this little body that's orbiting him. He knows at what distance it orbits, it knows how fast it goes, and I think the little prince fell in love with that little body. And now he wants to see if all the time as it goes around the asteroid. But the little prince just wants to keep sitting there. He doesn't want to move. So how fast does the asteroid need to rotate so that the little prince will always see the body as it rotates around it? Well, for that, we need to simply consider that the period of the little body going around the asteroid needs to be the same as the asteroid rotation period. So we're going to call that TA for asteroid. And, well, if we want to know at what distance that works out, then we're going to use Kepler's laws here again, and we're going to have that the radius of between the body and the asteroid will be gm1 over 4 pi squared, and now we have ta squared in here in the third root of that. So all of these wonderful quantities make the little prince really happy.
This week, we will examine some more advanced topics in the application of Newton's laws of motion. First, we will look at more examples of constrained motion, where the motion is forced to obey some particular condition in addition to Newton's laws of motion. These conditions usually specify some particular relationship between coordinates of objects in the system we are studying. Specifically, we will re-examine the case of objects suspended with pulleys and ropes, but with more complex systems than we have discussed previously. The fact that the ropes have fixed length will provide a constraint condition relating the coordinates of our various masses. Second, we will examine the case of forces acting on a continuous extended mass distribution as opposed to acting on discrete point masses. This will allow us to introduce a powerful differential analysis technique from calculus, where we model
1 second. Guess we're talking now. So, can I just show you? Are you on the stream? Are you on the stream? I'll just show you. Okay, listen. We are here, and let me see where the hell have I put in the file. The file is somewhere here. Okay, I'm gonna put the file there. Okay. Now the file is in the correct spot and I need to fix my camera and stuff. Okay, so example. This video is okay. Okay. It's 2 hours long, and I want and I do mostly bad stuff in those 2 hours.
And
But
purple flowers here.
But sometimes I go on tangents and say something funny. Sometimes I'm not that funny. So I would like to, from this 2 hour video, get 5 minutes of compiled, like, creamy, juicy stuff.
Taurus,
That's
but
it.
I was never a mime.
See? I'm
This
putting
is a
blonde.
real dinosaur.
See this.
Turn
Like
the
that.
churn, not churn, turn.
So that's how it would go. I would not edit the videos, these videos. But how much? We need to talk. We need to talk in Discord. On Discord. How much per video and so on? What's the budget? And so on. And I will do a Fanboy Dinosaurs Part 3 probably tomorrow. Music non-copyrighted is okay. Crazy colors. Maxer. It hits. Can we do okay? Nobody else, so I'm not intruding upon studying. I'm just intruding upon my studying, which is 10:26. That's okay. And I'm sorry if I reject you. I'm really picky, and I don't have a lot of money. I'm just using the money I have to edit. Just have someone to just chop the clips. That's how it works. I'm really uh, I'm really not. I know you're doing your job and so on. You were nice in my chat, so trying to find a job. I know finding jobs is hard, but I must secure myself as well. I'll pay for the trial run video, anyways. Just how much is the question? Okay, I'm gonna go to back to physics. Okay, everything is perfection. Good.
continuous mass distributions as made up of lots of small, discrete mass elements, and then examine the limiting case of infinitesimally small elements to obtain the continuous behavior. This is a technique that you will see applied over and over again in physics and engineering, and in fact, we will return to it again later in this course.
We
Our
will.
specific example will be to study how tension varies in a long, massive rope. This is in contrast to the light, effectively massless rope.
Okay, let me read.
Will be discussed previously. Finally, we will discuss velocity-dependent forces, that is, forces whose strength depends on the velocity, or some function of the velocity, of the mass being acted on. The most common example of this is resistive forces, or drag forces, which are caused by motion of a solid object through a fluid like air or water. That is the example we will discuss this week. Another example you may be aware of is the magnetic force that acts on a charged particle, which depends upon the velocity of the charged particle. In all three of these cases, we will simply be applying Newton's three laws of motion, but the situations will require a more sophisticated treatment than what has come before.
Let's look at a typical application of Newton's second law for a system of objects. So what do I consider as a system of pulleys and masses? So I'll have a fixed surface here, a ceiling, and from the ceiling will hang a pulley, which I'm going to call pulley A, and this pulley will have a rope attached to it, wrapped around.
Pulley. You're a great editor, I can see that. I just can't afford it. And I need a bad editor, to be honest. A newbie.
here we have object 1, and the rope goes around the pulley, and now it's going to go around another pulley B, and fixed to the ceiling. So that's fixed. And hanging from pulley B is another mass 2. And our goal in applying Newton's second law is to find the accelerations of objects 1 and 2. Now, how do we approach this? Well, the first thing we have to do is decide, if we're going to apply Newton's second law, what is the system that we'll apply it to? And there's many different ways to choose a system. When we look at this problem, we'll have several different systems, so let's consider the ones that we're going to look at. And the first one is very simple. It will be block 1. And the second system that we look at, we'll call that A. B is pulley A. Now, that brings us to an interesting question about pulley B and block 2, because we could separately look at pulley B, and we could separately consider block 2, or we consider them together. And I want to first consider separately pulley B and block 2. Now, in some ways, when you're looking at a system, a compound system, and it has 4 objects, it makes sense to apply Newton's second law to each object separately, but we'll pay careful attention to the fact that object 2 is connected to pulley B, and eventually we'll see that we can combine these two things. So the next step is, once we've identified our object, is to draw free body force diagrams for each of the objects. So in order to do that, let's start with object 1, and we want to consider the forces on object 1. Now that brings us to our first issue about what types of assumptions we're making in our system. For instance, we have a rope that's wrapped around this pulley, and we have 2 pulleys that in principle could be rotating. But what we'd like to do to simplify our analysis, so let's keep track of some assumptions here. Our first assumption will be that the mass MP of pulley A and the mass of pulley B are approximately 0. Now, the reason for that is that we're not going to consider any of the fact that these objects have to be put into rotational motion. Later on in the course, we'll see that this will give us a more complicated analysis. We're also going to assume that our rope is not slipping, so the rope is just slipping on the pulleys. So what that means is it's just the rope is sliding as the objects move. Now, again, what this is going to imply is that the tension in the rope, this rope is slipping, and the rope is massless as well. It's a very light rope. And all of these assumptions we've seen when we analyze ropes tell us that the tension T is uniform in the rope. So that's our first assumption. And we need to think about this before we even begin to think about the forces on the object. And now we can draw our forces. What do we have? We have the gravitational force on object 1. And now we can identify the tension pulling in the string, pulling object 1 up. Now, for every time we introduce a free body diagram, recall that we have to choose what we mean by positive directions. And in this case, I'm going to pick a unit vector down, j hat 1 down. So that's my positive direction for force. Now, before I write down all of Newton's laws, I'll just write down our various force diagrams. So for pulley A, I have 2 strings that are pulling it downwards. So I have tension and tension. And this string, I'm going to call that T2, is holding that pulley up. So we have the force diagram. Now, I could write MAG, but we've assumed that the pulley is massless. And again, I'll call j hat A down. For object 2, let's do pulley B first. Now, what are the forces on pulley B? I have strings on both sides, T. Pulley B is massless, so I'm not putting gravitational force. And this string is pulling B downwards, so that's T3. And again, we'll write j hat B downwards. And finally, I have block 2. So I'll draw that over here. I'll write block 2. In fact, let's save a little space here. We'll have j hat B downwards. Now, block 2, what do we have there? We have the string pulling up block 2, which we've identified as T3. And we have the gravitational force on block 2 downward, M2G. And there we have j hat 2. So I've now drawn the free body diagrams on the various objects, and that enables me to apply Newton's second law for each of these objects. So let's begin. We'll start with object 1. We have, remember, in all cases, we're going to apply F equals ma. So for object 1, we have m1g, positive downward, minus t is equal to m1a1. And that's our F equals ma on object 1. So sometimes we'll distinguish that the forces we're getting from our free body diagrams, and A is a mathematical description of motion. For block 2, we have m2g minus t3 is equal to m2a2. And now for pulley A, we have 2t pointing downwards, minus t2 going upwards. And because pulley A is massless, this is 0. Even though pulley A may be, it's actually fixed too, so it's not even accelerating. And what we see here is this equation. I'm going to quickly note that it tells us that the string holding pulley 2 up, T2 is equal to 2t. Now, so we can think of, if we want to know what T2 is, we need to calculate t. And finally, we have B. And what are the forces on B? We have T3 minus 2t. And again, pulley B is 0. And so we see that T3 is equal to 2t. Now, if you think about what I said before about combining systems, if we combine pulley B in block 2, visually what we're doing is we're just adding these 2 free body diagrams together. When we have a system, B and block 2. Let's call this j hat downwards. And when we add these free body diagrams together, you see that the T3 is now internal force to the system. It cancels in pair by Newton's second law. And all we have is the 2 strings going up. So we have T, and we have the gravitational force downward. And separately, when we saw that T3 equals 2t, and we apply it there, then if we consider a system B, 2. And look at our free body diagram. We have n2g minus 2t, and notice we have the same result there. 2t equals
Yes.
n2a2. So in principle now, and I'll outline our equations, we have equation 1, we have equation 2, and in these two equations, we have three unknowns, t, a1, and a2, but only two equations. And so you might think, what about this missing third equation here? However, in this equation, we have a fourth unknown, t3, and this equation is just relating to t and t3. So in principle, we would have four unknowns and three equations, or if we restrict our attention to these two equations, we have two unknowns, three unknowns, and two equations. Our unknowns are t, a1, and a2. These are our unknowns. And now our next step is to try to figure out what is the missing condition that's relating some of these unknowns, and that will be a constraint condition that we'll analyze next.
Okay.
So when we analyzed Newton's second law applied to this compound system, we had two equations for M1, object 1 and object 2. And what we found is that we had three unknowns, the tension in the string, and the accelerations of the two objects. Now, how do we solve this system? Well, we're missing one condition, which is a constraint condition, which is as object 2 moves and object 1 moves, they have to move in some relationship together. And now what we'd like to do is show an analytic approach for finding that constraint condition. And the way we think about it is that we'll call L equal to the length of the string, and this quantity is a constant. And what we'd like to do is introduce coordinate functions for our object 1 and our object 2, and express L in terms of those coordinate functions, and then take two derivatives of L, set that equal to 0 because it's a constant, and that will give us a relationship between the accelerations of objects 1 and 2. Now, this is a little bit tricky, and so what we want to do is very carefully show how we introduce coordinate functions. Recall that we had j hat 1 down and j hat 2 downwards. What that implies is that we're choosing some origin, and let's choose an origin up here, and for coordinate functions of object 1, it has to be consistent with our choice of what we mean by j hat 1. So in this sense, y1 is a positive quantity when we're going downward. Now, what about coordinate functions for the other objects in the system? Well, let's look at a few things first. This is a fixed distance, we'll call it S1, between the center of the pulley and between the ceiling and the center of the pulley. And let's make each of the pulleys a radius r. And let's call this a function yb. And let's make this y2 of t. So now we have coordinate functions for 2 and coordinate functions for 1. And again, recall that this distance here, S2, is a fixed distance. And when we define these coordinate functions in this fashion, we know that the second derivative, d squared y1 dt squared, this is precisely what we mean by the acceleration of object 1. And in a similar fashion, d squared y2 dt squared is what we mean by the acceleration of object 2. So we've introduced a coordinate system. We've made it very clear what we mean by the accelerations of a1 and a2. And now let's look at our constraint condition that the length of the string is constant. So what we're going to do is try to see if we can express the length of the string in terms of all the coordinate functions and some of these ancillary quantities. So what we have here is that the length of the string is yb going down here. So the length of the string has a factor yb. It wraps around pulley b, so that's pi r. And it goes up to this length here. Now, this length is yb minus s1, so that's yb minus s1. We wrap around the pulley again, that's pi r. And now we have this length here, which is y1 minus s1. Now, s1, yeah. And let's just make sure we have all of our quantities here. Now, we also have another constraint condition that this length of the string, we're going to call this L1. We have a second string here, L2, and L2 is given by y2. This length is y2 minus yb, and that was what we called this constant S2. So we now have two string lengths, L2 equals y2 minus yb, and both of these string lengths are constant, and we have the following facts. Let's start with this one first, that the second derivative of L2 dt squared, because the length of the string is a constant, that's 0. And that tells us two derivatives of this is a2, and two derivatives of that is ab. And this is something that we saw before, that block b and 2 are moving together. So when we treated the system as just b and 2 together, we see that the acceleration of 2 and the acceleration of pulley b are the same. So we could have just said that before we began. Now, let's put these equations aside for the moment. And now let's consider taking two derivatives of length of string 1. We'll call string 1 is this object here. We'll call this string 1 and this string 2. Now, again, if we take two derivatives, let's look at our expression first. We see that we have two factors of yb, and we have a bunch of constants whose derivative is 0. So we don't have to worry about the wraparound distances, the pi r's. We don't have to worry about the constants s1. All we have to think about is which quantities are changing in time. So we have 2ab when we take two derivatives, and we have one factor of a1, and that's 0. And now, because the block and 2 and pulley b are accelerating together, we have our condition, which is 2a2 plus a1 is 0, or that a1 is equal to minus 2a2. And that is the extra constraint condition that will enable us to solve the system of equations.
Okay, that makes sense.
When we did our analytic analysis of the constraint conditions between the accelerations of objects 1 and 2, we came up with a condition that a1 was equal to minus 2a2. Now let's do something which we call a virtual displacement argument. Suppose that b and 2 move down a certain amount. Let's imagine, and I'm going to draw it in a different color too. So we have object 2, and pulley 2 has moved down. Now, this object has displaced by a distance delta y2, which is also equal to delta yb because they're connected. Now, what happens when the system does that is our rope has to extend downwards around this pulley and come back up. And that means that the rope, that object 1 has been foreshortened by not just delta y2, but on both sides, delta y2 and delta y2, object 1 has displaced up by that amount. So we'll just
2 times.
make this so we can draw it in a reasonable way. So what we see here is that delta y1 is equal to, now notice if 2 goes down, y by delta y2, then delta y1, which is this whole distance, is a negative quantity, and it's going upwards, and so we see that that's minus 2 delta y2. And if we took two derivatives, or displacement, and then look at the change in displacement, we would see that this implies that the acceleration of 1 is minus 2a2. But let's come back to our two conditions for length and see the same thing here. Because delta L2 is 0, this tells us that delta y2 is equal to delta yb, so we'll write minus equals 0. And that was our condition, that the block and 2 are moving together. And up here, we see that because delta L1 is also 0, this implies, and now I'll make that substitution, that delta yb is equal to delta y2, that 2 delta y2 here and here, plus delta y1 has to be 0 coming from that piece. And so we see that delta y1 is minus 2 delta y2, which is what our virtual displacement argument showed us. And again, if you take two derivatives, here we have that, recall that in the simplest way, that the velocity is dy1 dt, and the acceleration a1 is d squared y1 dt squared, then the same proportionality is maintained under the two derivatives. And that's another way of thinking about how to get the relationship between accelerations, but you have to be extremely careful about that sign, because as 2 goes in the positive direction, 1 will go in the negative direction. We are now in position to find the accelerations a1, a2, and tension, because we have Newton's second law and our constraint condition for the acceleration. Let's recall the equations that we found. We had m1g minus t was m1a1, and we had m2g minus 2t was equal to m2a2. And we also had the constraint condition between accelerations that a1 was minus 2a2. So now we have a system of three equations, and we can solve for any of these quantities that we want. So one way to do it is to identify an equation and to identify the quantity that we would like to solve for. So for instance, let's identify that we want to solve for a1 first. So how are we going to develop a strategy for that? Well, I'll choose equation 1 as my backbone equation, and I have an unknown t, but in equation 2, that unknown t disappears there, but it's expressed in terms of a2, and a2, though, from equation 3, is expressed in terms of a1. So my first step is to rewrite equation 2 as m2g minus 2t equals m2. Now here's I'm going to make the substitution, which is minus a1 over 2. So we'll call that 2a. And now I have equation 1 and equation 2a, two unknowns t and a1. And what I can do is I can solve for either equation, and I can make a choice what's easiest. When I look at these equations, it's easiest for me to identify what t is in terms of a1. So I'll write m1g minus m1a1 is equal to t. I'll call that equation 1a. And now I can substitute that value of t into equation 2a, and I get m2g minus 2 times m1g minus m1a1, and that's equal to minus m2 over 2 times a1. And now I'd like to collect my a1 terms, and what I have over here, let's bring all the a1 terms to this side, and I get m2g minus 2 m1g. I have a plus, so I'm going to bring that over to this side, and I get equal to, that's plus plus, so I'll have two minus signs, and I'll have 2 m1 plus m2 over 2 a1. And now I can solve for a1, and what I get is I get 2 m1g minus m2g, and I want to divide through by this denominator, and what I have downstairs is 2 m1 plus m2 divided by 2. And that's my expression for a1. Once I have that expression for a1, I can easily come back and find out what a2 is, or I can substitute into the equation here for a1 and find out what the tension is, and so I can now easily find my expressions for a2 and t, but I will leave that as an exercise.
Okay.
We want to look at this pulley system. We want to find out what this force here is, for example, with which this block is being pulled. Now we have two massless pulleys here and two moving parts. And one key component of this problem is to derive the acceleration constraint. How we're going to do that? Well, we have to look at this string here. First of all, it's a fixed string length, and that will help us. Ultimately, this is just a distance that connects all of these objects, and if we eventually differentiate that twice, we get to an acceleration. So the first thing we're going to do is to figure out what the string length is, to then derive the acceleration condition. Let's begin by first identifying the fixed lengths in this problem. So we have a little distance here. We'll call it SB, and we have a distance here that's fixed SA. And we furthermore know that this block here is fixed to the ground, and we can choose a coordinate system origin. Let's say we do that here. We know that we have the distance d here to this little block. The moving parts are block 1 and block 2, so we have to assign position functions. And actually, this one here is x1. It goes up to here because we want to measure the string length. Ultimately, we know this portion here, so we can subtract it. And then, of course, we need also x1 that goes here, x2. So now we can tally up the length. Let's start with this portion here. That is d minus SA minus x2, d minus SA minus x2. And then we have a half circle here, pi r, and we know actually that there's another half circle going to come there, so we can just write 2 pi r immediately. And then we have this part here. That one is x1 minus SB, and then minus SA minus x2. And then finally we have this portion, and that is x1 minus SB minus x2. Okay, so the next step is that we need to simplify this a little bit. So we have 1x1 and another one here, 2x1 plus x2, 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 actually 3, minus 3x2. And then we have all sorts of constants. We have d, we have fa, fb, the 2 pi r. But as you will see, if we differentiate this L here, that will actually all fall away. So we're going to make it a lot easy and just add a constant here. And so we want to now do the second derivative here of our string length with respect to time, because these are all position functions, so we can differentiate those. What's important, of course, here is the string length is not changing with time. So actually we know that that derivative will be 0. And we can just write this up here because x differentiated twice is a. So 2a1 minus 3a2. And we immediately see from that that a1 equals 3 half a2. So this is our constraint condition that we will need later. For now, we need to continue with setting up free body diagrams of all 4 objects. We want to now do the second derivative here of our string length with respect to time, because these are all position functions, so we can differentiate those. What's important, of course, here is the string length is not changing with time. So actually we know that that derivative will be 0. And we can just write this up here because x differentiated twice is a. So 2a1 minus 3a2. And we immediately see from that that a1 equals 3 half a2. So this is our constraint condition that we will need later. For now, we need to continue with setting up free body diagrams of all 4 objects. Let's start that with object 1. What's acting on object 1? Well, we have f here. Well, we're just going to write it as magnitude. We have f, and then we have here a tension that goes to the pulley B. That one is different from the tension in the string, so we're going to call this TB. And then we have object 2. Oh, and of course, our I hat goes in this direction because it follows the motion of the object. We have here kind of the reverse. Now we have a tension of this string here that's attached to pulley A, but it's different from the string tension. That's a specific one, TA. And we also have a T from the string here, so add a T. And then if we look at pulley A, we have 2 string tensions, T and T, and here we again have a TA, and pulley B, TB, and 2T over here. So that means we can write down our equations of motions using Newton's second law, F equals ma. And since this is just going in the I hat direction, we can just write it down, the 4 equations following the 4 free body diagrams here. So we have F minus TB equals M1 A1, A1. We have T plus TA equals M2 A2. Then we have 2T minus TA equals 0. That is 0 because we're dealing with 2 massless pulleys there. That means M is 0, and so our acceleration term is 0. So the M is 0 here. And finally, we have TB minus 2T. Oh, not 2 pi, 2T. And that one is also 0 because it is a massless pulley. So here we have our 4 equations of motion that fully govern this pulley system. And we can use it then, for example, to find this pulling force here. We know what TB is from the equation down here, so 2T. We know what TA is. It's also 2T. And we can then solve this for F. The only sticky part is that we have this A1 and the A2 in here. But for that, we derive this constraint condition here. So with that one, we can fully solve this. Otherwise, we would have one too many unknowns. Alternatively, if one were to be interested in one of these accelerations, then this equation system can also be solved for A1 or A2.
Okay, makes sense.
Okay, well, I like to lay in the hammock in the summer, and this is our version of that hammock. So we're having 1 rope, or perhaps 2 ropes, hanging between 2 trees here, and they span an angle theta on each side here. And we want to know what is the tension in this rope at the midpoint, and here right where it is attached to the tree. And here we already have the free body diagram. I just drew this piece of the rope here that's hanging on this tree here. And we made an imaginary cut. We just cut it in the middle, which means gravity is obviously acting on it. It's hanging through, and but it does so with m half here for our half rope. We know that there's a tension here at the midpoint, T mid. And up here we have a tension at that endpoint that goes under this angle here. I just use an ordinary Cartesian coordinate system with the I hat direction going in the x direction and j hat going in the y direction. So all we need to do is we need to apply Newton's second law and do an F equals A analysis to figure out what these tensions are. So let's apply Newton's second law, the F equals ma analysis, to figure out what the tensions are at the midpoint and at the end over there. So we have F equals ma. And we'll have to very carefully separate the components here. Let's start with I hat. We have T mid minus T end. But of course, we have only the projection of T end, so this is T end sine theta.
Sine theta,
and
yeah.
since this rope is just hanging there, the acceleration is 0. In the
Okay.
j hat direction, we have minus m half g, and then plus T end, and here we have the cos theta component, and that is also 0. So we see from here, pretty much immediately, that T end equals m half g over cos theta. And we can stick this one here into the I hat equation. So we'll get T mid equals m half cos theta g sine theta. And that's nothing else but mg over 2 tangent theta.
We've seen previously that if a rope is under tension and we approximate the rope as massless, that the tension is then uniform everywhere along the rope, even if the rope is accelerated. However, if the rope has non-zero mass, then its tension will vary along its length. We can see that by looking at this example. Imagine we have a massive rope of length L suspended from a ceiling. Now, it's easy to see that at the top of the rope, a little element of rope right at the top has to support the entire weight of the entire rope. So if I were to examine just a little piece at the top here, the weight of the entire rope would be acting downwards. And for the rope to remain stationary, there has to be a tension upward. I'll call this T top because this is at the top of the rope. And so we see immediately from that at the top of the rope, the tension is just equal to mg, where m is the mass of the entire rope. Similarly, if we ask what the tension is at the bottom of the rope, an element right at the bottom of the rope isn't supporting any weight because there's no weight below it. And so at the bottom, the tension is 0 because there's no weight pulling on the bottom of the rope. So the tension is going to vary from mg at the top down to 0 at the bottom. And if we wanted to work out at some distance from the ceiling, let's call it x, at some position x, say here, what the tension is at that point, one way of figuring that out would just be, imagine we cut the rope at this point and then ask what tension force would be necessary to support this bottom part of the rope. This length is L minus x, so the mass of that fraction of the rope is L minus x over L, and the mass of that fraction of the rope is that fraction times m. And so the tension at this point, T at x, is equal to the weight of the length of rope below that point. So that's this mass times g. And I can rewrite that as 1 minus x over L times mg. Okay? And this gives me mg if I put in x equals 0, and it gives me 0 if I put in x equals L. So that's one way of figuring this out. I'd like to use the same example, though, to introduce another more elegant way of analyzing what the tension is as a function of position on this rope. And the advantage, so this is going to be a little bit more complicated, but it's a much more powerful method, and it's one that we can generally use for any continuous distribution of mass as opposed to a point mass. So let's consider the same example again of a hanging massive rope of length L and mass m. So here's the length L and the mass m. And the approach we're going to use is called differential analysis. It's a technique from calculus, and it's applicable to any continuous distribution of mass. What we're going to do is imagine our continuous distribution of mass is made up of a whole bunch of little pieces, little elements, examine F equals ma acting on a single element, and then generalize to the entire mass. So let's do that here. What we'll do is we'll examine a piece at some position x. So I'm measuring x from the top. And let's say I define a little element here, which is at position x, and which has an extent delta x. So this thickness is delta x, and we'll call the mass of that little piece, that little element delta m. Okay? Now, one thing I want to point out to begin with is that we want to pick an element that's somewhere in the middle of the distribution, not at one end or the other. The endpoints are special cases. So we want to pick a general case, so choose some x somewhere in the middle of our distribution, and which has a finite extent. That extent is delta x. In this case, we'll assume that that piece delta x has a mass delta m. So let's blow that up here and analyze it. So here's my element. And it's going to have, let's analyze what the forces acting on it are. So there's gravity acting downwards, which will be delta m times g. There's a tension acting upwards exerted by the rope above it. This is, I'll write that as t of x because it's at the location x. There's also a tension exerted in the downward direction by the remainder of the rope below the mass element. And I'll call that T of x plus delta x. We expect the tension to vary along the rope, and because this element does have a finite extent, the tension at the bottom is going to be slightly different than the tension at the top. Okay? So T of x upwards, T of x plus delta x downwards, and then the weight downwards. All right, so that's our free body diagram. Let's write down Newton's second law, F equals ma, for that mass element. So in the positive direction, which is downward, we have T of x plus delta x plus delta mg, and then in the upward or minus direction, we have minus T of x. So those are the combined forces. Now this rope is suspended, it's not moving, and so the mass on acceleration is just 0. Okay? I'm going to rearrange that. I can write that as T of x plus delta x minus T of x is equal to minus delta m times g. And by the way, let me remind you, if this were a massless rope, then delta m would be 0, and so the right-hand side would be 0, and the tension would be uniform. We'd have the same tension above and below. But because the rope does have mass, and in particular this element has a non-zero mass delta m, there's a difference in the tensions. Okay, now our delta m can be represented in terms of what this length is. Notice that that mass delta m, so note that delta m is just a fraction of the total mass that's in that particular mass element. Well, the fraction of the total rope is just the length of this element, delta x, divided by the length of the entire rope, which is L. So that's the fraction, and I multiply that by the total mass. So that is my mass delta m in terms of the length. So now I can rewrite this equation as T of x plus delta x minus T of x is equal to minus delta x m over L times g. Now, I'm going to rearrange this by dividing both sides by delta x. I'll do that over here. So we have T of x plus delta x minus T of x divided by delta x is equal to minus mg over L. This tells us how the tension is varying over this small but finite-sized mass element, delta x. Now, I'd like to examine what happens if I go to the limit of a small mass element, where, so the limit as delta x goes to 0, or in other words, the limit of an infinitesimally small mass element. So I'm going to take a limit of this equation as delta x approaches 0. Now, the left-hand side of this equation should look familiar. It's just an expression for the derivative of the tension T as a function of position. So I can write that as dt dx, and that's equal to minus mg over L. This is an example of a differential equation, or an equation that involves a derivative. This particular differential equation can be solved very simply by a technique called the separation of variables, where I just take each part of the integral of dt over dx and put it on different sides of the equation, and then integrate both sides of the equation to find the solution. So in this case, I'll multiply both sides of the equation by dx, so I get dt on the left-hand side is equal to minus mg over L dx. And now I want to integrate both sides, so I'll integrate this side, and remember mg over L is a constant, so I can keep it outside the integral. And I'll integrate this side. I'm going to do a definite integral over the continuous distribution that I'm studying. So on the right-hand side, I'm going to start at x equals 0 and go to my position of interest, which is x. And to avoid confusion, I'm going to call the integration variable dx prime. This is a dummy variable. So x prime here represents all the values of position ranging from my first endpoint 0 up to my other endpoint x. Okay, so x here represents a particular position, whereas dx prime is a placeholder for all the positions between the two endpoints in my infinite sum, which is an integral. Okay, so that's on the right-hand side. On the left-hand side, I'm integrating the tension t with respect to the tension t. My limits need to correspond to the limits on the right-hand side integral. Okay, so on the right-hand side, my lower limit is at x equals 0. So on the left-hand side, I want to have my lower limit be the tension at that position x equals 0. So that's t of 0. And then the upper limit of the integral is the tension at the upper limit of the position integral. So that's t of x. And again, to avoid confusion, I'm actually going to call the integration variable dt prime. This is a dummy variable. It's a placeholder for all the values of tension from the tension at x equals 0 to the tension at my position of interest x. Okay, so this integral now tells me how the tension is varying in a continuous fashion along this continuous mass distribution. So now I can evaluate both integrals. On this side, I have the integral of a constant with respect to the tension, and so that's just going to give me t of x minus t of 0. And that's equal to minus mg over L. The integral of dx prime from 0 to x is just x. Okay, so this tells me how the tension changes from the endpoint to some arbitrary position x. If I want to actually solve for t of x, I need to specify what the tension is at the endpoint. But we know what the tension is at the endpoint. We found that earlier. We solved from the simple argument that at the endpoint, the tension here is just equal to the weight of the entire length of rope below that point. So we know that t at x equals 0 is just equal to mg, and therefore the tension at position x is just, if I bring t of 0 to the side, is just mg minus mg x over L. And so I can just write that as mg times 1 minus x over L. So that tells me what the tension is as a function of position. Note again that if I put in x equals 0, I just get mg. If I put in x equals L, I get the tension is 0. And for any point in between, we see that the tension varies smoothly between mg and 0. This is exactly the same result we found earlier by just cutting the rope at x and asking how do we balance the weight of the remaining rope below that point. But the advantage of this technique, which is a little bit more complicated, is that it's a very powerful technique applicable to any continuous distribution of mass. So in this specific problem, if instead of the uniform density rope that we had here, imagine we had a clumpy rope where the mass of the rope wasn't distributed smoothly, but was, there were clumps, there were little parts of the rope that were heavier than others, and so the density of the rope varied with position along the rope. In that case, we would represent that when we were writing what our mass element delta m is. Delta m, instead of just being delta x over L times m, where here delta x over L is the uniform density of the rope, we would have to put in some position-dependent density. So delta m would depend upon position. And then when I did this integral, instead of a constant out front with my integral of dx prime, I would have something that was a function of x, and I'd get a different value for the integral. But the technique would still work. So this differential analysis technique is applicable to any system where we have a continuous mass distribution. And we're going to actually use this technique over and over again in this course. We'll see it a number of times. This is just the first instance we're using it. We want to introduce you carefully to the approach.
Okay, that makes perfect sense.
In many problems throughout this class, we will find it useful to consider how the mass of an object is distributed throughout the object. To do this, we will define a small piece of that object, and then consider the mass that's contained within that small piece. For an object in one dimension, the differential element of length is delta L, and that length contains a certain amount of mass, delta M. We could also have a linear object in the shape of an arc, or just an arbitrary path. For an object in two dimensions, we have an area element, delta A, that contains a mass, delta M. For a volume, we have a volume element, delta V, which contains a certain amount of mass. In this case, we can write the volume element, delta V, as the area, A, times this delta X. We want to relate the small length, area, or volume element to delta M, the amount of mass contained within. In one dimension, this relation is called the linear density, lambda, which is delta M over delta L. For a uniform rod of length L and total mass M, lambda is equal to M over L. In two dimensions, the area element contains an amount of mass sigma times delta A, where sigma has units of mass over area. Finally, in three dimensions, the volume density, rho, connects the small mass, delta M, to the volume, delta V.
So let me summarize what the steps that we've taken are to do this differential analysis. So when you're trying to analyze a continuous mass distribution, the first step is to pick some arbitrary mass element, a small but finite size mass element, somewhere in the middle of the mass distribution. You don't want to pick one of the endpoints because the endpoints are special. You want to pick an arbitrary point somewhere in the middle, and then pick a small mass element at that point, so small but finite size. Analyze the forces acting on that mass element, the right down Newton's second law, the equation of motion for that mass element. That will give you what the action is, what the forces are on that element. Then go to the limit of an infinitesimally small element. That will give you a differential equation. You can then separate the differential equation and integrate both sides to solve the differential equation. And then finally, you can apply a boundary condition, something you know about one or the other of the endpoints, and that will allow you to solve for the function of interest at any point along your distribution.
We would now like to discuss drag forces in a fluid. Now, remember that fluids can be both a liquid or air. And drag forces are actually quite complicated, depending on a lot of factors. If we had an object falling in a fluid, the drag forces can depend on both the properties of the object, and in that case, it might be the speed, or the size, or the shape of the object. And it also can depend on the properties of the fluid. It can depend on the density of the fluid. It can depend on a property that measures the resistance of the fluid, something which we'll refer to as viscosity, and also a property about the compressibility of the fluid. So in general, this is quite complicated. And this is done empirically. There's a few very special cases that we'll discuss that can be solved exactly. Now, let's begin our modeling by considering what we call air drag. Now, in air drag, objects that are moving, and we'll consider objects that are moving rapidly. So our objects are moving very fast. Now, in that case, we can make a rough model of the air drag as follows. The magnitude of this force is going to be proportional to the speed squared.
Hey,
So the
Bonzi!
factor where it's the cross-sectional area that the object presents in the motion perpendicular to the plane of motion. It can depend on the density of the air. And traditionally, there are a couple of coefficients in here that are dimensionless that are empirically determined by the shape of the object, and that's called the drag coefficient. And in fact, there's also a factor 1/2 in Wave's law.
It's cooking
So what
physics.
we have here is a resistive force,
Physics
which is
is
proportional
cooking.
to the speed squared, and depends on the properties of the
I'm
air,
doing
the
all
density
of
the air,
physics
and some physical parameter properties of the object
until
itself.
there's
Now, this
nothing
drag coefficient,
left.
we can have a table that can represent that, and you can see here that for a variety of different shapes, the drag coefficient is somewhere on the order of 1. So this is an example of what we refer to as air drag. When we drop objects in a fluid at very slow speeds, we have a different effect than what we talked about air drag. For example, if we drop a marble in molasses and drop the same marble in water, we see a very different motion. And that depends on a property of the fluid, which we'll refer to as viscosity. Now, we'll denote a coefficient of viscosity by the symbol n, eta. Now, when we drop an object in a fluid, that the drag force in magnitude will be proportional to both viscosity, will be proportional to the speed, and it will be proportional to the viscosity. And now, for very special cases, so for the special case, which is a sphere of radius r, if you study fluid dynamics, we can get an exact solution for this drag force, and we'll describe that as it's going to be opposite the direction of the velocity, so there's a minus sign. There turns out to be some coefficients, 6 pi times the viscosity of the fluid times the radius of the sphere. And this particular law, which we'll known as Stokes' law, is exactly applicable to the motion of a sphere. Now, in fact, by experimental measurement, this is a method for determining eta experimentally by dropping spheres in various different media with different viscosity. So we can use this to experimentally determine the viscosity of the medium. And what's important to realize, too, is that this is applicable to many different examples.
Okay.
We'd like to consider velocity-dependent resistive forces. So let's imagine a situation where we have an object, and it's falling in a gravitational field, so we have a gravitational force. And this object is like a marble falling in a vat of oil, and there is a velocity-dependent resistive force that is acting on this object. And let's again choose a positive direction down. And now, for objects that are moving very slowly in a fluid, let's make a model for our velocity-dependent resistive force. We'll assume that the resistive force is proportional to the velocity, it's opposing the direction of motion, and we'll put a coefficient alpha in front. And this is our model for velocity-dependent resistive forces for objects that are moving very slowly. For our case, let's consider the units of the coefficient alpha. So the units of alpha have the units of force divided by velocity. So the units of force are, we have the units of force divided by the units of velocity, and that gives us kilogram meter per second squared, divided by the units of velocity, which are velocity per second. And so we see that the coefficient of alpha has the units of kilogram per inverse second. Now what we'd like to do is apply Newton's second law. So let's analyze the forces and get the equation of motion for this object falling in a viscous medium with resistive force. In the j-height direction, we have the gravitational force, and we have our resistive friction force, which we're writing Vy as the y component of the velocity, and that's equal to m times dvy dt. Now notice that the acceleration we're not treating as a constant, it's the derivative of the velocity. This leads us to our differential equation, which is written as dy dt. I'll divide through by m, g minus alpha over m vy. Now this is a linear velocity first order differential equation with a constant term in here, which is called inhomogeneous linear first order differential equation. We shall solve this like we did with our other equations by separation of variables. So what we do is we bring the velocity terms to one side and the time terms to the other side, and now we can integrate both sides directly. But before I integrate this side, I'd like to rewrite it by writing it as dvy, and I'd like to pull out a minus alpha over m, and this term here becomes minus mg over alpha. Why did I do this? For the integration, it just makes my natural logarithm integral look a little bit easier. And over here, I have dt. Now what I want to do is integrate, and we're going to integrate from some initial velocity, which we're going to take to be 0. We're going to drop this, let this object be released from rest, and we're going to integrate to some final speed vy of t. Over here, let's just call our integration variable t prime, and we integrate t prime from 0 to some time t. So this is our variable, and the velocity is a function of time. Now, doing this integral, first off, this constant term comes out, so we have 1 over minus alpha over m, and the integral is just a natural log integral of vy minus mg over alpha, and we have to divide that in the lower limit, vy is 0, and we have just minus mg over alpha, and this side is very simply t. Now, we can rewrite this equation by bringing the m over alpha to the other side, and we have log of vy minus mg alpha over minus mg alpha equals minus alpha m t. Now recall that e to the log of any quantity x is equal to x. So if I exponentiate both sides, I get vy minus mg over alpha divided by minus mg alpha is equal to the exponential e to the minus alpha mt. Now the last step is simply to bring this over to there, multiply, and do a little bit of algebra. And so I get that the velocity as a function of y is equal to mg alpha times 1 minus e to the minus alpha mt. Now there's a few interesting things here that we want to look at. Suppose we define this exponential e to the minus alpha mt as equal to e to the minus t over tau, where tau is m over alpha. The units of tau, when we look at the units, it has the units of mass, which is kilograms, over the units of alpha, which we worked out before. So we have kilograms over kilogram inverse second. That gives us units of seconds, and that's what we expect because t, seconds over seconds, gives us a dimensionless quantity for the exponential. Now, the last thing we'd like to look at is let's just see what happens when we plot this. Well, if we're plotting vy as a function of t, we start off at 0, and we're going to reach some terminal quantity, vy terminal, which is when we have a graph like that. And we can see what that terminal speed is. When we set t equal to infinity, e to the minus infinity is 0. And so this terminal speed is equal to just this coefficient, mg over alpha. And that's the terminal speed. Now, notice that as a check for what we did, we can come back to our differential equation. And what does terminal speed mean? Notice that when you get to this limit as t approaches infinity, the slope of the velocity curve is 0. And that's really the statement over here that vy terminal is when the velocity is no longer changing in time. You can see it graphically. And this is the statement, when we go back to Newton's second law, that there's acceleration is 0, so the sum of the forces at terminal speed are 0. The resistive force is equal to the gravitational force. And so from this equation here, as a check, we can see that vy terminal equals mg over alpha, which checks with our calculation. And so we have confidence that we analyze this correctly. And that gives us our motion. One last thing that's quite interesting. Notice that the terminal speed depends on mass. This coefficient alpha is only a function of the properties of the object, the size, the shape, the geometric properties of the object, not how dense it is. So if you had two objects, like two balls, same radius, but one was denser than the other, then the other one mass would be heavier, and the terminal speed would be greater. So what we see is that two identical objects, one heavier than the other, the heavier object reaches a faster terminal speed than the lighter object, which explains a well-observed phenomenon.
It does. Yeah, absolutely does.
Now we're going to analyze a more complicated example of drag forces, where we have an object falling free in a gravitational field with gravity. We have a resistive force, and this is an object in air, and so our model will be for the resistive force that it's going to be proportional to the velocity squared. Now, to get its direction right, opposing motion, j hat. So this will turn out to be a more complicated analysis. But first again, let's think about the units of our coefficient beta. It has the units of force divided by velocity squared. So we write the units of force, kilogram meters per second squared, and the units of velocity squared, meter squared per second squared. And so we see that we have units of kilogram per meter for our coefficient beta. Now, we'll apply, as usual, Newton's second law, F equals ma, to get our equation of motion. We're looking at the j direction, and our forces are gravity minus the velocity squared resistive drag force, and that's equal to the derivative of the velocity dv dt. In this example, it's a one-dimensional motion, so I'm dropping any mention of our y direction for simplicity. Now we can rewrite this equation as dv dt. Let's divide through by m is g minus beta over m v squared, and this is a linear, it's a first-order differential equation, dv dt. It's a nonlinear equation because the velocity term appears here as a square, and there's a constant term. But we can still apply our technique of separation of variables, and so we'll rewrite this equation as dv dt. We'll separate out the dv's and the t's. So we have dv times g minus beta over m v squared is equal to dt. Now I'm going to do two things just to clean this up for algebra a little bit later. I'm going to multiply both sides by a minus sign, and I'm going to pull the g out. So I have 1 minus beta over mg v squared. And on the other side, I have minus dt. And now I can get this equation in the form that I'd like to integrate, which is minus dv times 1 minus beta over mg v squared equals minus g dt. Now, the trouble here is this integral is a little bit complicated, so I'd like to make a change of variables. And my change of variables will be u equals the square root of beta mg times v. And that implies that du is beta mg dv. And the limits, if we start our object at rest, so if u naught equals 0, then because v naught equals 0, that's our first limit. Now, we have to be a little bit careful because if we drop this object at rest, initially it will be moving very slowly. And so our resistive model doesn't actually apply. However, we're going to neglect that effect. Even though if we were to do a more complicated analysis, we would have to change our model as the object is falling. So it will be a multi-stage motion, first at the beginning with our only velocity-dependent resistance, and then as it gets some initial speed and it's going faster, we change our model. That's why the actual problem can be quite complicated, but we're just trying to keep things simple here. And then u at t is square root of beta mg v of t. And then with this change of variables, my integration, remember I have a dv, so I have to multiply the left side by mg over beta, and I'm integrating with a minus sign, du times 1 minus u squared from 0 to this final value, u of t. And over here, I'm just integrating minus g dt. Now, again, for simplicity, I'm going to bring this term, the beta over mg, over to the other side. So I'll use the magic of our whiteboard by just erasing that and bringing it to the other side, which makes my life a little easier. And now, this integral can be done by the method of integration by parts. It's a nice problem in calculus, and you can verify for yourself that the result is 1/2 natural log of 1 plus u over 1 minus u evaluated at our limits. And over here, I have minus g square root of beta over mg. Now, once again, for a little bit of simplicity, I'm going to bring the 2 over to the other side. And now I evaluate my limits. Now recall that when you have a minus log, we're flipping, because log of b over a equals minus log over ab. So when I put out my limits in, I have natural log of, now remember, what are our limits? We have 1, I'm flipping, minus u is beta mg times b of t, and I have the 1 plus beta mg b of t, and that's equal to minus 2g square root of beta mg. Now, again, we'll use the fact that, that e to the log of x is x, and so if I exponentiate both sides, I end up with 1 minus square root of beta mg b of t over 1 plus square root of beta mg b of t is equal to exponential minus 2g beta mg times t. And just remove that. Okay, now this is a little bit of algebra. I want to solve for v of t. If I bring this side over to there, I'll just do that to make the first step a little simpler to see. So we have 1 minus square root of beta mg b of t equals 1 plus square root of beta over mg b of t times e to the minus this factor 2g square root of beta mg t. Now, this is a lot of stuff to carry around. I'd like to introduce a constant here, tau, which I'm going to define to be square root of mg beta 1 over 2g. And so this whole term is going to just be e to the minus tau. It's a nice example for you to work out that the units of tau are the units of seconds. And that's a little exercise to work out. Now, I just have to collect my terms. And what I'll do is I'll collect the t terms on the right and the terms that don't have dt on the left. So I have 1 minus e to the minus t over tau on the left is equal to 1 plus e to the minus t over tau on the right times beta mg b of t. And so I get my solution, b of t equals the square root of mg over beta times 1 minus e to the minus t over tau over 1 plus e to the minus t over tau. Well, it's not a simple solution at all, but let's examine when you have a case like this. Again, it would be a nice exercise to graph this out, but right now we're going to consider the limit as t goes to infinity. And remember that e minus t over t goes to 0 when t goes to infinity. So we just have 1 over 1, and what we get as t goes to infinity is the quantity mg over beta, and this is what we call the terminal velocity. Now, what does terminal velocity mean? Well, when an object is falling and there's a resistive force, as the object falls faster and faster, the resistive force gets greater and greater until, if we go back to Newton's second law and look at it, as the v gets faster and faster, eventually these two terms are equal. And when these two terms are equal, that's the statement that the right-hand side has to be 0. So what we mean by terminal velocity is the velocity is no longer changing in time. And then we can immediately check our work by going to Newton's second law and see what that case is if we set this quantity equal to 0. In other words, when we set mg minus beta v squared terminal equal to 0, we can solve for v terminal, and we get square root of mg divided by beta, and that agrees with our lengthy calculation.
Yes.
So we think we're on the right track.
It does. You're on the right track.
Up until now, we have analyzed the motion of objects that we treated as so-called point masses, where literally all of the mass of the object was treated as lying at a single point. This is obviously an unrealistic idealization. Real objects have spatial extent and come in various sizes and shapes, some regular and some highly irregular. The mass distribution within these extended objects might be smooth and uniform, or highly non-uniform and lumpy. Moreover, sometimes we will be interested in simultaneously analyzing a large system of particles or objects. To deal properly with such situations, it is necessary to introduce a new physical quantity called the momentum, which is a vector that we traditionally denote with the symbol p. For a single point mass, the momentum is the product of the mass and the velocity vector. The form of Newton's second law that we have used so far, F equals ma, is actually only true for the special case of a point mass. The more general form of Newton's second law is that F equals dp dt. That is, that the force is equal to the time derivative of the momentum vector. This is applicable to either a single particle or to a system of particles. This more general form provides us the way to address extended objects or multi-particle systems. We will once again appeal to a calculus-like argument, breaking down an extended distribution into a large number of small elements, treating each element separately, and then summing the results. As part of this process, we will introduce the concept of the center of mass, a sort of mass-weighted average position for an extended object or system. Momentum is also the first of several special measurable quantities that we will discuss that obey special, powerful rules called conservation laws. The other two quantities are energy and angular momentum. Conservation laws are principles that provide that the given measurable quantity remains unchanged during the evolution of a system with time, as long as certain requirements are met, essentially the requirement that the system remains isolated. With this restriction in place, the possible evolution of motion of a particle or system of particles is greatly restricted, simplifying this calculation. We will see how this can be used to our advantage in understanding what will happen.
Okay, makes sense. Momentum.
So suppose we have a point mass particle of mass m moving with a velocity vector v. We can introduce a quantity we call the momentum of that particle. I'll label it with the symbol p, and it's equal to the product of the mass
mv
times the velocity. This is something you've undoubtedly seen before. Now let's think about the dimensions of momentum for a moment. So dimensionally, momentum has units of mass times the velocity, and so that's in SI units, the units of mass are kilograms, and the units of velocity are meters per second. You can also express momentum dimensionally as a product of a force times time. And so again, in SI units, the units of force are the Newton, and the units of time is the second. Right? So these are the SI units for momentum, two different ways of writing the same dimensions. Now we've seen that for a single particle, we can write Newton's second law as the force is equal to the mass times the acceleration, or equivalently, we can write that as the mass times the time derivative of the acceleration, dv dt. Now if m is a constant, then I can rewrite this as f is equal to the time derivative of mass times velocity, or equivalently as the time derivative of momentum, since mv is just equal to p. Okay? So I actually want to stress this, I'm not going to put it in a box because it's very important, that I can write Newton's second law instead of f equals ma as f equals the time derivative of the momentum. And this is actually where we'll see the momentum becomes very useful. Because it turns out that this form of Newton's second law is actually the most general form of the equation, because it's applicable not just to a single point mass, but also to a more complicated system, a system consisting of many masses, or a system where the mass is changing, or where mass is flowing, as in a fluid. In all of those cases, this form of Newton's second law is correct. F equals ma, which is probably more familiar to you, is actually a special case of this law for the case of a single point mass. So this is where we'll see that momentum is quite a useful concept, especially as we start considering more complicated systems, as we'll get to a little later in the course. What I'd like to do now, though, is to take a closer look at this equation. Force is equal to the time derivative of the momentum. Whenever we have a relation involving a derivative like this, we can always also rewrite it in an equivalent integral form, which can be very useful and give us a different way of looking at the same information. So let's take a look at that. So if I take this equation and integrate both sides with respect to time, then I can write that as the integral of f with respect to time is equal to the integral of the right-hand side, dp dt, with respect to time. And let's make this a definite integral. I'll go from time t1 to time t2 on both sides here. Okay. Now this right-hand side is just, so the integral of dp dt with respect to time is just p at time 2 minus p at time 1, and that is just the change in the momentum vector going from time 1 to time 2. Now this integral on the left-hand side, we give a special name. We call this the impulse. This name, impulse, calls to mind a short, sharp shock of some sort, but it can also refer to a weak force acting over a long interval. And notice here, the function f, the force f, is in general a function of time. Okay, so this doesn't necessarily mean a constant f, this can mean a force that's varying in time. And what this equation tells us is that the change in the momentum of the system doesn't depend on the detailed time dependence of f, but rather just on the integral of f. And so suppose I were to graph the force as a function of time going from time 0 to a time delta t, and suppose I had some complicated function that looked like that. The impulse is just the area under this curve. It's the integral of this function. That's the impulse. And the change in the momentum depends only on the area under this curve and not on the detailed shape of the curve. So what that means is that I can define an average force by choosing a constant force that has the same area as this example on the left. So suppose I calculate that, and there's some constant force here. I'll call this f average, going over the same time interval. The average force is that constant force which has the same area as the area under my f of t. So in other words, f average times delta t, which is the area on the right-hand side here, is equal to the integral of f of t dt integrated from 0 to delta t, okay, which is the area under this right-hand curve. And so my average force is just that integral f of t dt divided by delta t, and this is integrated from 0 to delta t. So that's my average force.
We would now like to use Newton's second law to relate impulse to change in momentum. So again, let's look at our setup. We have an object m of velocity v, and let's say here the picture as t initial, and we have some initial velocity, and then a little bit later in time, we have at time t final, the moment the velocity has changed, and that's because throughout this time interval, we're applying an impulse. We can call this the I hat direction. Now, recall that our definition of impulse is a vector quantity. It's equal to the integral of the force. Now, when I write force of t, I mean force as a function of time, and that's our dummy variable t prime. It's not force times time, but force as a function of time, and we're integrating from the initial to the final time period. Now, here's where we use the version of Newton's second law, which is that force causes the momentum of an object to change. So we can write this integral t prime, t initial, t prime equals t final of dp dt. I'll just make a note that we've now applied Newton's second law, and because we're using our dummy variable dt prime, and you can see that the two dt primes cancel, and this just becomes the integral from t initial, t prime to t final of dp, and this is a pure differential, and so we end up with impulse is the momentum at t final minus the momentum at t initial. Now, recall, this is a vector integral, but a vector integral is just 3 separate integrals for each component. So each component of impulse satisfies this equation. For instance, the x component of impulse is how the x component of momentum is changing in time. Now, generally, when we write a final momentum in our final state minus the momentum during the initial state, we can call this the change in momentum. So down here, we would have change in the x direction. And so in conclusion, we now have an integral way of casting Newton's second law. We have that impulse causes momentum to change, and so we can see that the SI units of impulse are the same as the SI units of momentum, which we saw before was kilogram meter inverse seconds.
Okay, makes sense.
Let's consider a ball that is dropped from a certain height, hi, above the ground, and this ball is falling. It hits the ground, and it bounces up until it reaches some final height, h final. Now, when the ball is colliding with the ground, there are collision forces, and in this problem, what we'd like to do is figure out what the average force of the ground is on the ball. So we'd like to find and that will be the normal force, the average normal force on the ball during the collision. Now, if we look at this ball dropping, it's going to lose a little bit of energy because it's getting compressed at the collision. Let's look at an example of the actual ball dropping. As you can see in this high-speed video, as the ball falls down, it collides with the ground. When it collides with the ground, it's compressed, and then as it rebounds upwards, the ball expands back to its original shape, but it doesn't quite get to the same height. That's because when the ball is compressed, there's some deformation in the rubber structure of the ball, and it's not a completely elastic deformation, and so some of the energy is transformed into, first, molecular motions, which turn into thermal energy that's radiated into the environment. let's look in particular at the details of the collision. If we look at it in slow motion, what we have here, and I'll draw a picture, as the ball is colliding with the ground, the ball compresses, expands as it goes upwards, and so we can draw a free body diagram on the ball with a normal force and a gravitational force. Now let's choose our positive direction up. So now what we'd like to do is apply the momentum principle to analyze the average normal force. And our momentum principle, remember, is impulse. The force integrated over some time during the collision is equal to the change in momentum. So what we'd like to do is identify the states that are relevant. So we'll have a state before. So what we'll do is we'll call this the before state. And that's right before the ball is hitting the ground. And we have an after state. And in the after state, the ball has now finished colliding with the ground, and it's now moving up with speed up. Now, again, we're going to choose positive up. Here, I'm representing things as speeds. One of the things, we need some times here. So let's say that at t initial is 0. This is our final time. We'll call this time the before time. We'll just call this t before, and this is t after. And then our integral is going from before to after of the momentum, and we can now apply the momentum principle. Well, this is a vector equation, and we've chosen unit vectors up. So what we have here is the integral of from t before to t after of n minus mg integrated over dt, and that's equal to the momentum at the y component of the momentum at t after minus the y component of the momentum. We don't have a vector here anymore. The y component of the vector t before. And so this is our expression of the momentum principle. Impulse causes momentum to change. Now we're assuming that the normal force is just averaging it, and so this integral simply becomes n average minus mg times the time of collision is equal to, now in here, we can put the mass of the ball, we have the velocity. Now here's where we have to be a little bit careful, because we're looking at the y component. We chose speed downwards, that's in the negative y direction, so we have we're looking at v after, we have plus v after, because this is going in the positive j hat direction. And over here, we have negative mass, but it's going in the minus direction, so we have minus mv before, and so we get mass times v after plus v before. So our first result is that the normal force average, let's bring the divide through by delta t and bring the mg term over, so we have mva plus vb divided by delta t plus mg. So we see that if the collision time is very short, then this average force is a little bit bigger. A long collision time, the average force a little bit smaller. Now from kinematics, we already have worked out the problem that the speed for an object that rises to a height h final, this is the velocity afterwards, is just square root of 2g h final. And in a similar way, if an object is falling a height hi, the speed when it gets to the bottom is 2g hi. And so now we can conclude with these substitutions that the average force equals m times square root of 2g h final plus square root of 2g h initial over the collision time plus mg. And of course the collision time we're saying is t after minus t before. And so that's how we can use the momentum principle to get an average expression for the normal force. Let's now extend our concept of momentum to a system of particles. Again, we need to choose a reference frame, so we'll have a ground frame, and let's consider n particles. Now, when we have a lot of particles, we need some type of notation. So let's use the symbol j, and it will go from 1 to n. And then our arbitrary jth particle will be moving, this particle will have mass mj, and it will be moving with a velocity vj. Now recall in our system we have many other particles. We can call that one 1, this one, and we have lots of different particles in the system. And this just represents an arbitrary particle in that system. And the momentum of the jth particle is just the mass mj times the velocity vj. And again, we're assuming some fixed reference frame. So the total momentum of the system, we now have to add up the momentum of all the particles, all the way up to the nth particle. Now, when we make a sum like this, there's a standard mathematical summation notation, which we'll write like this. We'll do the sum, this capital sigma sign, of j goes from 1 to j goes to n, of the momentum of the jth particle, and that represents the sum j goes from 1 to n of mj vj. And this is what we call the momentum of the system. This is a vector sum. And now let's see how Newton's second law applies to the momentum of the system. Suppose that acting on our particles, for instance, here's our jth particle, we have a force Fj acting on the jth particle. Then we know that from Newton's law that the force will be also the sum of the forces on all the particles, F1, F2, plus dot, 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 plus Fn. So once again, we can write this as a sum, j goes from 1 to n, of the force on the jth particle, and that's the force on the summing of all the forces on all the particles in the system. But now we can apply Newton's second law. So Newton's second law is the statement that the force on the jth particle causes the momentum of the jth particle to change. And when we write that now, the total force on the system, j goes from 1 to n, is just the sum of the change in momentums. Because every single term, let's just look at that, t1 plus dp2 dt plus dot, 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 plus dpn dt, that's what we mean by the sum. We can rewrite this as d by dt of p1 plus p2 plus p3 plus dot, 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 plus pn. And what we see is that the total force is the derivative of the sum, j goes from 1 to n, of the momentum. But recall, this sum we've defined as the momentum of the system, so our conclusion is the total force causes the momentum of the system to change. Now, so far, all we've done is we've recast Newton's second law in this form. Our next step is to analyze the forces on the individual particles and apply Newton's third law. So we'll do that next.
All right.
We now would like to analyze in more depth our result that for a system of particles, so let's indicate our system. We have particle 1, we have our jth particle, and we'll have our particle n. So here's our system of particles, where the total force caused the momentum of the system of particles to change. Now, I'd like to examine that concept of the total force. Before we said that our total force on the jth particle, we just wrote it like this, and I'm going to put a little t up here for the moment. Because when we examine what force we mean here, and I also want to put a little boundary around our system. And let's now consider another particle internal to the system. And let's try to identify the types of forces on the jth particle. We can really have two types of forces here. Our first force can be an interaction between these two particles. So what I'll write is the force on the jth particle due to the interaction between the k and the jth particle. And I'm going to put a little sign up here. I'm going to write this internal. What do I mean by internal? This is a force strictly between the internal particles in the system. Now, of course, we know that there must be a force on the kth particle due to the interaction between the jth and the kth particle, and we can call that internal. So what we have here is that we can divide, there can still be other forces acting on the jth particle, and we'll do a decomposition like this. We'll say that the total force on the jth particle can come from some external forces. There could be an object outside our system. If these were interacting gravitationally, there could be a planet outside here, and this could be a moon, and our system is just the moons. That would be an external gravitational force plus the total internal forces. So I'm going to keep the same color, internal, on the jth particle. Now, how do we write this total internal force? Well, we're interested in the force on the jth particle, but the internal forces can come from all of the other particles in the system. So what we're looking here is for a sum over all of the possible interactions where the other particles k go from 1 to n, and we have to be very careful here that in this sum k cannot be equal to j. Now this sum, again, because it's a little bit tricky to understand, is the internal force on the jth particle. Here's the kth one, but this could be a sum. I'll just draw 1 here. This is the internal force on the jth particle due to particle number 1. And so we're adding, as k goes from 1 to n, all of these internal forces, but we're excluding the case when k equals j, because that would be a force of an object on itself. And this quantity here we can write as the total internal force on the jth particle. So in summary, we see that the total force on the jth particle is equal to the total external forces. I didn't say total there. I'm assuming there could be many different types of external forces, plus the total internal force. A little bit later on, we can drop the t's for simplicity of notation, but this is our big idea, that a force on the jth particle, external plus internal. And now, when we look at this sum, and we want to now apply our main idea, we have that the force, which we're writing as, let's explore this, our total force is the sum of the forces on the jth particle. And we've now done this decomposition. I'm going to drop total. So it's the sum of the external forces on the jth particle. J goes from 1 to n. And here we have a sum of the internal forces. So we have our sum j goes from 1 to n of the internal forces on the jth particle. Now we want to apply Newton's second law. And the concept is very straightforward, but the mathematical expression can be a little bit messy. We know by Newton's second law that the sum of a pair of internal forces is 0. Third law, by Newton's third law. So what we're saying here is, as an example, for Newton's third law, let's just focus on this particular pair, that F internal kj plus F internal jk is 0. So this is a statement that internal forces cancel in pairs. And so when I look at this total internal force, which is the sum of all of these pairs of internal forces, I can see that the total internal force has to be 0. So internal force cancel in pairs. Now here, we can see it another way. If we want to look at this notation, we took the sum, j goes from 1 to n, of F internal j. Now we use our definition for F internal. This is where things get a little bit messy. K goes from 1 to n, k not equal to j goes from 1 to n, F internal, k, j. This looks terribly messy. But what we're saying is this sum is just a sum of pairs. And every single pair in this sum adds to 0. So what we have for our statement now is that the total force is the sum of the external forces plus the sum of the internal forces, which we've now said that cancels in pairs. So let's rewrite that as the total force. Now, instead of writing the sum, let's write this as the sum of the external forces and the internal forces cancel in pairs. And so this is now our force on our system. It's only the external force. And now we can recast our Newton's second law for a system of particles with the following statement, that the external force causes the momentum of the system to change. And this becomes our expression for Newton's second law when we apply it to a system of particles, where the beauty of this idea is that no matter how complicated the interaction is inside the system, all of those interactive pairs sum to 0, and so only thing that matters is the external force in terms of changing the momentum of the system. And now we'll look at some applications of that.
Let's examine when the momentum of a system is constant and apply that to solving problems. First, we'll revisit the impulse equation. On the left, we have the impulse, the integral of the total external force acting on a system between some initial and final times. And on the right, we have the change in the total momentum of the system between those initial and final times. In a situation where the impulse is 0, we have that the change in the momentum is 0. P initial is equal to P final. In other words, the momentum of the system is constant between some initial and final time. This is a vector equation, but in many problems, we can set up our coordinate system, so we only have to consider one dimension. Here's a simple example of one block moving along a horizontal surface with some initial velocity, colliding with a block at rest, and then the two blocks stick together and move. Is momentum constant during this collision? To answer that question, we need to think about what our system is. Let's look at the system of both blocks together. We can see the external forces, gravity and the normal force, add up to 0, so our total external force is 0. During the collision, each block exerts a force on the other, but that is an internal force if both blocks are included in our system. You can see that if our system was just one of the two blocks, we would need to know the collision force in order to solve for the final speed. Therefore, we will choose our system to be the two blocks together. We then need to set up a coordinate system. We'll pick the origin here, and this direction will be positive x. Now we need to identify the initial and final states. Our initial state will be just before the blocks collide. The momentum of the system is the sum of the momentum of each block individually. We have m1 times v1 initial x times I hat, plus m2 times v2 initial x times I hat. This second term is 0, since block 2 starts at rest. The final state is right after the collision, when the two blocks are moving together.
Yeah.
They have the same velocity,
Yeah.
so the final momentum is m1 plus m2 times v final x times I hat. This gives us an equation that will allow us to solve for whatever quantity we are not given. Now let's look at a similar collision, one that's happening in 2 dimensions. If we have one block coming up from the bottom, hitting one that's coming in from the side, I'll choose my unit vectors to be like this, my origin here. The momentum equation gives us two equations, one along the x direction and the other along the y direction. Once again, I'll choose the initial state to be just before the collision, and the final state to be just after the collision. The momentum in the initial state is again the sum of the momentum of each block individually, and the momentum in the final state is the mass of the two blocks added together times the velocity of the two blocks. Notice that this velocity has a component in both the x and the y directions. Again, the total external force on the system is 0, so the impulse is 0 in both the x and y directions, and therefore momentum is conserved for both the x and y components. So I can write my two momentum equations like this. The impulse equation is a vector equation, so generically in 2 dimensions we will have two equations. We always need to check that the momentum is conserved in each direction separately, and it is possible to have a case where momentum is conserved in one direction but not the other, if we have some net external force in one direction. What would happen if, in our 1D collision example, the blocks now experience friction along the surface? Can we still assume that the momentum is conserved? In fact, if we pick a point in time right before the collision and compare that to a point in time right after the collision, we can see that the impulse from friction is over such a short period of time that the impulse is really, really small, and we can say that the momentum is approximately constant. If we consider times later after the collision is over, then momentum is certainly not conserved, which is what you would expect. You'll see the two blocks slow down due to friction. So even if there are other forces acting on the system, like friction or gravity, we can still calculate the result of a collision as if the momentum is constant during the collision by picking times only a very small delta t apart.
Makes sense.
We would like to now introduce a new methodological tool for analyzing problems that involve momentum transfers, and we call that tool momentum diagrams. Now, what we'd like to do is look at our fundamental idea, which was for discrete objects. We have that involved in a collision. We have that the external force integrated with respect to time, impulse, is equal to the change in momentum between two different states. So this is the momentum of the final state, and this is the momentum of the initial state. So when we want to analyze problems, how can we methodologically introduce a picture representation of our problem? So let's look at what we need to do first. We always need to choose a system that we're referring to. And with respect to the choice of that system, we need to also choose a reference frame. Now, once we've done that, we can now represent a collision with respect to this system. For instance, let's consider two objects as our system, object 1 and object 2. They're moving on a frictionless horizontal surface, and we're choosing as a reference frame the ground frame. Now, what we'd like to do is identify two states. So for our initial state, we'll have, if we're given some initial conditions, what we'd like to do is represent each object with a velocity vector. So here, we'll write v1 initial, and let's suppose this object is coming at it with v2 initial as an example. And once we've represented the velocities of the objects, we can write down their momentum in the initial state. Similarly, if these two objects collide and they're moving, we actually don't know which way those objects will end up moving. And so what we'd again like to do in our final state after this collision is to represent the velocities by, again, vectors. So this is v1 final, and this is v2 final. And then we can represent the change in momentum. So our momentum principle now becomes, in this case, let's just assume that the external force here sums to 0. We're assuming no friction. And then our momentum principle says that 0 equals p final minus p initial, and now we can read off those momentums as vectors on the diagram, and so what we have is that the final momentum will be equal to the initial momentum, so we can write down m1 final plus m2 v2 final is equal to m1 v1 initial plus m2 v2 initial. And that's how we can represent a collision where there's no external forces and use our momentum principle to get a vector equation. Now, in many problems you're given information. You might be given information about the speeds and magnitudes of the objects, and in order to then take this equation and represent it in speeds and directions or even components, we need to choose some coordinate system. So if we choose a coordinate system, and that's the third step. So suppose we choose a coordinate system. Then we can start to look at two different representations for our problem. For instance, let's just choose this to be the I hat direction. Now, given that choice, we could describe the velocities in terms of components. Now, this gets awkward, v1 I x component I hat. And similarly, we can write down all the velocities v2 I as v2 I x I hat, etc. for all the velocities. And our momentum equation in components then becomes, in the I hat direction, m1 v1 I x plus, well, here we have the final state, so let's make this consistent, the final, plus m2.
Okay, very boring stream. Don't worry.
2 b2 final x equals m1 b1 initial x plus m2 b2 initial x. And that's the same equation that we have as vectors, now expressed in terms of components, and recall that components can be positive or negative. Today we'd like to explore the idea of the center of mass or the center of gravity of a rigid object. For instance, take this rod, and if I try to balance it on my finger at a certain point in that rod, I'm balancing it via the gravitational force, and this point is often referred to as the center of gravity of the rod. Now, if we were in an empty space with no gravitational field, then center of gravity doesn't make any sense, but this point still coincides with what we call the center of mass of the object. And now I'd like to define center of mass. So let's consider our rigid body, and we'll just describe it as some object. We'll make it idealized, and that there's going to be trying to find some point in this object, and we'll identify that point as the center of mass. Now, let's imagine that this rigid body is made up of a bunch of little pieces. So we have mj, and this jth piece is located from the center of mass, a vector rcm. Now, how we want to define this particular point is that when we make the sum from j equals 1 to n over every single point in this body, then that will be 0, and this will be the definition of the center of mass. That when you add up the position vector with respect to this point, weighted by the mass, and you add up all of those vectors, you'll get 0. Now, if you don't know where the center of mass is, then this is difficult to calculate. So let's find a way where you choose an arbitrary point, and let's write that arbitrary point, say, over here. We'll write it like this, s, and we'll treat that as our origin. And I'll draw a vector rsj, and here I'll draw the vector rcm. And now what we have from our vector relationship is that the vector rsj equals the vector rcm, and that's what I want to find, plus the vector rcmj. And now let's add up, multiply each of these by the mass and make a sum. So we have mj rsj equals the sum of mj. Now, the vector rcm, this vector, no matter where we pick a point in this object, this vector is always the same, and that's why I pulled it out of the sum. And over here, I have the sum from j goes from 1 to n, j1 to n, of mj rcmj. Now recall, this is precisely how we define the center of mass point, that this is 0. And so we can now conclude that the center of mass, so you pick an arbitrary point, and if you want to find that vector to the center of mass, what you do is you make the sum from j goes from 1 to n of mj rsj, and you divide that by j goes from 1 to n mj. And this is what we call the center of mass. So conceptually, the center of mass is the point in the object where if you take a vector to any of the little mass elements and you weight it by the mass element and you add them up, you get 0. If you wanted to calculate the center of mass about any point, you choose a point s, you draw the vector from s to the object, you sum up those vectors. We see by our vector triangle rule that we can now calculate that center of mass vector by this equation. And now, let's just rewrite this because this is the total mass. And what we see is that rcm equals j goes from 1 to n, nj rsj divided by the total mass.
The little prince is sitting on his little planet, and he's watching the planets go by, and so suddenly he's seeing 3 of them, 1, 2, 3, and he wonders, what would the center of mass of these 3 planets be? So let's calculate it. We have one planet here that's 3 times the mass of this guy, and then this one has half of m1. And I've written this up there already. And the center of mass, when we want to determine its coordinate, it is a coordinate that depends on this coordinate system and this origin here, then we need to have the total mass of the system because it's a mass-weighted coordinate. And so the total mass is going to be 4.5 m1. And if we want to calculate this, this position function of the center of mass, rcm, that is the mass weight here. And then we need the sum of all our masses times our distances. We're going to sum here over j from 1 to n. And what that means is we need to now write out the sum for our 3 planets. And we need to give this a radius here, so the r1 would be going from here to here, r2 goes from here to there, and r3 from here to here. We need to write them out in the I hat direction and in the j hat direction. Let's add that here. And then sum it all up and calculate our r. So let's write this out. We have m1, and we're going to have 35 and 10. 35 I hat plus 10 j hat. M2. That's going to be 5 and 20. 5
Yes.
and 20. And then m3.
And
We
then
have
3,
40 and 30.
40, 30, yes.
And what we can do, oh, and of course that has to be divided by my
By
system.
the
mass.
system.
And what we can do is we can concentrate first on the x component and then on the y component. And maybe we'll just continue in here. So we're going to have, and we can plug in all the m's. We'll do it for the x component first. We're going to have m1, and then we have 35 I hat, plus here we're going to have half, m2, that is 3, m1, 5, plus, and for m3, we have 0.5, m1, 40. That's in the I hat direction. And we'll have to divide that over our system mass, and then we do the same for the y component. So m1, 10 plus 3 m1, 20 plus 0.5 m1, 30 j. And again, we have to divide this over our system mass. So this boils down to, let me do this again. Let me actually look at the answer first. What do we have here? 70 and 85. Okay. So this boils to m1 over the system mass, and we have 70 in the I hat plus 85 in the j hat direction. So the 70 comes from this term, the 80 comes from this, and I put it back together, and now we need to plug in this one here. And so we will get in the end that RCM equals m over 4.5m, so the m goes away, and we have a factor of 1 over 4.5 here. We'll divide this through, and we're going to have 15.5 in the I hat direction and 18.9 in the j hat direction.
Yes.
All right, so let's see where this fits on our graph here. So 15 in the I hat is somewhere here, and 19 is almost 20, so it's going to be here, so about there. So this is my RCM, and this here is my center of mass of the system of these three little planets. Of course, we use approximate masses here for the planets, but if we look at the real numbers, imagine that this would be Earth, and it has 1 Earth mass. And if this was Saturn, it would have something like 318 Earth masses. And if this is Pluto, it would have 0.0025 Earth masses. You will see that Saturn really holds all the weight. And if we were to do this calculation with these numbers here, then our RCM would, and keeping this coordinate system in the arrangement of the planets, then it would go right into, if here's the center, it would go right next to the center, right over here. Because Saturn just weighs so much more than Pluto and Earth together.
True. Next.
Let's try to find the center of mass of a uniform object like a uniform rod. And let's assume this rod is length L, and we want to find the center of mass. Now, before I begin this calculation, you can probably already guess that it's going to be exactly in the middle, and we'll verify that. But let's first define what we mean by our center of mass for discrete particles. Recall that this was a sum over all the particles in the system, so we'll take a label j goes from 1 to n, and it was the mass of that jth particle times the position vector of that jth particle with respect to some origin, and we're dividing that by j goes from 1 to n of the total mass in the system. Now, how do we translate this equation for a continuous system? And let me just again show that we had chosen an origin. Here was our jth particle of mass mj and rj. So what we want to do is draw the analogy, and here's how it works. That for each discrete particle, we're going to look at that as some mass element, delta mj. Our vector rj will go to a vector for this mass element. I'll just write it delta m. And our sum from j goes from 1 to n is actually going to go to an integral over the body. So let's see how that looks. So first we'll do it with the total mass. M, here we're summing over j from 1 to n of mj. That goes to the integral over the body. Now, the delta m, when we take limits, because that's where an integral goes, we'll write that as dm. So that becomes a limit over the body. And likewise, our sum, j, goes from 1 to n of mj rj, goes to an integral over the body of dm vector r going to that element. So we can say in the limit that this becomes r going to that element. Now, that means that our continuous expression for the continuous object is an integral over the body of dm r to that element dm divided by an integral over the body of dm.
Okay.
So now we want to find the center of mass of a uniform rod, and we have the result for a continuous body, which is an integral over the body of dm r to that mass element dm divided by an integral of dm. Now our goal is to figure out how to apply this result specifically to real physical objects. And the key, as always, is choosing a coordinate system. So now I'll draw the object again, and the first thing I'll do is choose an origin. I can pick my origin anywhere I want. I can pick it in the middle, I can put it in the middle, I can put it this end, I can put it that end, I can put it down here, but I'll choose it over here. Because the object is linear, this is a very Cartesian system, I'm only doing a one-dimensional object, so I choose my coordinate system plus x. That's step 1. Now, my origin. Now here comes the crucial thing. In this argument, dm is the infinitesimal mass element, and I want to pick that at an arbitrary place in the object. I don't want to pick it at the origin, I don't want to pick it at the end. Note down here, this is x equals L. So I'll arbitrarily pick an infinitesimal element, I'll shade it in dm. That represents, this is what I'm going to make my summation over when I do my integral. I'm going to add up all these dm's. And the point is that the dm's are different distances from the origin. So the vector, and here's the next step, is I draw a picture of my vector rdm. So now I have these terms at least explained in my diagram. The next step is to introduce an integration variable for both of these quantities. So step 1 was the coordinate system. Step 2 was the identification of dm. And step 3, and I think this is absolutely the crucial one, is to introduce the integration variable. Now, you'll see that will come in 2 different places. So this is the quantity, the distance from dm to the origin that's changing. You can see for each of these little elements, that changes. So what I'll write dm as a vector is x prime, which will be my integration variable in the I hat direction. So the integration variable is x prime. That's the first place that I introduce the integration variable. And x prime, you can see, will vary. And it varies from x prime equals 0 to x prime equals L. And that will show up in terms of the limits of my integral. Now, the second place that the integration variable comes in is dm. I want to express dm in terms of x prime, which is a measure of where this object is. And that's how, if we choose this length here to be dx prime, notice in terms of the integration variable, then I have a relationship between dm and dx prime. dm is mass in this little element, dx prime is the length of the element, and if the whole object is a uniform rod with a mass capital M and a length L, then it's just given by m over L dx prime.
Yes.
And this quantity, m over L, is an example of a linear mass density, which we have a skill challenge about. So I have 2 places where my integration variable has been introduced. And now I can write up every piece in this integral. So let's now indicate that we're integrating from x prime equals 0 to x prime equals L. dm is m over L dx prime, and our vector is x prime I hat. Then downstairs, it's just m over L dx prime, from x prime equals 0 to x prime equals L. And that's how I set up the integral for the center of mass. Both of these integrals are now not difficult to do. Notice it's x prime dx prime, so this integral is x squared over 2, and I get 1/2 m over L, L squared, and downstairs, the x prime from 0 to L is just L, so the downstairs integral is just m over L, and when you have m over L's cancel, we just are left with this is just m, not m over L, dimension incorrect. So we get, for the position of the center of mass, the m's cancel, one of the l's cancel, and we have an I hat in this expression, so our answer is r equals L over 2 I hat, which is exactly what we expected. We expected the center of mass to be halfway down the rod.
Okay, perfection.
I'd now like to talk about the velocity of the center of mass for a system of particles. So let's take a system, which I'll just outline by this, and in that system we have a bunch of particles, particle 1, particle 2, let's refer to this as the jth particle, and some point xcm. And if I want to talk about the position of the center of mass, I can choose a point S. And if I want to define that vector RCM, then what I have to do is draw a vector to each object, RSJ. And we saw that this velocity, the position of the center of mass, with respect to this origin S, is the sum mj RSJ. And that's divided by the total mass, m total. And j goes from 1 to n, where n is the number of particles in the system. Now, if I want to find the velocity of the center of mass, then I can just differentiate this. And I'm dropping the point S for the moment, but let's just differentiate 1 to n, you'll see why. And when I differentiate the position vector of the object, that's the velocity of the object, divided by j goes from 1 to n, the total mass. Now, why did I drop the position? Because if you have any two fixed points, so I chose another fixed point, say over here, P, then this distance, R, we'll call vector from S to P, RSP, this is a constant. And if I draw the position vector with respect to P, now the point here is that this is constant distance because this is a fixed, these are fixed points. Then if you were to draw your vector triangle, which is the position of the object with respect to S, that's this vector, is equal to that fixed position vector from S to P, plus the vector from P to J, and I differentiate this, drs j dt, well, this derivative of a constant vector, this is 0, plus drp j dt. And so we see that the velocity j is independent of the choice of point S. You choose any other fixed point, and you get that these velocities, drs j dt equals drp j dt for all fixed points P. And that's why in this expression, when we differentiate the velocity, even though we had an index S, we drop that. And so our conclusion is that we can treat that we have the velocity of the center of mass of this system is equal to the sum mj bj, j goes from 1 to n, divided by the total mass. Now, what's interesting here is, why is this an important quantity? Let's just add that if we want to talk about the acceleration of the center of mass, I do exactly the same type of calculation. I just differentiate, and I get the mass of the jth particle times the acceleration of the jth particle divided by the total mass. And our next step is to understand why this is an important quantity for a system of particles. We'd like to consider a system of particles. Say we have object 1, we'll call this the jth object, object n, and somewhere in the system of particles is the center of mass. Now, we know that the external force is causing the momentum of the system to change, and what we'd now like to show is that we can reduce this system to an effective single particle. The way we'll do that is recall that the momentum of the system is given by the sum of the individual momentums. We'll call that the jth particle, where we're summing j from 1 to n, and that's the sum of the momentums of the various particles. Now, when you differentiate the momentum of the system with respect to time, we're just differentiating the velocity, and so that becomes the acceleration of the jth particle. Now, we saw when we defined the center of mass that the acceleration of the center of mass times the total mass of the system was equal to this sum of mj aj. J goes from 1 to n. So we see that another way to think about how the momentum of the system of particles is changing is simply the total mass times the acceleration of the center of mass. And our combination of Newton's second and third law now becomes that only the external forces cause the momentum of the system to change, so that's equal to the total mass times the acceleration of the center of mass. Now, what does this equation really mean? So let's draw our pictures again. Here's our system. We have particles 1, etc. That's the jth particle, n particles, and in here is the center of mass. Now, I'm going to outline my system like this, and what this equation is telling us is that we can just focus by putting all of the mass, m total, at the center of mass, and that center of mass is going to move according to some trajectory, and all we have to think about is this is now this is a point particle of total mass m total. So what we've done is we've done a very important reduction. We've taken a complicated system of particles and reduced it to a single point particle of total mass m located at Cm. And the dynamics of that total particle is, if there is an external force acting on this system, we place this external force at the center of mass, and now we can calculate the acceleration of the center of mass is just that external force divided by the total mass. And that's how we can reduce this complicated system of particles to a translational motion of the center of mass. Now, we still cannot describe the individual interactions in the system, but we're not trying to do that anymore. We're not trying to trace how each particle moves. We're just looking at our system as a point particle and talking about how that point-like object is translating in space. And this is a powerful tool that we use again and again and again.
Yes.
This week, we will use the concept of momentum to analyze some more advanced situations, namely systems in which there is a continuous flow of mass rather than just the motion of discrete objects. The classic example of this is the thrust due to exhaust from a rocket engine. Once again, we will appeal to a differential analysis technique, breaking the flow down into a large number of small elements, analyzing one of the elements in detail, and then generalizing. This is an important example of a situation where the point mass form of Newton's second law of motion, F equals ma, is inadequate, and one must instead use the more general form of the law, F equals vp dt, or the force is equal to the time derivative of the momentum.
And now we
We will
differentiate
practice going
mass
between reference
as
to
well.
look at relative velocities in one dimension. Let's say that an observer is standing on the sidewalk, and that observer sees a car drive past to the right at a speed of v car. The observer also sees a bike that's riding to the left at a slower speed, v bike. Now, I'm interested in what the car looks like from the perspective of the bike. The bike sees itself as stationary and sees the world around it moving to the right. To the bike, the observer on the sidewalk appears to be moving to the right with a speed of v bike. The car was moving to the right relative to the reference frame of the observer standing on the sidewalk. So to the bike, the car looks like it's going even faster to the right, with a total speed of v car plus v bike. Let's say, later on, the biker throws an apple in the direction of her movement, and sees this apple travel to the left with a speed of v apple. Now I want to know what an observer sees in the stationary frame on the sidewalk. The apple appears to be traveling a speed v apple faster than the biker, all to the left. So the observer on the sidewalk will see the apple move to the left with a total speed of v apple plus v bike. Now let's say the person throws the apple forward at a speed v apple. What does the car see? To the car, the apple is going to the left at a speed of v car minus v apple.
Yeah.
How about the bike? To the bike, the apple is going at a speed of v apple plus v bike to the right.
We would like to now apply the momentum principle to examples of recoil. So recall that the momentum principle is that the external force causes the momentum of the system to change. Now this is a vector equation, so for example, if the external force in the x direction is 0, then the momentum of the system in the x direction, let's say the final momentum, will be equal to the initial momentum. I would like to now apply the momentum principle to an example of recoil. In our recoil example, we have a person jumping off a cart. So let's just look at how this example can work if we draw momentum diagrams. So suppose we choose a ground frame. And in that ground frame, we have a cart and a person. The person is standing on the cart, and this is t initial. And here, they are at rest. Now, the person we're going to assume to jump horizontally off the cart, and the cart will recoil in the opposite direction. So after the jump, we can describe this picture. The person is moving with velocity v. The cart is moving with vc, and the person has jumped with the velocity vp. Now, suppose I choose a different reference frame. That instead of choosing a ground frame as a reference frame, moving with the velocity vc, you can imagine that maybe I have a car here, and that car, you're inside that car, moving with velocity vc, and you're looking at this picture. Then what would our momentum diagrams look like? Well, if I'm moving in a car this way, and in the ground frame, the initial picture is the person in the car is at rest, then in my moving frame, it actually looks as if the cart and the person are moving in the opposite direction. So let's write that this way. Here's the initial picture, t initial. And in this frame, the person and the cart are moving with vc minus vc. I put an arrow here to indicate that it's opposite the direction of vc there. But their velocity is minus the velocity of the reference frame. After the jump, so here's the person now, the cart is at rest. Why? Because we're in the reference frame moving with vc. So if you're in a car and you're moving at the same speed that the cart has with the ground frame, then in your frame, this cart looks like it's at rest. What about the person jumping off? Well, let's write it this way. So this is the velocity. I'm going to use a symbol u. Now u, this is what we mean by that. This is the velocity of the person in the moving frame that's moving with velocity vc. That's the velocity of the person as seen by a cart. Sometimes we call this the velocity of the person relative to the cart. What does that word relative to the cart mean? Well, you can see in this picture, in this moving frame, the cart is at rest, and the person jumps with a speed u, velocity u, relative to the cart. So these are our momentum diagrams for a ground frame in which the person and the cart start at rest. The person jumps off. I can put an arrow here, but it's really information is in that vector. The cart is moving. In a frame moving with the velocity of the cart, then what does my picture look like? Well, the cart and the person initially are moving opposite direction. Again, you're moving this way. The cart looks like it's moving that way if you're inside the car. And the final state, cart is at rest, and the person is jumping with the velocity u relative to the cart. Now, our question now is how do we relate these two velocities, u and vp? What are u and vp? Vp is the velocity of the person in the ground frame, and u is the velocity of the person in the moving frame. Well, we've already seen our equation for how to get velocities in different frames. We have that vp equals the relative velocity of the two frames plus the velocity in the moving frame. So what we have is this is the velocity of the person, just clean that up, of the person in the ground frame. V is the relative velocity of the two frames. So here we have that v is the velocity of the cart,
But it
because
has
you're in a
the
frame moving
mass.
with vc with respect to the ground, and u
They shouldn't have the
is
same
the velocity
mass.
of the person in the moving frame. So this is how we can show the same type of interaction in two different reference frames. Next, we'll figure out what these velocities are.
Yeah, we need masses.
So we've now drawn pictures of the interaction of a person jumping off a cart in both the ground frame and a reference frame moving with velocity vc, which is the final speed of the cart. These were pictures in the reference frame moving with vc, and these are the pictures, momentum diagrams of the person in the cart in the ground frame. Now we would like to apply the momentum principle to solve for vp and vc. We are given that the velocity of the person in the moving frame, u, we'll treat this as a given quantity. And we'll express the velocity vc, and so we want to find vc and vp in terms of u mp, and mc. Now, we'll use the ground
Okay.
frame first. And our assumption here is that the person jumped horizontally and that there are no external forces in the horizontal direction. So all the vectors we've drawn are horizontal, and there's no external forces in the horizontal direction. Then we know that the initial momentum of the system is equal to the final momentum of the system. In our initial picture, nothing is moving. And in our final picture, we have m cart v cart plus m person v person is 0. Now, recall that we also showed that the velocity of the person in the ground frame is related to the velocity of the person in the moving frame by adding the relative velocity of the two frames. The relative velocity of the two frames is the velocity of the car, vc. So what we have is vc plus u. So this is how Vp is related to u. And now I can use this start equation to write it as 0 equals mc vc plus mp times vc plus u. And by adding terms, I get that mc plus mp vc equals minus mpu, or the velocity of the cart is equal to minus mpu divided by mc plus mp. Now that I have the velocity of the cart, I can just substitute that in here to find the velocity of the person, which remember was the velocity of the cart plus u. So now I've
Okay.
solved this problem in the ground frame. Next, I'll do the same analysis in the moving frame. So we've been trying to find the velocity of the cart and the velocity of the person in terms of the relative velocity of the person jumping in the reference frame of the moving cart, the mass of the person, and the mass of the cart. We've already solved this in the ground frame. Now I would like to solve this in which my reference frame is the moving frame. So our pictures in the moving frame were actually much easier. Because the moving frame is traveling with the final speed of the cart, at the final interaction, after the interaction is done, in this moving frame, the cart is at rest. They're moving together. You're sitting in the cart, you're moving at the same speed. The person jumped off with speed u relative to the cart. The tricky part was to realize that in the ground frame, when the cart is at rest here in the ground frame, an observer moving with speed vc would see the person in the cart moving backwards in the moving frame with the speed minus vc. So now we can apply the momentum principle to these two states. In the moving frame, we have that momentum of the system initially equals momentum of the system finally. Now the initial momentum is just minus mp plus m cart v cart. Notice the minus v cart. And the final momentum is equal to just m person u. And so we see that v cart equals minus m person u over m person plus mc, which is exactly the same result that we got in the ground frame, but it was actually much easier to solve in the moving frame. We'd like to analyze a physics problem called the rocket problem, in which we have a continuous mass transfer. Let's see what we mean by that. Let's consider a rocket launching. So here's a classic example of a rocket that's launching off in a gravitational field. As a rocket starts at rest, it starts to burn fuel and ejects the fuel backwards. And as the ejected fuel backwards is producing a thrust on the rocket, and you can see as the rocket starts to rise, it's starting to accelerate upwards as fuel is ejected backwards. Now this process goes on for some time interval, and a lot of fuel is ejected backwards during that time interval. In this particular case, we could analyze the situation from the ground frame of the rocket, from the ground frame of the Earth, and the fuel is ejected backwards relative to the rocket moves up forward. So how do we analyze this situation? If we just looked at the rocket when the rocket initially launched, the mass of the rocket is the dry mass of the rocket plus all the fuel in there. It's at rest. In a state much later on, the mass of the rocket has decreased and the speed has increased, but we can't just compare this initial to this final state because throughout this process there was a continuous mass transfer. Fuel was ejected backwards. So how do we analyze these types of continuous mass transfer problems? And the key is, again, identifying states. So for a continuous mass transfer problem, we always have to choose a reference frame. So here in our example, we were choosing the ground frame of the Earth. And then we want to identify two states. We don't want to identify the initial and the final states. We want to pick two arbitrary states that are separated by a small time interval. So we can take a state at time t, and then our second state occurs at a small time afterwards, time t plus delta t. And what we want to do is now represent the state changes by momentum diagrams. And that will lead us to a differential equation, which is called the rocket equation, and that's how we'll analyze all continuous mass transfer problems. In applying the momentum principle, our first thing is just to choose a reference frame. So in our example, we're going to choose the ground frame of the Earth as a reference frame. Now, the next step is the key to these processes. Instead of choosing some initial state where the rocket is at rest and some final state much later on, we want to choose two states that are separated by a small time interval delta t. So our first state at
Obvious.
time t, and our second state we choose at time t plus delta t. Now, the next step is that we have to identify what is our system. And so in this case, our system is going to be the mass of the rocket at time t. That mass is the dry mass of the rocket plus all the fuel that's still in the rocket at time t. And this mass will stay the same between times t and t plus delta t, even though some of the mass has been ejected downward. So our next step is to look at that mass conservation of the system. We would now like to apply the momentum principle to analyze the motion of the rocket. So what is our momentum principle? We know that the external force at time t is equal to the rate of change of the momentum of the system over t. Now, recall, we're going to actually use the formal definition of a derivative to write this as a limit as delta t goes to 0 of the momentum of the system at time t plus delta t minus the momentum of the system at time t divided by delta t. So in order to analyze the rocket, what we need to do is separately analyze the momentum at our two states. So we have a state at time t, and we have a state at time t plus delta t. And our goal will be to analyze the system momentum at time t, and separately the system momentum at time t plus delta t, and then we can apply the momentum principle. So let's begin by analyzing the system at time t. So recall that at that time, we had our rocket, and this is our time t. And the rocket had a velocity v of r of t. And what we identified, the mass mr of t, recall this was the mass, the dry mass of the rocket, and the mass of the fuel. And so now it's very simple to write down the momentum of our system at time t. That's equal to just the mass m(r) of t times the velocity of the rocket at time t. And so we can use that in our expression for the momentum of the system. Now our next step is to consider the system at time t, t plus delta t. Now recall, we still have the rocket, but the mass of the rocket has changed. That's inside the rocket. So this is dry mass of the rocket plus mass of the fuel, but recall, some of the fuel has been ejected outwards. So how do we depict that in our momentum diagram? Well, let's just symbolize that by a certain amount, and we're going to call this delta m fuel. Now, what we need to do, again, is to have our velocities. So here, the velocity of the rocket is now the velocity at time t plus delta t. And what about the velocity of this fuel that's being ejected? Well, in our problem, the fuel is ejected at a speed, at a velocity u relative to the rocket. So what we have is u is the velocity of the fuel relative to the rocket. But we've been choosing the ground frame as our reference frame, and the rocket is moving at a velocity at time t plus delta t with respect to that ground frame. And so recall that the velocity of the fuel in the ground frame is equal to the velocity relative to the rocket plus the speed of the rocket with respect to the ground frame. And that's what we're going to draw on our diagram as the fuel. And so now we can finish this analysis, and we'll apply that next, is to write the momentum of the system at time t plus delta t. Now this is going to have two terms. It has the mass of the rocket at time t plus delta t times the velocity of the rocket. And we also have to add mass of the fuel times the velocity of the fuel with respect to the ground. And now we have the momentum at time t plus delta t. So we have both of our pieces here, and we still have a little bit of analysis because we'll use our mass conservation equation to end our relative velocity condition to simplify this expression. So we'll do that next. So now we wrote down the momentum of the system of our rocket at time t and the momentum of the system of the rocket at time t plus delta t. Let's make some simplifications in our notation just to make our calculations a little more easy to read. So the first thing we want to do is we want to say that the mass of the rocket at time t, this is the mass of the rocket plus the mass of the fuel in the rocket at time t, we're just going to denote that by mr. And keep in mind that when you write the mass at time t plus delta t, we'll write that as the mass at time t plus delta mr. This is precisely how you define a differential. Even if this quantity is negative, you always write the difference, m of r t plus delta t minus m of r t equal to delta mr. That's how we write a differential delta mass of the rocket. So the mass of the rocket at time t looks simpler, m of r plus delta mr. So those are two ways of simplifying our expressions for the terms that are appearing here and there. Now the next thing was, recall from our mass conservation that we had the condition that delta m fuel was equal to minus delta m rocket. So now we'll take those two simplifications, and now we'll write down our system momentum at time t. That's very simple, mr v of r at time t. And we'll now write the momentum at time t plus delta t. Well, we have the first piece, which is mr plus delta mr times the velocity of the rocket at time t plus delta t. Now be careful here because we're going to use our conservation of mass condition to replace delta m fuel with minus delta m rocket, and we'll use our expression for the velocity of fuel in the ground frame of the rocket, so we have minus delta m rocket times the velocity u plus v of r of t plus delta t. And this simplification, we'll write equations 1 and equation 2, will enable us to apply the momentum principle in a very transparent way, and that's what we'll do next. Now that we have all the pieces in place, we'd like to apply the momentum principle to the rocket problem. Recall that the momentum principle is that the external force on the rocket causes the momentum of the system to change. And the fundamental definition of a derivative is to look at the change in momentum between sometimes t plus delta t, our two states that we've identified, divided by delta t. Now recall that we had the momentum of the system at time t was the mass of the rocket times v bar of the rocket at t. I'll just quickly show mass of the rocket, vr t. And we had the system at time t plus delta t, where we had delta m fuel equals minus delta m rocket. Here we had mr plus delta m, and we had the velocity in the ground frame, which we saw was equal to, so let's write out the momentum of the system at time t plus delta t. That was a little bit longer. P system at t plus delta t had two pieces. We had mr plus delta mr times v of r of t plus delta t, and we were subtracting. Now, because we made this change, that's minus delta mr u plus v of r of t plus delta t, and this, recall, was the velocity of the fuel. Now we're in position to apply our momentum principle, because we have expressions for the momentum of the system at time t, and at time t, and at time t plus delta t. So now this will be a big expression. So we'll write external force is the limit as delta t goes to 0. Now here, our first term is m of r plus delta mr times the velocity of the rocket at time t plus delta t. And now we have the fuel term, minus delta mr times u plus v of r of t plus delta t. And we have to subtract from that, and I'll indicate that with a slightly different color, mr v of r of t. And the whole thing we're dividing by delta t. Now, let's look at this expression first, because there's some very nice simplifications. The first thing we can see, let's look at this term delta mr times v of r. Notice we have minus delta mr v of r here. So those two terms cancel. And we're just left with three other terms, and let's write them out. So now we have the limit as delta t goes to 0. And I'm going to combine terms in the following way. mr times v of r of t plus delta t. And over here, I have mr minus v of r, so I have a minus v of r of t divided by delta t. And now I have one more term here, and I'm going to write this as minus the limit as delta t goes to 0 of delta mr over delta t. Remember, this term canceled. We only have the speed of the fuel relative to the rocket. And in both cases, this is our first term, and here's our second term. Let's look at these limits. Notice in here, we're just taking v of r t plus delta t minus v of r t divided by delta t, and that's precisely the definition of the derivative of the velocity of the rocket. So this first term, our expression, becomes the external force is equal to the mass of our system times v of r, the velocity, derivative of the velocity of the rocket. And the second term, this is the rate that the fuel is changing in the rocket. This is rather the rate that the mass of the rocket is changing. So that's the derivative, the mr dt times the relative velocity of the fuel with respect to the rocket. So this equation here, I'll box it off, is called the rocket equation, which we derived from the momentum principle using our momentum diagrams. And you can see that this is what people refer to as rocket science. For a rocket in an external force, we have the rocket equation, which we wrote as mass of the rocket. Now remember, this is a function of time times the derivative of the rocket, dr dt. And we also have this second term that came from the ejecting fuel. Now, from our mass conservation equation, we can rewrite this equation as a differential relationship that the change of mass of the fuel in time is equal to minus the change of the rocket. It doesn't matter which side we put the minus sign on. So now I want to interpret this equation in a different way, and it will come back to what we mean by our system. Let's first off bring this other term over to this side. So we have plus dmr dt u, and that's equal to mr dvr dt. Now, separately, let's make this substitution again and go back to our fuel term. So that's minus dmf dt u equals mr dvr dt. Now, notice that over here we have mass times the acceleration of the rocket. So if we just rethought our system as simply the rocket, mr, then we have two forces acting on the rocket. The external force might be the gravitational field, but we have a new term here, which we're going to refer to as thrust. And so our thrust can be thought of as an external force simply on the rocket as a system. And that's equal to minus df dt u. Now, again, if I chose j hat up, let's just look at this in components. Then our thrust as a vector, we'll write it as a y component, is equal to minus dm fuel dt. Now, what is that relative speed? Well, the fuel is being ejected backwards, so that's minus mu j hat. The external force, by the way, would be minus mg j hat if it's near the surface of the Earth. So we have another minus u j hat, and we see that we have a positive thrust force in the vertical direction that is giving us an additional force other than the gravitational field. And in Cartesian, in our unit vectors here, we have minus mg plus dm fuel dt times u is equal to mr dvy dt of the rocket. And so this is the rocket equation in components.
Perfection.
We would now like to look at some applications of the rocket equation, in which we have an external force plus dmr dt, where mr is the mass of the rocket at time t, times the relative velocity of the exhaust velocity, was equal to m of r dv rocket dt. And now we want to consider some special cases. So our first example will be a case when there's no external force. Now, this might be characteristic of a rocket that's far away from any type of gravitational interaction and is either speeding up or slowing down. This is a special case that will enable us to understand our problem. Now, let's consider, we'll draw a picture at time t, just to remind ourselves. So we have mass of the rocket, it's moving with velocity v of r of t, and we're going to call this our plus I hat direction. And then at time t plus delta t, we have our fuel, delta m fuel, which was equal to minus delta m rocket, moving with a relative velocity u plus v of r of t plus delta t, and our rocket itself is moving with v of r of t plus delta t. So in our coordinate system, we have to remember that the exhaust speed is relative to the rocket, and we define that to be u. Since its rocket is moving forward, and we've chosen plus I hat in that direction, it's minus u I hat, and we can write our vectors vr as v of r I hat. So our rocket equation in this special case becomes dmr dt minus u I hat equals mr dvr dt I hat. Now, in this equation, remember that it's important to recall that m of r is a function of time. And unless we have an explicit model for how the mass is ejected, in principle, we can't solve for the time behavior, but we can look at this differential equation just by eliminating the time completely by multiplying through by dt, in which case we have minus dmr u equals m of r dvr. Now, this is separable, and I can integrate it, so I'll bring the terms minus dmr over mr on this side times u, and that's equal to dvr on that side. Now, when we integrate, we're going to be integrating mass of the rocket, say at some initial time, t initial, to mass of the rocket at some final time. And over here, we're going to be integrating the velocity from some initial time to some final time. And both these integrals are straightforward. On the left-hand side, we have a natural log, so we have minus u, natural log of mr t final over mr t initial. And this side, we just have the velocity difference, v of r at t final minus vr at t initial. Now, again, we always check our minus signs, but recall the mass of the rocket is decreasing, so the log of a fraction is negative, so we have a positive quantity on this side, and that's indicating that the velocity has increased on that side. And so we conclude that the velocity of the rocket at its final time is equal to the velocity of the rocket at its initial time. Now here, I'll keep this minus sign in here, minus natural log of mr t final over mr t initial. Now, in our answer, we need to know what the mass of the rocket is at the final time. So in general, this equation is still not going to give us an explicit expression for v at t final, unless we have one special case in which our final time is when all the fuel has been burned. and our initial time is the rocket with all the fuel there, and then this ratio is a known ratio, and you can look at a variety of different examples for that. So there's an example of solving the motion of a rocket with no external forces. We've seen our rocket equation, and we've studied the example when there's no external forces. Now let's consider an example when the external force is not 0. Well, one of our examples is just a rocket taking off in a gravitational field, and so when we want to focus on the external forces, let's draw our rocket at time t, and now consider what are the force diagrams on this rocket. Well, we have a gravitational force, mg, so we're going to choose j hat up. So now what does our rocket equation look like? We wrote the exhaust velocity as minus mu j hat, and so if we write this now as a vector equation in the j hat component, we get minus mg. We have the rate that the rocket mass is changing, and this is in our, we have this is, remember, dm dr dt is going to be negative, so there's a minus, and over here we have another, this is u, because u is minus u, and finally we have m rocket dvr dt. Now, once again, we're going to try to integrate, this is actually equal, and we're going to try to integrate this equation to find a solution for the velocity as a function of time when all the fuel is burned. So what we do is we'll multiply through by dt, and we have minus dmr times u equals mr dvr. And this is mass of the rocket. And now let's divide through by mass of the rocket. So we have minus g dt minus dmr over mr u equals dvr. And once again, we can integrate this equation from some initial time to some final time. I'll just denote that by I initial and I final. And what we see here is we have minus g times t final minus t initial because we're integrating with respect to time. Here we're integrating mass, so that's minus mu, natural log. And I'm going to write this as mr final over mr initial. And over here we have dr final minus dr initial. And let's just remove that time t. And so now here is our rocket equation. Now what we notice here is, let's look at some rocket taking off. So suppose that at t initial equals 0, we have the special condition that dr initial equals 0, and mr initial equals the mass of the rocket, dry mass, that's all, that's not counting the fuel, plus the total mass of the fuel. And the final, at t final, when the engine turns off, we're going to try to find this velocity at t final, and our condition for the final mass is all the fuel's been burned, so this is just the dry mass of the rocket. And so what we get is we get minus g t final. Now I'm going to switch the sign here. So we have, if I invert the log, that will give a minus sign, and I have plus u log of mr of d plus mass of the fuel, that's the initial mass of the rocket, divided by just the dry mass, and that's equal to Vr at t final. So one of the interesting questions that you might ask is, how fast should you burn the fuel? And what will that have to do with the final speed? So we can see from this expression that if you burn the fuel for a very long period of time, so t final is big, then this piece will diminish the final velocity. So if you want the fastest speed after you've burned the fuel, you want to burn the fuel so that t final is as short as possible. You have the shortest burn time will give us the largest velocity when all the fuel has been burned.
Makes sense.
Let's look at this rocket sled here. It's going on in the snow, but it wants to stop. There are two little devices mounted on the sled, and they can eject gas. And so the forward one is used to eject gas to make the sled stop. We want to derive a relation for the differential between the speed of the sled and the differential of the mass of the rocket sled. But before we do that with the rocket equation, we need to actually consider what else we know about the system. Well, we know that the dry mass has a mass of m naught. The fuel mass is given also as m naught. And we know that at time of t equals 0, the speed of the sled is v naught. We also know that at a later time, t plus delta t, we have the sled here, whose mass is now m of t plus delta t. Then we have this little mass parcel that has been ejected, so the gas, and that has the mass of delta mf, so the mass of the fuel. We furthermore know that relative to the sled, this little gas parcel is moving with the speed u. The rocket equation says that my force, my external force, has two terms. We have the mass of the rocket times the acceleration of the sled, minus the differential here of the mass times the speed u, and these are actually all vectors. And so this describes this little gas parcel here, and this one describes the rocket. And we know that v equals v I hat, that's going in the direction of motion, and u equals u I hat. We also know that there are no external forces applied to the sled, so that's actually 0. We can then turn this equation, we can apply all of this, we will get 0 equals mr dvr dt minus dmr dtu. We can bring this one on the other side, and we end up with the relationship that we wanted to obtain, namely an equation that contains the differentials of the speed of the rocket, that sled, and the differential of the mass. We just derived this relation here, the relation between the differential of the speed of the rocket sled and the differential of the mass of the rocket, and we want to ultimately get the speed of the rocket. So we have to apply a technique called separation of variables, and then we want to integrate. What we're going to do is first we're going to multiply by dt, so that falls away, and we're left with mr dvr equals dmru, and we're going to shuffle the m onto the other side, and we're left with dvr equals u is a constant, so that goes up front, and then we have dmr over mr. That's an equation that we can integrate now, and we can do that. And the tricky bit is that we need to take care of the integration limits here. We have Vr, and actually these now are all primes. So we have Vr going from v naught, that is our initial condition here, to vr prime of equal vr of t. And for the mass, we have mr prime equals m naught. Actually, not quite m naught, it's 2 m naught, because the initial mass of this is the dry mass and the fuel mass, so that's 2 m naught. So this is the initial mass. And then we go to mr prime equals m of vr. All right, so let's do that. We're going to get vr minus v naught equals u 1 over m integrated gives us an ln. So ln, and then we can immediately do this here over 2m naught. And well, we ultimately want this, so this is an VRT, of course, and then we got V naught plus U ln mr over 2m naught. And that is our equation. So what does this equation tell us? mr, the mass of the rocket, is less later on than it was before, which means this term here is going to be less than 0, which means the velocity is our initial velocity minus something, which means we have a decrease in velocity, which means my sled will eventually come to a stop.
That's because, yeah.
So the last question you can ask us is, what was that V naught here, initially of the sled, making use of the fact that the sled comes to a stop at the time that the fuel is all used up. That means that our final velocity here is 0. We'll bring V naught to the other side, and then we get a minus U ln, and the rocket mass by then is just the dry mass, m naught over 2m naught, and that of course cancels out here, and we can say that is plus U ln of 2. So that was the velocity that the sled was going with.
Okay.
Let's consider another example of continuous mass transfer. Suppose we have a truck, and that truck has some type of plow, and it's plowing snow. And there's some type of external force acting on this truck, friction pushing the truck forward, so let's just assume we have some type of force, F, on the truck. And this is our snow, and what's happening in this problem is that the truck picks up the snow, and then, which is at rest initially, gets the snow up to the speed of the truck, and then the snow falls off the plow. So how do we model this problem? Well, let's look at our situation at time t, and what we're going to do is we're going to consider a certain mass of snow, delta ms, that's at rest. And our truck, with a fixed mass truck, is moving with a velocity dt at time t, the truck. So now what happens at time t plus delta t? Well, the truck has picked up the mass of the snow, and the truck has now changed its speed. So that's at time t plus delta t. And now we want to write down our momentum law. So we have our external force. Let's call this the plus I hat direction. We have our external force is equal to the limit as delta t goes to 0 of the momentum at time t. So we have t plus delta t. So what we have is the mass of the truck plus delta ms times v of t plus delta t, and we have to subtract from that's divided by delta t, and we have to subtract from this the momentum at time t. The snow is at rest, only the truck is moving, so we have minus t of the t divided by delta t. Now, as usual, we're going to say that the truck has changed its velocity in this interval, and what we want to do now is write out our equation. We have f equals the limit as delta t goes to 0 of, now when we write this out, notice that we're going to have a number of terms here. We have mt plus delta ms times v plus delta d, the truck. That's the first term, divided by delta t, and the second term is just minus mass of the truck, v of t over delta t. Well, first off, we see some cancellations between this term and that, and what we're left with is limit as delta t goes to 0 of, we have the snow term, delta ms over delta t times v truck. Now here we have a term which we're going to analyze in a moment. It has two infinitesimal quantities, and this term is of second order, which we're going to neglect. And finally, we have the term of mass of the truck times delta vt delta t. So neglecting the second order term in differentials, what we get when we take the limit is that we get the force is the rate that the snow is being picked up times v of the truck plus mass of the truck times v truck dt. Now, the only issue that we have to think about here is about the rate that the snow is being picked up. So that's our last consideration, but this will be our differential equation for adding mass continually to a system. So when we found our equation for describing the rate that the truck changes its speed, the snowplow, when it's pushing snow away, we wrote down our equation in terms of the external force on the truck, the rate that snow is being picked up by the truck, the velocity of the truck, the mass of the truck, the rate of change of velocity of the truck. If we multiply our equation through by dt, we have the following equation. And now what we want to consider is we want to focus on how much dms is picked up in our infinitesimal time dt. So one way to think about that is let's do a little drawing. So here's our truck. And let's say at time t, the plow is right here. So here's a picture at time t. And let's draw some snow here. Here in New England we have lots of snow. And at time t plus delta t, the truck has moved a certain distance. And so this quantity is the amount of snow that's picked up by the truck and displaced. Now, the truck has moved a distance v truck delta t. And so we can identify the delta ms, which in the limit will be dms, is equal to the density of snow times the cross-sectional area of the plow times the length v of truck delta t. And so now we have an expression for the rate that the mass is being picked up in this time interval, and we can write that in the following way, that we see that our differential equation, f dt equals dms, which is rho a dt times dt plus mt dvt. Now, we can bring this term over to the other side, and so we have F minus rho A bt squared times dt equals mass of the truck times dv dt. And mass of the truck in this case is fixed. Why? Because when the snow gets into the truck, at the end of this delta t time interval, it gets displaced to the side. So this is an equation that we can separate and integrate. So we have dt is equal to mt divided by F minus rho A bt squared dvt, and we integrate from some initial time to some final time. And here we're integrating from v of truck from some t initial time to some final time. And that's our integral version for our finding the velocity. This integral is an integral that's not hard to do, that you should try as an exercise in elementary calculus.
Okay.
We previously discussed the concept of conservation of momentum. We will soon see that there is another very powerful conservation principle in physics called the conservation of energy. It states that there is a certain quantity called energy that remains unchanged in the system, except for any that flows in or out of the system. It's hard to say exactly what energy is. It's an abstract quantity that we count up in a certain way. When calculating the energy of a system, we must keep careful track of any energy that enters or leaves the system. There are also a number of different forms of energy: kinetic energy, gravitational energy, elastic energy, electrical energy, heat energy, and others. Each of these has its own formula for calculation. If you sum all these energies up for a system, the total will remain unchanged except for what goes in and comes out. It turns out that using energy rather than force, one can construct a complete system of mechanics that is fully equivalent to the Newtonian system. This was done by Lagrange and Hamilton, and you may encounter their system in the future if you take more advanced courses in physics. However, even in the Newtonian system, energy remains a useful concept. This week, we will discuss kinetic energy, the energy associated with the motion of a mass, and also the concept of work, which allows us to calculate how the action of a force changes the kinetic energy. We will see that the work done by a force is calculated by evaluating an integral that, in general, depends upon the specific trajectory or path taken by the object or system. However, we will also see that there is a special class of forces called conservative forces, for which the work integral is path independent and instead depends only on the starting and ending points. Finally, we will discuss examples of both conservative and non-conservative forces.
Okay.
Let's talk about kinetic energy. We're calling kinetic energy K, and it's given by 1/2 mv squared. And this is a scalar quantity, so it's going to be either 0 or positive. It's never going to be negative. The SI unit for kinetic energy is joule, so we have 1 joule here for kinetic energy, and the units come from this, so we have kilogram and then meter per second squared. Now, let's assume we have an object that is first at rest, and then it speeds up with a certain velocity, which means the object is going to experience a change in kinetic energy. And so we'll express this as 1/2 mv final squared minus 1/2 mv initial squared. And if we have a motion, so velocity in let's say a 2D or 3D space, then we can then we have to consider all these components here, and we can also pull out the 1/2 m, and then we have v x final squared plus v y final squared plus v z final squared, and then minus all the initial values, x initial, y initial, and z initial. Now, when we consider just a point particle, then we can also ask, what is the momentum? How can we pair up momentum and kinetic energy? So I'm writing it again here. K equals 1/2 mv squared. If we multiply this by m upstairs and downstairs, we're going to have m squared over v squared, and that's actually p squared. Remember, p equals mv. And so we're going to get that this actually can be expressed as p squared over 2m. And so that is the kinetic energy expressed in terms of the momentum of a particle.
Suppose we have an object, and we're applying a constant force in the horizontal direction. We would now like to introduce the concept of work. Suppose our force starts at a point xi and goes to a position x final, and we'll call this the I hat direction. Then our force, as a vector, will write fx I hat. And now what we'd like to calculate is the product of force with the displacement of the object. So our displacement vector, delta x, is equal to delta x I hat, where delta x is equal to x final minus x initial. And for our constant force, for the case where fx is a constant, we would like to define the work done by this force in displacing the object from our initial position, and we'll mark it like that, to the final position here, is given by the product, so we'll call work is the product of the force, fx, times the displacement, and so that's equal to fx times x final minus x initial. And this is our definition for work for the special case where the force is constant. Now, if we look at this, our force may, in our diagram, we drew it in the positive x direction, but if our force fx were
1/3
less than 0,
volt.
and our
Yes.
displacement was in the positive direction,
Costa
positive, then we
Sordano.
can see that the work is negative. So if the
What
force
you
was
doing,
opposing
man?
the displacement. And that's what would happen if fx was pointing in the negative direction, the work would be negative. If fx is positive and the displacement is positive, then the work
Every
is constant.
time
So we see work is
we
a
get to
scalar that has a sign quantity, positive or negative. Now, whenever we
every
introduce a new
time
quantity, we always
it
have to be a little careful about the units. Since work is
reduces
the product of force and distance,
a new
then our
video,
SI units
it's
for work are
it's
the
more
units of
bold.
force, which are newtons, times the units of distance, meters, and we call this a joule. So 1 joule is equal to 1 newton meter. Now, graphically, we can make an interpretation of this. Let's draw a graph of force, the x component of the force, and here, if we had some origin, we'll have x, and our object is starting at xi, and it's going to x final, and throughout this process, we're assuming that the force is constant. So what we see in
Yes.
this diagram here, I'll just shade in this area, that our work, which was the product of force times the displacement, corresponds to the area here.
Onto the curve.
So we have a geometric interpretation of work as the area under the force versus position graph. And this is our example of work for a constant force.
Yeah, how is he so symmetrically
We already
bald?
defined work in one dimension as the product of force times displacement or constant force, but now let's look at a case where
I
we
haven't
apply a
even
force F
noticed that.
that is a function of x. So our component f of x is a function of x in the I hat direction, and one of the simplest examples of a force like this is what we call the spring force. Now, when we apply this force to our object, and let's look at an object I hat direction will have an origin, and this is our plus x coordinate system. Now, when we apply a force, what we want to look at is, because the force is a function of position, then we want to look at the
He's so
displacement over a small
wavelength.
So let's call this the point xj, and out here, let's refer to this as xj plus 1. And what we've
Yes.
done is we're going to ask how much work is done when the force is displaced from here to there. And that's what we'll call delta x. So now our displacement is a small displacement, x of j plus 1 minus x of j. And our work for this small displacement, and that's why we'll indicate it with a delta, is equal to the force, which is a function of x, times this displacement. And so now we get f of x times x of j plus 1 minus x of j. And what we have to indicate here is because the force is varying, we're looking at just this displacement here. Let's refer to this force as in the jth part. Now, the total work is just the sum of all these scalar quantities. Remember, although force is a vector and displacement is a vector, the product of these two quantities is a scalar. And so if we want the total work, we have to sum, from j goes from 1 to n, of this quantity f of j dot, and I'll put a little j there to indicate that, delta xj. Now, what does this sum mean? Well, imagine that we're making a series of displacements all the way out to a final position, x final, and we have divided this interval into n pieces. And so this now represents a little bit of work done for all of these displacements. And that is what we define to be the work for a non-constant force. Now,
It's
the
nice
issue here
seeing you.
is about how fine we cut this interval, and we made n individual pieces. But if we want to ask ourselves what is the limit as n goes to infinity, then that's what we now need to consider. So what we're doing is we're making smaller and smaller and smaller little displacements, and we're taking the sum, j goes from 1 to n, of x of
Very
xj
nice to
times
be
delta
here.
xj. And
I'm
this
not
limit of a
doing
sum
much
is by
talking.
definition
This
the
is a
integral of the
boring
force with respect to
stream,
dx.
man.
So what we end up with is our work is the integral of
It's
f of
just
x. Now,
something
it's a
I
function,
want to
and
do
we have
too.
integration variable x prime of dx prime, where
To
x prime
learn.
is going from our initial position to
And then
our final position. And this is now
apply.
our definition of work, which generalizes a constant force to a
I mean,
non-constant
it's
force.
just classical
Now again,
mechanics.
let's try and look at some type of geometric interpretation.
I've
So
heard
plot
all
f of
this
x
before.
versus x. And now let's consider a case
But
where
I'm doing
we
it
have
at
some
2
arbitrary
times
force.
the speed,
So
so I
let me just
cannot
draw the
really
force as if
comment
it were
on
arbitrarily increasing
stuff.
as a function of x. And here's our x initial, and here's our x final. And
It's
again,
still
we would
at
like
the
to make a
area
geometric
under the
interpretation.
curve.
Let's consider xj, and I'll make this very big, xj plus 1 for the sake of visualization. And this value here is f of xj. And so what we see now is that little bit of work, like we had for a constant force, can be approximated as the area underneath the curve for just this small interval between xj and xj plus 1. And if we make this sum, what we're doing is we're just taking a series of approximations to the area under these curves. Now you can see graphically that there's very little error when the function was nearly constant, but in this position where the function is growing, this represents our little error. However, in the limit, as n goes to infinity, we can
He
make
made
that
a
error
box
go
plot, yeah.
vanishingly small.
I mean,
So once again, we see as a geometric
any
interpretation
differentiable
that this
function
the area
is a box plot.
under the curve of the
Just
force versus
an
position between the points,
infinitesimal
the initial xi
box
and the
plot.
initial and the final x final, where the particle is being displaced from an initial position to some final position. And here we can call our initial position anywhere we want. If I write that as x initial to the final position. And that's our generalization of the definition of work. I'd like to now show you two mathematical facts about how we integrate quantities of motion. Suppose we have an object, let's call this the I hat direction, and it's moving, and it has an x component of velocity. And suppose it starts at some initial position and goes at some final position. And in the initial position, it was at time ti, and the final position was at t final. Now, we have two very important integrals that we want to look at, which govern how we describe, how we integrate acceleration with respect to time, and also how we'll integrate acceleration with respect to space. Now, recall that our acceleration, which may be a function of time, is the derivative of the x component of velocity with respect to time. So let's first look at a simple integration of acceleration with respect to time and see what we get. So if we integrate acceleration, I'm going to introduce an integration variable, dt prime, and our integration variable goes from our initial time to some final time. And if we use our fact that acceleration is the derivative of velocity, then we can write this as ddx dt prime again. After a while, I'll drop the dummy variables and the endpoints of the integral, and this simply becomes the integral from t prime t initial, t prime equals t final of dvx prime. Now notice we've done a change of variables in integration. So instead of now talking about the endpoints of the integral from t prime t initial to t final, now what we're doing is we've changed our integration variable. And so what we have is we have the velocity integration variable is going from some initial
He would. He
variable
fucking would. He would fucking dodge it like in Matrix, and then somehow the gravitational pull of his hair, every single hair has a gravitational pull, they all add up into the center of mass, which we don't know where it is because of the wavelength type of hair he has, and then it would just the bullet would just rebound gravitationally and go right back into your head. So you would lose against this guy.
As dvx times dx prime dt prime dt. And when we do that, we have this result that dx prime dt prime is precisely what we mean by dx. Now, I'll introduce some dummy variables there as well. So what our integrand becomes is dv x prime, dx prime. That's
Yes,
the product
an
of integrand,
extremely quick
dx prime.
orbit.
And now our new integration variable is going from some initial value to some final value. Once again, this is a straightforward integral. For those who haven't seen integrals like this, it's just something like x dx is x squared over 2, but our integration variable is dx prime. So what we get is 1/2 dx final squared minus dx initial squared. And so what we see here is two fundamentally different facts, that if you integrate acceleration with respect to time, you get the change in velocity. But if you integrate acceleration with respect to space, you get 1/2 times the change, not of velocity, but of the x component of the velocity squared. And both of these facts are central to how we'll analyze the concept of work and how we apply Newton's second law.
Good, good. Yeah, yeah. It would hit you. You would
We're
die.
now going to derive the work energy principle. We're going to do so by using Newton's second law, but we're not going to consider it with respect to time as what we've previously done, but we're now going to consider it with respect to space. So F equals ma, and we're going to take the x component of that, and now we're going to integrate this. So f x dx prime, and it runs from x prime equals x initial to some final value. And then over here we have, we're going to pull the m out, m integral, and it also goes from some initial to some final value. And we are going to have x dx. We have previously shown that this integral here is 1/2 v final squared minus v initial squared. And if we're going to plug this in here, we're going to get that this expression is 1/2 m v final squared minus v initial squared. And you should recognize this term. This is the change in kinetic energy. And what we have here on the other side, this integral fx dx is defined to be the work. Work done on the system, which we're going to call W, and that work done on the system is change in kinetic energy. So this is the work energy principle.
Good.
Consider
Power.
the motion of an object that is under the action of a force. So we have some force that's acting on this object, and we have a little displacement ds. So this is a small displacement of the object. Then we know that the small amount of work done by the action of this force is f dot ds, and the rate of doing work. So let's now
It's
use the
him.
concept of power.
He does the most
That is f
things,
dot ds
the most
over dt.
videos.
And ds dt is just the velocity of the object.
And I like
So
him,
we see
to
very
be
simply
honest.
that when
He
we talk about power,
explains it
sometimes people use the symbol P,
really good.
although we can also talk about pressure and momentum, so it's a little bit tricky. But here, the power is f dot v. And power is a concept that will appear in many different settings.
He is power. Oh, we have a skill
We
of
now would like to generalize our concept of work to the motion of an object that goes in more than one dimension. And so if we have our object here, and we're applying a force, and the object is moving, and let's say the path is a little bit more complicated, so our object a little bit later has moved, and we're going to call that the displacement, we now want to generalize our concept of work to handle this type of motion in more than one dimension. In order to do that, we'll need a new mathematical operation, which we're going to call the scalar product. So what I'd like to do first is define this in terms of vectors, and then we'll apply it to the concept of work. So suppose I have two vectors, A and another vector B, and they're separated by an angle theta. And in this case, our theta, we're going to just take it between 0 and pi. Now, I'd like to talk about how much one vector projects in the direction of the other. So if I call this the parallel component of B, then I want to define a quantity, which we're going to call the scalar product of A dot B, which is the magnitude of A times the amount of B that is in the direction parallel to A. Now, from our geometric diagram, you can see that B parallel is equal to the magnitude of B times cosine of theta.
cosine of
Now,
theta.
remember, theta is going from 0 to pi, so this quantity, B parallel, can both be positive or negative. If theta is between 0 and pi over 2, then in that range, the cosine goes from 1 to 0, and this quantity, B, will be greater or equal to 0, B parallel. If theta is going from pi over 2, theta to pi, then we have that B parallel is less than or equal to 0. And in particular, at the value pi over 2, B parallel is 0, because when theta is pi over 2, the B vector is completely perpendicular to A. And this is what we're going to define to be the scalar product. But geometrically, we can also look at, let's draw our pictures again, A and B. And now let's consider how much of A is parallel to B. So that's A parallel. And if this is the angle theta, we see that A parallel here, and I'll write it as A parallel, is the magnitude of A times cosine of theta. And so I can also define A dot B as equal to how much of A is parallel to B times the magnitude of B. Now, in both of these instances, because B parallel is the magnitude of B cosine theta, and A parallel is the magnitude of A cosine theta, what we're writing is that A dot B is the magnitude
It's a
of A
cosine.
cosine theta, magnitude of B. And now you can
That's
see
it.
that this quantity is A parallel, and this quantity is B parallel. And this is our geometric definition of a dot product. Now,
Yup.
one thing that we want to consider are two important rules for dot products. And they're the following. That if we take a vector and multiply A by a quantity, C here is a scalar quantity, then this is equal to C times A dot B. Now, geometrically, this is very easy to see, because if we draw A and we draw B, and if I multiply A by a scalar, and let's make, in this particular picture, our scalar bigger than 1, then the new vector A is multiplied by C, and it's C times A, and the scalar product is just CA dot B is the magnitude of CA times how much of B is parallel, and when you multiply this together, you get C times A times B parallel. Now, C of A dot B is equal to c times the magnitude of a times b parallel, and you can see that these two expressions are equal. So if you multiply
If you saw
the dot
this,
product
man,
by a scalar, it satisfies
you
this
would
equation.
run.
And there's one other crucial rule that we'll need when we
You
look at
would run
that if you take a
out
vector
of your
A
house.
and you add to it a vector
You
b,
would forget
and
about
you
your
add a vector
house.
c,
You would
then
forget about
this is vector addition is vector
everything
multiplication.
you
This
have.
vector addition distributes over vector
You
multiplication
just
by a
go.
dot c
That's
plus
it.
b
No
dot
guns,
c.
no
So these two
nothing.
facts
You
are crucial
Americans
to our
could not save
development of
yourselves
vectors.
from this
And
guy.
one thing that we can say is we'll leave this as a little
Because
exercise.
this guy
to
explained
prove this result.
the
It's a pretty
rocket
straightforward
equation,
construction,
the
and just to give you a
power,
little bit of a hint, we have a vector A,
most
and
of
another vector B,
kinematics, everything.
and we have a
If you
similar
just
vector
think
C.
about it
Then
for a moment,
if I draw the vector
this guy
A dot B
knows the
plus
in
C,
and outs of your
and I want to
house.
take A
He
dot C,
calculated
so I
the
have how much of A is
he
parallel to C,
calculated the
and if I look at how much
torque
of
on
B
the
is
house
parallel
he
to
would
C,
need
then
to
as part of the
exert
exercise,
to
make sure that you
destroy
see
it
that how much of A
completely.
plus B is parallel to C.
You would just die if you closed the
So
door.
these are our definition of scalar product and the two key facts that we'll need when we apply it in our example of work. We've so far described abstractly what we mean by a dot product by a definition of AB equals the magnitude of A and cosine theta times the magnitude of B. But
You
many
would
times in
run.
physics problems, we actually have vectors in space, and we want to see how to do this in terms of a Cartesian or any coordinate system in particular. So let's set up a coordinate system. We'll call it Cartesian, A and J. And now this is very important. Let's define a vector A here, and let's have another vector in a completely different point B. We still can take the dot product of these two vectors, but in order, this is our plus x plus y, and I'm only doing things in two dimensions. So how do we calculate the dot product? Well, the first thing that we want to look at is our unit vectors. What are the dot products of unit vectors? Well, if we take I hat dot I hat, that's the magnitude of I hat times cosine of the angle 0 times the magnitude of I hat. And cosine of 0 is 1, and the magnitude of the unit vectors are 1. So when you dot product the unit vector with itself, you get 1. And therefore, it's also true for the j hat. J hat dot j hat is 1. What happens when you dot product two vectors that are perpendicular? Well, in this case, this is 0 because the angle theta is 90 degrees. And remember that cosine of 90 degrees is 0. And anyway, when two vectors are perpendicular, there's no component of one vector that's parallel to the other. So these are
Yeah.
the essential facts that we're going to need to calculate the dot product. of
Vape
two vectors that are separated
Nation.
in space. So the way we do that
That's
is
from
we'll
the
begin by
YouTube.
writing down the vectors in Cartesian coordinates, where ax is a scalar, and the vector part is in the unit vector, and we have
If
ay,
I
j,
saw this
and likewise
guy,
we can write b as bx
I
I
would
hat
run.
plus by
Forget
j hat.
about the
And now when we take
buildings.
the dot product of these two
Forget
vectors,
about everything.
we're gonna write out both
There's
of
a
them here,
nuclear
so we see.
bomb somewhere near
So
me.
here is our scalar or dot product. We use those words interchangeably. Now notice that we've already shown that the dot product distributes over vector addition. And also, if you multiply a scalar by a vector, you can pull the scalar out. So there's four terms here. Ax I hat dot bx I hat plus ax I hat dot by j hat plus ay j hat dot bx I hat. This is a little tedious to write out. By j hat. And now, because these are scalars, we can pull them out, and the only part of a dot product that matters is how the unit vectors dot. And that's why we have these two results. I hat dot I hat is 1, j hat is 1, and I hat dot j hat is 0. So the first term is ax bx. I hat dot j hat is 0, so we don't need that. J hat dot I hat is 0, and finally j hat dot j hat is 1, and so we get plus ay by. And that's how we define the dot product in Cartesian coordinates of two vectors. Now notice that if we dotted a vector, a dot with itself, that would just be ax plus ay, which is the components squared. And that's equal to the magnitude of the vector squared. And so we can say that the
Yes.
magnitude of the vector, of any vector, is you take its dot product with itself, you take the square root, but remember, we always take the positive square root because magnitudes are positive. And that's how we calculate the scalar product of vectors. And many times in the application of physics, when we have physical quantities that are vectors in different places, we use vector decomposition, and we use this procedure. We'll learn how to do this this is a Cartesian picture, we'll learn how to do that in polar coordinates when we need it later on.
Polar coordinate is gonna be insane. Okay,
So
how
let's
does
talk
the
about
bro
kinetic
write
energy.
in
Remember,
reverse?
an object moving with speed v.
He
We
is
define
in
kinetic energy as a
reverse.
scalar quantity,
Don't you
1/2
understand?
m v squared.
He
This
is
is
in
squared.
reverse. Just
what's very
think
important
about
about
it.
is reference
He's
frame
writing
dependent,
like
because the velocity of the
normally,
depends on what reference frame we're in.
and they just
Now, one thing to keep in mind
reverse
is that
the picture.
remember our definition of scalar
They
product.
just
A dot b is the magnitude of a,
they
magnitude
just
of b times
swap
cosine of theta.
left
So
to
a
right.
vector dotted into itself is
That's
just
it.
the magnitude of a squared, which we can just write as a squared because the angle is 0. So here we have a v squared. So the dot product b dot b, d squared, enables us to write kinetic energy as 1/2
Think.
m v dot d. And we see our first example of a scalar product describing a physical quantity. Now, if we had a coordinate system where we wrote v as vx I hat plus vy j hat plus vz k hat, and we took the dot product of that vector with itself, then we just know that it's the square of the components. And so in a Cartesian system, we can now say that the kinetic energy is 1/2 m vx squared plus vy squared plus vz squared, because that's the velocity squared. So there's a simple way to express abstractly the kinetic energy of the dot
Now
product,
he
and
writes in
explicitly the coordinate
reverse.
system as the sum of the
No,
squares of the components
the
of
only
velocity.
proof he doesn't write in reverse is that there are other people who write
So far we define work
sometimes.
in one dimension, but let's consider the
If
time particle in
if
one dimension.
this
On the screen,
man
it's a two-dimensional path, and here's our
was
particle.
the only
And what we have
man
to do is define the concept of
here,
work for this type of path.
I
Now,
would
let's say
believe
for
it
this instance,
that
our particle
he
is
wrote
experiencing
in
the force
reverse.
F. And
I
the
would
particle
believe
is being
it.
displaced by distance ds, which is always tangent to the path.
Like there's
And what we'd like to do now is
no
talk about the
way
work done
you
with this
you
particle.
wouldn't
Now,
convince
what
me
we'd
that
like to
this
first
man
say is
could not
what we're
write
going to do
in
is imagine
reverse.
that we're going to break the path down into a bunch of small intervals. And
Yes.
let's call this the jth point and the j plus 1 point. Then our particle will start at j, and we'll displace it, delta Sj, to the j plus 1 position on the path. And here, let's denote the force by Fj. And now what we'd like to do is define the work for this particular section. Now, our concept of work is the force in the direction of the displacement. So what I'd like to do is I'd like to define the quantity Fj, and I'll put a little parentheses upstairs, parallel lines upstairs. This is the component of the force Fj in the direction of delta Sj. Now, the way we denote that is we can then say that if I take the dot product of Fj dot delta Sj, this is the component of the force in the direction of the motion, because remember our dot product, if we call this angle theta j, is taking
I
how much
don't
one
have
vector
a
in the
mirror
direction of
to
the other
try.
times the magnitude of that displacement. And again, when we write that component in our notation, if we call this angle theta j, we know that that's the magnitude of Fj times cosine of theta j. Now,
Yes.
because this is the amount of force in the direction of the motion, that's how we've defined work done, and we'll symbolize the work done in taking the particle from j to j plus 1 by the symbol W.
It's
WJ.
really not hard
And
to
now, this is a scalar
understand
quantity,
this.
and when we want to find the total work, what we have to add up is from some initial point to some final point, how much work is being done. We're taking
Currently,
our
I
particle from
really
this
like
position
it.
to the
I
final
am
position, and
kind
it's
of
just
even
the sum
excited to
for all
get
these
to
j's,
the
and let's say we have n of them,
examples
of Wj,
and do
and
do
right now
it
we're going to call
myself.
this W, is just that scalar sum, and that's equal to the sum, j goes from 1 to n, of Fj dot delta Sj. So now we'll use the vector dot product, because we already know that this is how much of the force is in the direction of the motion. However, this answer depends on how fine we broke up this path. And what we've seen many times now is that the actual work that we want,
Integral.
let's write this as n because it depends on the number of paths, is the limit as n goes to infinity of this sum of scalar amounts of work. Now, when we take that limit as n goes to infinity of this sum, j equals 1 to n of Fj dot delta Sj, this quantity is formally what we mean by a line integral. And we denote that with a new notation. We'll denote a line from our initial to final, and it's a dot product of the force dotted into the small displacement. Now, whenever we see the dot product in an integral, that distinguishes it from a normal integral, and this is what we call a line integral. Now, again, why did we switch from our delta s's to ds's? Because when we take the limit as n goes to infinity, our grid becomes finer and finer and finer until we're shrinking down to a point where we can just talk about the differential displacement ds and the force acting on a point. And that's what our line integral is. Now,
Yes.
what we'll learn next is how to calculate this line integral for a number of important physical examples that occur in our interest in mechanics.
Yes. Work kinetic
We would now like to
energy
generalize the
theory.
work energy theorem to more than one dimension. Remember that we defined our work as an integral from a to b of a force dot ds. And graphically, let's look at that as if we start at a and we go to a point b, and if at some point on this path
Where is the
we have a force f, and the displacement is always tangent to the force for an object m, we would like to now figure out how this integral is related to the change in kinetic energy. So, first off,
I could
it's
add
always important
subway
when analyzing
surface
a Newton's
here
law to understand where
and
Newton's second
play
law
it.
comes in. And for our point particle, Newton's second law is that the force is
That's
equal to mv,
actually a good
which we can
idea.
write as mass
That's
times
actually a
the
good
derivative
idea.
of the velocity. And so our first step is to rewrite the work integral.
But
And now
I
to
don't know where
incorporate
to
Newton's second
put
law
it on the
into this
screen.
So this is no longer simply
Because
a
he uses
concept of
most of the
physics, but
screen,
it's
even
combining
I'm
the
covering
second law
up
and our definition of work.
what
Now, what I'd like to do here is to
what
note
he's
that
using.
the displacement of a particle is always equal to the velocity times dt. So if we put that result in here, ab of m dv dt dot v dt, you can see that we can cancel dt's, which is essentially taking the time out of this integral and writing the work entirely in terms of the small change in velocity dv scalar product with the velocity. And this is the quantity we now like to calculate. So one way when we ever want to calculate these dot products, we choose a coordinate system. So let's choose a Cartesian coordinate system plus x plus y with our unit vectors I hat and j hat. And now our task is to write down these various vectors. So for instance, dv can be written as dvx I hat plus dvy j hat. Now if we were to go into 3 dimensions, we would have dvz k hat, but I'm just going to do this in 2 dimensions. Similarly, the velocity is vx I hat plus vy j hat. And now when we take the dot product, as we've learned in Cartesian coordinates, it's just the components dvx, dx, and I'll just do a little parentheses there, plus dvy, dy. And so now our work integral, AB, is equal to the mass times dvx dx plus the mass times dvy dy. Now what we have here is a sum in the integrand. But by the rules of integration, we can rewrite this integral as 2 separate integrals from a to b
But where
of
would I
m
put
dx,
subway
dx,
surface, man?
and from a to b of m dvy dy. And now we can integrate
I
each
can
of these
try
separately. And if you
that
recall,
for the
in one
next
dimension, we used our integral formula.
stream.
This is just vx squared. And
I can
when we
try
integrate them,
that.
what we have to look at is the endpoints of our
Or
integral.
Minecraft or
What we're
something.
integrating is the velocity, and we're going from some initial value to some final value. So our first integral simply becomes m vx final squared. I'll pull out the factor 2 minus vx initial squared, where a dx initial is the initial x component of velocity at a, and vx final is the final component of b. And I have a similar term here, which is vy final squared minus vy initial squared. And when I combine our terms, vx final squared plus vy final squared minus 1/2 m vx initial squared plus vy initial squared, we've already shown that our kinetic energy, 1/2 m v dot b, is 1/2 m vx squared plus vy squared. And so we see that this is just the final kinetic energy minus the initial kinetic energy. And so we can call that delta k. And what we have now is the work energy theorem, and I'll come back to my original statement that the work is equal to the change in kinetic energy. And this is a combination of our definition of work and Newton's second law.
Yes.
Let's apply the work energy theorem principle to the motion of a block sliding down an inclined plane. And here's an inclined plane at an angle theta, and let's choose a coordinate system. We'll choose x equals 0 up here, I hat here, and here is our coordinate function. And suppose that the object starts at xi, that it ends at x final. If we want to calculate the work energy, then what we're going to learn is that this theorem is two different sides. Calculating change in kinetic energy is simply a description. This is 1/2 m v final squared minus 1/2 v initial squared. That's a property, parameters of the system at the initial state, the speed, or the velocity speed, which is kinetic speed squared, and the same property v final in the final state. Now over here, we have two types of forces acting on this object. So here, we need a free body force diagram first, and this side is where the physics side lie. And so we want to draw our force diagram. So if we have our block, we have the friction force, we have the normal force, we have mg. Recall, if the plane is inclined theta, that's also the angle theta. If we chose I hat, j hat unit vectors, I just want to repeat that on my free body diagram. Now, we can think of this integral as just one-dimensional motion in the x direction. And so we have two different forces that we have to calculate. The friction force is in the minus x direction, so we're integrating minus the friction force with respect to displacement from x initial to x final. And what about the gravitational force? Well, the gravitational force has a component mg sine theta in the x direction. So when we integrate that x component, we have now plus, because it's in the same direction. Remember, we're displacing a little bit dx down the inclined plane, so we're going from x initial, x final of mg sine theta, which is a constant, dx. And so when you're applying the work energy theorem, you need to integrate your forces and actually calculate the work. Now, again, if you looked in the j hat direction, and we applied Newton's second law, n minus mg cosine theta is 0, and our rule for friction is it's mu k times n, or mu k mg cosine theta, then what we have is that in both instances we have a constant force, so it's just force times displacement. So we have minus mu k mg cosine theta times the displacement, which is x initial, x final. Over here, we have mg sine theta times x final minus x initial. And now we've calculated separately both sides of our work kinetic energy principle. As in all our physical laws, the equal sign means the work is equal to the change in kinetic energy. I'll emphasize that by now placing the equal sign because of our physical law. And so equaling 1/2 m v final squared minus v initial squared. And now I have a relationship between the parameters of the initial state, which I'm calling x initial and v initial, and the parameters that describe the final state, x final, v final. And depending on which set of these parameters are given, I can conceivably solve for the other ones. One thing I do want to point out when we do this example is we've described work as a dot product from A to B. Take the friction force. Well, in this instance, if we wrote this out explicitly, it would be minus fk I hat dot dx I hat from the initial to the final. I hat dot I hat is 1, and so you see we recover from x initial to x final of fk dx. And that was the first piece. The second piece, the gravitational force dotted into ds from x initial to x final. Well, if you wrote down the gravitational force mg as a I hat component and a negative mg cosine theta j hat component, then when we take the dot product, again, where our ds here, we'll write ds as dx I hat. Then when you dot product mg dot ds, we have I hat dot I hat, which is 1, but j hat dot I hat, they're perpendicular, so that's 0. So the only piece that survives in the scalar product, mg dot ds, is these two pieces, and so we get the integral from x initial to x final of mg sine theta times dx, and that's precisely our second piece here. So here's a simple application of the work energy theorem.
All right.
We would now like to explore a property of work done by forces called path independence.
Okay, path independence.
So recall that our work
good.
is defined to be an integral of f dot ds from some initial to some final point. Let's
BRB.
look at an example. Force that we're going to look at is the gravitational force. And let's draw a coordinate system. Let's take an initial point and a final point, and let's choose plus x and plus y, and our unit vectors I hat and j hat. And in this example, we're going to consider the gravitational force near the surface of the Earth, which is constant pointing downwards. And what I'd like to do is consider two paths. I'd like to consider a path. That first path goes straight up and over. So this will be path 1. It has 2 legs. And the second path, path 2, will go horizontal and vertical. So that's going to be path 2, and it has 2 different legs. And we'd like to evaluate this integral on both paths. Now, the way we do that is, first off, let's start with path 1. We'll call this y initial, and we'll call that y final. And we'll draw the gravitational force, mg on both legs. And now we see that when we do the integral along this first leg of path 1, the gravitational force is opposite the direction we're moving, the displacement, so the integral will be negative. The force is constant, and so the work done is simply minus mg times delta y, which is y final minus y initial, on that first part. Now, on the second part, this is a right angle, and because it's a right angle, the dot product is 0, so that's the total work done on path 1. Now, on path 2, well, again, let's just draw our forces. We have gravity down, and we have gravity down. And we can see that once again, on the first horizontal leg of path 2, this integral is 0, because it's moving perpendicular to the force, the direction of this along the path. And on this leg, just as on that leg there, the gravitational force is down, the integral is negative, we get exactly the same result. Now what we'd like to do is consider a more general path, rather than these 2 horizontal and vertical legs. So let's draw a coordinate system again. Let's introduce I, and let's introduce f, plus y, and plus x. And now let's consider a path which is moving like that. Now, on this path, what we want to do is break it down into horizontal and vertical pieces. Horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical. And let's focus on one of these pieces, which has a displacement ds going from one point to another. Now, if we blow that up, so we have our displacement ds, then what we have here is a displacement dx in the horizontal direction and dy in the vertical direction. And so we see again that when we compute this work and our gravitational force is downward, then the horizontal part of this displacement, dot product in the horizontal direction, 0, only the vertical part cancels. And so when we add up the work along these horizontal and vertical pieces, only the vertical piece counts. We're just adding up the dy's until we get y final minus y initial. Now let's be a little more analytic here and write out our ds as a vector dx I hat plus dy j hat, and our gravitational force as minus mg j hat. Now the work is the integral from the initial to the final place of fg dot ds. And so when we do that, we have minus mg j hat
Green
dot
sure doesn't
dx
help.
I hat plus dy j hat, and from our initial to the final place. And notice that we have j hat dot I hat, they are perpendicular, so that dot product is 0, and j hat is 1. And so what we're left with here in the integral is simply now we're integrating from y initial to y final, because we only have minus mg dy. And that's what we said before, only the vertical parts are adding up. And so when you do this integral, mg is a constant, we get mg times y final minus y initial, and that agrees with what we had before. So this type of
Great.
force is an illustration of a force where the work done is independent of the path we choose from the initial to the final place. Let's now explore an example of a force in which the work done is not path independent. And the classic example is the friction force. So let's consider the following setup. Suppose we have a horizontal surface with friction, and we have an object, and we're moving this object. So let's choose an origin. We'll call this plus x, our I hat direction. It's all going to be one-dimensional motion. And we're going to move this object from an initial to a final state, and we're going to move it directly in a straight line from the initial to the final state. And this will be our path 1. And in our second case, what we'd like to contrast with that is that we'd like to move the object out to a point xa, and then back to the final point. So this is our path 2, has 2 legs, and we'd like to compare the work done on these 2 paths. So for path 1, we'll begin by calculating. Our force here is the kinetic friction force, and the kinetic friction force, remember, is, in this case, it's going to oppose the motion.
Okay.
So we have force kinetic for path 1, and that is minus mu k mg in the I hat direction. And so when we do the integral for the work from x initial to x final, this is path 1, then we have minus mu k mg I hat dotted into, now what is the ds for this path? It's simply dx I hat. So dx I hat. Notice we're not putting any sign into dx. That's the sign will show up in terms of our endpoints of our integral. So when we do the dot product here, we have I hat dot I hat. That's 1. And so this integral, we can pull out all the constants, mu k mg. We're just integrating dx from x initial to x final. And so we get mu k mg times x final minus x initial. Now for path 2, we have 2 separate integrals. So for path 2, we'll just show the first part where we're going from x initial to xa. Then the friction force is opposing the motion. And we always just write dx in terms of the coordinate system, dx I hat, because you'll see that the signs show up in the endpoints of the integral. And then when we're coming back, I'll put that in a different color, and I'll put it below it. So when we come back, notice the friction force is going to change direction. ds will still be written that way, but pay close attention to the endpoints of the integral. So now what we have is 2 integrals. So w is the integral from x initial to xa. And now I'm going to take the dot products here directly. It's the same friction force. We still have the same integral, which is minus mu k mg dx. Now here's where it's a little bit tricky. Notice on this path, fk is plus mu k mg I hat. And so when we dot it into dx, we have a plus sign. We'll just continue that integration here of mu k mg dx from xa to x final. Both of these integrals are straightforward integrals to do. This is minus mu k mg xa minus x initial. And over here, we have a plus mu k mg x final minus x initial. Notice x final minus x xa rather is negative. And so both of these integrals are negative as we expect. And so what we see here is that we have 2 pieces. So minus 2 mu k mg xa. And then we have that other piece, mu k mg x final minus x initial. Hang on, this is actually...
So we did that amount of more work.
So our answer is very different.
2 times.
Because it displaced the amount that we traveled is different. So what we see here is an example of a force, which is the work done is not path independent, but depends on the path taken from the initial to the final states.
Good. Conservative forces.
We considered the work done by a gravitational force, which was path independent. Now let's generalize that to any force between 2 points, I, and another point, F, that if the work done in going from the initial point to the final point, this is path independent, then we call this force a conservative force. Now, there are many conservative forces that we'll analyze in this class. Examples will be the inverse square, electric force, or the gravitational force. We've already seen gravitational force near the surface of the Earth is conservative. Spring forces are other examples of conservative forces. But let's look a little bit in detail. Suppose we call this path 1, and we consider a second path, path 2. Then a property of conservative forces is that the work done is independent of that path. So if we total up the work from the initial to the final on path 1 of f dot ds, and then we go from the final point to the initial point on path 2 of f dot ds, then because these integrals are independent of the path, and all we've done is shifted the endpoints, is we get 0. And that's the statement, and we'll write W conservative here for conservative forces. So we're going to call this force conservative if it's path independent. So what we have here is a statement that the work done by conservative force, now what we'll do here is indicate a circle by a closed path, that the work done by conservative force on a closed path is 0. What does that closed path look like? Well, remember what we did was we went from 1, but then instead of going in this direction, we came back on path 2 from the final to the initial point. And if the force is conservative, the work done around the closed path is 0.
Makes sense.
So we saw that a conservative force is path independent. And we also had examples of forces which are path dependent. If you have path 2 and path 1. And the work done is path dependent. So that means for each path we would get a different answer. Then we call this force, F, we denote it by NC, is called non-conservative. And again, we see that friction is the best example of a non-conservative force. And if we go, again, for non-conservative work, if we integrate from the initial point to the final point, for instance, on our path 1 of this non-conservative force, so if we integrate this way, and if we reverse the integral, and so we go back from the final point to the initial point on path 2, that these integrals will not be equal to the negative of each other because the quantities are different for the different paths in general, and so this is non-zero. And in fact, that's the property of non-conservative forces, that the work done around a closed path for a non-conservative force is not equal to 0 in general. There may be one specific closed path in which that answer is 0, but in general, it's non-zero. Let's review what we've done this week. We've seen that the work
different guy.
done by a force along a trajectory from point A to point B can be written as the integral of the dot product of that force with the displacement going from point A to point B, where we note that this integral, in general, must be evaluated over the particular path taken from point A to point B. This is called a line integral or a path integral. And again, I want to emphasize the value of this integral depends, in general, on the path taken from point A to point B. And you can understand that if you consider the fact that, in general, the force is a function of position. And so if you go along different paths, the dot product of the force with a particular path may be different, even though you're going between the same endpoints. Now, the reason that the work is a useful concept is that it allows us to understand how the kinetic energy of an object, so the kinetic energy is 1/2 mv squared, the work allows us to understand how the kinetic energy evolves under the action of a force. And we see that through what's called the work kinetic energy theorem, which states that the work done, so again, the integral of F dot ds from point A to point B evaluated along the specific path, is equal to the change in the kinetic energy. So that's 1/2 mvb squared, since v is the final point, minus 1/2 m a squared, where a is the initial point, and this is equal to the change in the kinetic energy. And we derived this theorem from Newton's second law, F equals ma. So this is essentially just a restatement of Newton's second law. Now, two things to note about the work and this work integral. The first is that the work integral, when evaluated, it just gives a number, right, because the dot product is a scalar, and that number can be either positive or negative or even 0, depending upon whether the velocity increases, decreases, or stays the same under the action of the force as you go from point A to point B. The second point to emphasize is that, again, this integral, in general, must be evaluated along the specific path taken from point A to point B, which means that in order to evaluate the integral, we need to know what that path is. Now, if we have a situation where we don't know in advance what the path is, then we can't evaluate the integral. So, in a way, it might seem like a not very useful concept that we haven't really made progress, because we need to know the answer about what the trajectory is before we can calculate the work done, and it's not clear why that's useful. However, what I want to point out is that there are two special cases that are particularly useful. The first special case is that of constrained motion. Sometimes we know in advance what the path is going to be, because the motion is constrained. We know that it's going to be moving along, the object is going to be moving along a circular path or along some particular track of some particular shape, and as long as we can describe that trajectory, we can evaluate our work integral along that trajectory. So that's a case where, even though the work is a path-dependent integral, we know the path, and so we can evaluate the integral. The second special case we've seen is that there is a special class of forces called conservative forces. And conservative forces have the property that the work integral is independent of the path. So for a work integral, for a conservative force, the work integral only depends upon the endpoints A and B, and not upon the path you take to get from A to B. So for any path, you always get the same value of the work integral if the force is conservative. And so those are the two cases in which we can usefully apply work and the work energy theorem. Now, in general, one might have a combination of conservative and non-conservative forces acting on a system. And in that case, we can actually write the work as consisting of two separate terms. The work done by conservative forces, what I write as WC, plus the work done by the non-conservative forces, WNC. And so the conservative work is just the work integral evaluated for the conservative forces, so FC, or conservative force, dot ds, going from A to B. And because this force is conservative, this integral is path independent. Let me emphasize that here. This is a path independent integral. It's not a line integral. It only depends upon the endpoints because the force is conservative. The second term is the non-conservative work, and that is the work done by the non-conservative force, F sub nc, dotted with ds between the same endpoints, A and B. But this integral does depend upon the specific path. The path matters for this term because there the force is non-conservative. So in general, you can compute the work by separating out the conservative force and the non-conservative force acting on the system if both are acting. If the force is only conservative, then you only have to worry about the path-independent integral, which in general is much simpler to evaluate. If the force is non-conservative, then you need to specify the path in order to evaluate the integral. Again, a path-dependent integral is also called a path integral or a line integral.
See how much we have left. We're at 130.
Let's look at these two blocks here. Block 1 has a mass of 3m, and block 2 has a mass of 1m, and they are colliding and sticking together. And then they're going to move in this direction and eventually slide onto this rough surface here. What we want to figure out is what was that initial velocity v naught with which the two blocks collided. So up to this part here, before this x equals 0, there's no external force acting on the system. So conservation of momentum holds, which means that p final equals p initial. Okay, so let's put this together. We're going to have 3m v naught. That block goes in the positive I hat direction. Block 2 goes the opposite way, so we have m v naught. And then at the end, when they're stuck together, before here, we have to consider only this portion here with that pertains to a frictionless surface. We have 4m v final. And so the m's fall out. This is 2, this is 4, so we'll see that the final velocity is v naught half. Now, in order to get to this v naught, we also have to consider energy. And in particular, we have to use the work energy principle here because this joint block is going to slide onto this rough surface here, so we can make use of the work energy principle. We know what the initial conditions are up to this, or at this point here, using the conservation of momentum from here in the first place. So we want to use work equals delta k, the work energy principle. Let's look at the work first. Work is the integral of f dot ds, and we're dealing with a one-dimensional problem here, so we can just write fx dx, and we want to have this run from 0 to d. I should say here that this block eventually comes to rest at x equals d. We're going to use that in a second. So let's look at what this F is. That's the frictional force here at work. And actually, which direction does it go? It opposes the motion, Fk. So we're going to get a minus sign here, integral Fk dx. Again, going from x prime equals 0 to x prime equals d. Now, what is this Fk? We know that Fk equals mu k n. And from doing a quick free body diagram, we'll see that we have 4 mg going down, and we have a normal force going up. And so we'll see that n equals 4 mg, which we can then plug in here, and then that goes in over there. And the coefficient of kinetic friction is actually given to us, so that nicely works out. So we're going to have minus integral x prime 0, x prime equals d. The coefficient first, bx squared, and then the n, 4 mg dx. If we integrate that, we are going to get minus 4b mg, and we'll integrate this one. So that's x cubed over 3. And we're going to plug in this value here, so we're going to get a d, and that second term falls away, so we are left with a d cubed here. So this is our work, and now we need to look at the change in kinetic energy between here and there. We already know that this block is at rest at x equals d, so if the velocity is 0, our kinetic energy will be 0. And so our k final minus k initial is going to be just a minus initial, and that's initial here, which is the final situation of our collision. So we're going to look at the combined block. So we'll have minus 1/2, and we have 4 m v final squared. We determined here already that the final velocity is the initial 1/2, so we'll have minus, here we're going to have 2 m, and now v naught squared over 4, and that actually gives us minus 1/2 m v naught squared. Okay, so now we can put this all together. We apply this work energy principle, so we're going to get minus 4/3 b mg d cubed equals minus 1/2 m v naught squared. We'll see that this and this and this and this goes, and so we're going to get v naught equals 8/3, and then we have b g d cubed and the square root of that. So this is our initial velocity with which the two blocks collided initially, then eventually went onto this rough surface and came to rest here at x equals d.
Square root, not visible.
This week, we will continue our discussion of energy. We will introduce the concept of potential energy, which is related to the work done by a conservative force, and also the concept of total mechanical energy, which is defined as the sum of the kinetic and potential energies. We will demonstrate that the total mechanical energy of a system remains constant if only conservative forces are acting. This is known as the principle of conservation of mechanical energy. We will also see how the work done by any non-conservative forces causes the total mechanical energy of the system to change, usually causing mechanical energy to be lost from the system. Finally, we will see how graphs of the system's potential energy as a function of position provide an elegant way of understanding the behavior of the system for a given value of the total mechanical energy. We're now going to introduce the concept of potential energy. Let's begin by considering a system where a conservative force is acting. So I'll consider a conservative force, which I'll call F sub c. Right? So for such a force, the work integral is path independent. So the work integral for this force is the integral of F sub c dot ds, which is the path going from point A to point B. And for a conservative force, this integral does not depend upon the path from A to B. It's independent of A and B. So it depends only upon the endpoints. Okay, so this is a path independent integral. And since it depends only upon the endpoints, I can write it, since it's going to be an integral from point A to point B, this integral must be equal to some function of the final point, so some function of r sub b minus some function of the initial point, r sub a. And just because it's an integral from a to b, and so in our usual way of evaluating a definite integral, it's going to be equal to some function of rb minus some function of ra, since the integral depends only upon the endpoints. Now, let's call this function, I'm going to make a sort of funny choice here. So let's call this function minus u as a function of position vector r. And we'll see the reason for this funny choice of minus sign in just a moment. And so now with this definition, my work integral, which again is the integral of f sub c dot ds from point A to point B, is now minus u of rb minus u of ra. So in other words, that's minus u of rb. So minus minus gives me a plus u of r sub a. Okay? For shorthand, I can write that as minus u sub b plus u sub a. Okay? And since we start out at point A and go to point B, notice that I can also write this as the negative of the change in u. Since the final value of u is u at b, and the initial value is u at a, so this minus ub plus ua is equal to minus delta u, the change in u, as we go from the initial to the final position. Okay? And note that in addition to that, given that this is the work integral, I can summarize that by writing that. So I'll say, note that delta u is equal to the negative of the work done, going from point A to point B. Now, let's write the work kinetic energy theorem using this newly introduced u function. Okay, so the work kinetic energy theorem, which tells us that the work done, which we've seen is minus u sub b plus u sub a, is equal to the change in kinetic energy, delta k, which I can write as k sub b minus k sub a, or I can also write that as 1/2 m vb squared minus 1/2 m va squared. So this is just restating that the work done on the system is equal to the change in kinetic energy, and I can write the work in terms of my function u that I've introduced here, minus u sub b plus u sub a. So I'm going to rearrange this equation now, basically the one involving u's and the one involving kinetic energies, so that I have all the terms involving point A on one side, and all the terms involving point B on the other side. So rearranging, I get that at point A, 1/2 m va squared plus u sub a is equal to, at point B, 1/2 m vb squared plus u sub b. Now, notice, however, that there's nothing special about how I chose the points A and B. They're completely arbitrary. So that means this equation must be true for any points A and B. And what that means is that each side must be equal to the same constant for any point in the system. So in fact, we can write that k plus u for any point must be equal to some constant, which I'm going to call E sub mech. So k here is the kinetic energy. U is my function that I introduced, and we're going to call it
Mechanical
potential energy.
energy.
And E sub mech, and remember, this E sub mech here is a constant. E sub mech is something that we call the total mechanical energy. Now, what we've done here is that we've shown that the total mechanical energy, which is the sum of the kinetic energy and the potential energy, is a constant under the action of a conservative force. In other words, if we look at this equation and look at how it changes with time, the change in the kinetic energy plus the change in the potential energy is equal to the change in the total mechanical energy, and this is 0 for a conservative force.
Yes.
So in other words, the change in kinetic energy is balanced by the change in potential energy, such that the sum is 0 when the force acting is conservative. Now, we've now introduced the very important concept of the potential energy that is associated with a conservative force. And we see that the change in the potential energy, the way we defined it, the change in the potential energy is equal to the negative of the work integral for a conservative force, going from point A to point B. Now, in fact, it's actually only the change in the potential energy that has physical significance. We'll be concerned with potential energy differences or changes. The actual value of the potential energy itself doesn't matter. We're free to choose any convenient reference point or 0 point for measuring the potential energy. It's equivalent to choosing a coordinate origin when we're talking about positions. Now, the potential energy change is related to the work done by conservative forces. But we know that in general, work can also be done by non-conservative forces, although that work by non-conservative forces will depend upon the path taken from point A to point B. So in general, the total work is given by the sum of the conservative work, the work done by conservative forces, which we can relate to a potential energy change, and the non-conservative work done. And it's this total work that tells us what the change in the kinetic energy is. Now, we'll soon see that in the presence of non-conservative forces, the total mechanical energy, which is k plus u, is not a constant.
Yeah, makes sense.
We now would like to explore the concept of potential energy difference for a conservative force. Let's consider the following case. Suppose you have an object of mass m, and it's located at a certain height yi, initial,
This is
and so this
Billy.
is our initial state. And we would like to move this object upwards, so it goes up to a height y final. This is our final state. And in our initial state, we might have some initial velocity, and in the final state, we might have some final speed. And what we like to do now is we know that if there's a gravitational force, mg, acting downwards, that this gravitational force is a conservative force. And now what I'd like to do is, because the force is conservative, it doesn't depend on the path that our object goes to the final state. It just depends on the parameters that describe the initial and the final states. In fact, we'll see it only depends on the initial height and the final height. So what I'd like to do is define a potential energy difference in the following way. So as a definition, the potential energy difference between these 2 points is given by the negative of the work done by the gravitational force in going from the initial state to the final state. Notice this negative sign. Because the gravitational force here, Fg, is minus mg j hat, where we're taking j hat up, we've seen that this is an example of a conservative force. And it doesn't matter how we went from the initial to the final states. So we can generalize this idea for potential energy. But first, let's just remind ourselves of the calculation. When we did this calculation before, we had u final minus u final initial equals a negative sign in the definition. And when we calculated the work done by the conservative force, we had negative mg y final minus y initial. Notice the 2 minus signs, so we get mg y final minus y initial. Now, many times people talk about changes in potential energy. So when I write delta u, I mean precisely the potential energy at the final state minus the potential energy in the initial state, the change in potential energy, and that's equal to mg times the change in the displacement. And so we see here for this example that if delta y is positive, that implies that the potential energy is increasing. Now let's connect that to our definition. Why is the potential energy increasing when we raise something? Well, the gravitational force points downwards, the displacement is upwards, so the work done is negative, and another minus sign means the change in potential energy is positive. If the object is moving with no change in height, that tells us that the potential energy is change is 0. And finally, if delta y is less than 0, that implies that the change in potential energy is negative. Now, again, let's examine this case. If we were actually lowering an object, dropping it down, the object moved downward from the initial state to a final state. The gravitational force is downward. The displacement is downward. The integral is positive. The extra minus sign corresponds to the change in potential energy being negative.
We chose it.
Now that we've calculated the change in potential energy between some initial and final heights for the gravitational problem, mg of y final minus y initial, for this conservative force of gravity, and we had our coordinate system like that, we were able to calculate the change in potential energy. And remember, our theorem is that non-conservative work equals delta k plus delta u. Now what we'd like to do is establish the concept of a reference point for potential energy. And we'll do that as follows. See, the change in potential energy only depended on, say, our initial state and our final state. What we'd like to do is introduce the concept of a reference point. So let's identify some point yp to be our reference point, and we'll define a potential yp to be the reference potential. And if we want to talk about the potential energy in a final state, we'll always refer it to the difference between that and the reference point. So this is delta u between the final state and the reference point. Likewise, for the initial state, we'll always refer that with respect to our reference point. So any state that we have, we can always refer the potential energy difference between some state and some reference point. Why do we do this? Because notice that if we look at u final minus u reference point, and we subtract from that u initial minus u reference point, then the difference, the reference points here, we have a minus, here we have a plus, this is just equal to u final minus u initial, which is delta u. So the change in potential energy between any two states is independent of how we choose our reference potential, but it can make calculations easier when we can identify what the potential energy is for a little state. Now let's look at our example. So for our gravitational problem, we will choose y reference point to be 0. And we'll choose the potential energy at this reference point also to be 0. So our reference potential at the origin is 0, and it'll be noted like that. Then the potential energy at some initial state minus the reference point, well, we can use our formula here because this is between any two states. So this is mg, y initial minus the reference point, but our reference point was 0. And so we see that u initial minus y reference point, which was also 0, is just equal to mg yi. And so we have a statement that the potential energy difference between our initial state and the reference point is just mg, where yi is the height that the initial state is above the reference point. In a similar way, we have u final is mg y final, and so we see we recover what we expect. This is just mg y final minus y initial. Now, this we can generalize just a little bit by saying that let's write that for our mass, which is for any height y, our potential energy function for the gravitational force u of y is equal to mgy. That's a formula that many of you have seen before, but it's very important to note that with this formula, u of 0 equals 0 because that's our reference point. And that becomes our potential energy function for the gravitational force. Now, our next step will be to do the same thing for spring forces and inverse square gravitational forces, and we'll also look at graphical analysis of this function.
Naturally.
I would now like to calculate the potential function for two other conservative forces that we encounter all the time, spring forces and gravitational forces. We'll begin with spring forces. So first off, let's begin with some type of coordinate system. Suppose we have a spring, we have a block. This is my point x equilibrium, unstretched length of the spring. And now whether we stretch it or compress it here, I'll stretch it. I'll introduce a coordinate function x, unit vector I, and my spring force F is minus kx I, where x can be positive for a stretched spring, force is in the negative I hat direction. When x is negative, negative times negative means the spring force is in the positive I hat direction when it's compressed. So this is a force that's a restoring force, always back to equilibrium. This is an example of conservative force. And now let's calculate the change in potential energy, and then introduce a 0 reference point and get a potential function for this force. So the first calculation is straightforward. So if we took our displacement to be dx I hat, and we take the dot product of f ds, we get dx I hat dot I hat is 1 times dx, and that's just the x component of the force, displacement, and minus sign, because the x component of the force is negative kx. And so now, if we were to start our system, so again, for our initial state, let's say that the block from the unstretched position is stretched xi, and our final state, whether it's stretched or compressed, it won't matter, but we'll just stretch it out a little bit more to x final. So now let's calculate the change in potential energy between our initial and our final states. Now recall, there's a minus sign because it's minus w conservative. That's minus the integral x initial to x final of minus kx dx. We have two minus signs. That's our integration variable if you want to see it in all the detail. And when you simply integrate x prime dx prime, you get x prime squared over 2. And so the change in potential energy between these two states is 1/2 k x final squared minus 1/2 k x initial squared. And that's physically meaningful. If I take my system initially and the system ends up in the final state, then what I'm calculating is minus the work done by the spring force on the block as it goes from the initial state to the final state. I'm not talking about the work that an external agent does in stretching or compressing it. This is explicitly the work done by the spring force on the block as it goes from the initial state to the final state. I introduce the minus sign in our definition of potential energy, and so this quantity represents the negative of the work done by the spring force as the system goes from the initial to the final states. Now, you may have already thought about it, but the reference point that we're going to use is x equals 0, the unstretched length of the spring. And our reference potential at that point will be 0, so our reference point is actually the 0 point for the potential. And then our arbitrary state, we can call this the reference state, if you like. That's probably better than the reference point. Our arbitrary state will be at some arbitrary stretch or compress, and our potential energy function at that reference minus the potential energy at the arbitrary state minus the reference state? Well, if we set xi equal to 0 and x final equal to x, as we have in this expression, we simply get 1/2 k x squared. So the potential energy function equals our reference potential plus 1/2 k x squared. And we've defined that our reference potential to be 0. It could have been anything, but we're making it 0 so that we get a nice function, 1/2 k x squared. And again, it's always worthwhile to plot that function. It's a nice parabola, u of x, x. And you can see down here, that's our reference point.
Perfection. Now the rotation they set at infinity.
We would now like to calculate the potential function for the universal law of gravity. So let's set up a coordinate system first. And in this case, we're going to make a very special case, although the general result doesn't depend on that. So suppose we have a planet of radius rp, and we have a small object. And initially, our object is a distance r away from the planet. This is our initial state. And the planet has mass of the planet, and our small object has mass m. And this object is moving. Of course, orbits really aren't like that, so we should be a little bit more careful. But our orbit might be some type of hyperbolic section, conic section, and the orbit over here is at some final position. And ri is the distance from the object to the center of the planet, as our final is. Now, let's just, because there's a central point in this problem, the natural coordinate system to use is polar coordinates in the plane. And let's just imagine that at this moment, we have the universal force of gravity. Here's our object, and it's being displaced a distance s. So our coordinate system is polar. Let's call r hat this way, and theta hat that way. And let's blow up our little displacement in terms of our coordinate system, just so that we see what's happening. So our displacement had a, let's imagine that our little ds vector is pointing like this, and our center point here, we have the r hat pointing radially outward, and the theta hat pointing towards the center. Now, to exaggerate this picture, if this is r, then the arc length here is r d theta. And the difference as the object moves from one point here to a closer point towards the center will be dr. And so our ds vector, we can write as a radial piece r hat. Now, I don't put a sign in there, because only the endpoints of my integral will tell me whether I was going towards the planet or away from the planet, and r d theta, theta hat. And our gravitational force is minus g mass of the planet over the distance squared r hat. So now what we see is that when we take the dot product of these two forces, r hat dot r hat is 1 in polar coordinates. Why is that the case? R hat dot r hat is 1 because these vectors are in the same direction. The angle between them is 0. And remember that any two vectors that are perpendicular have dot product 0. R hat and theta hat are perpendicular. And so r hat dot r hat is 1. R hat dot theta hat is 0. So we only get minus g np r squared dr. And that's the first step in calculating our potential difference, because u of r final minus u of r initial by definition is minus the work done in going from the initial state to the final state, which are described by these parameters, our initial and our final, of f gravitational dot ds. And now we have actually minus sign in the definition, another minus sign coming from the dot product. And let's make this our integration variable, r prime, r initial, r prime equals r final. And there's going to be a third minus sign because the integral of dr r prime squared is minus 1 over r prime. So there'll be 3 minus signs, 1 from the definition, 1 from the scalar product, and 1 from the integration. And so we get r final minus r initial equals 3 minus signs, get an overall minus sign g, m planet, 1 over r final minus 1 over r initial. So this is the change in gravitational potential energy as my small object goes from some initial state to some final state. What about the potential function? Where should we choose our reference point? Now, so our reference state here is a little bit unusual, and it will be at infinity. And we'll choose as a potential for our reference potential to be 0 at infinity. That means when our, imagine initial state very, very far away from the planet. And we'll take as a final state, an arbitrary state, just where the object is some distance r from the planet. Now, we have to be a little bit careful, because in this calculation, our final state must always be outside the planet. And the reasons for that is subtle, but the gravitational force inside the planet is no longer minus g m1 and 2 over r squared. So our analysis only applies for r bigger than our planet. And if we put these values for r and infinity in here, we get u of r minus the potential at our reference point, which will be 0, equals minus g m m p. And here's the reason why we choose that reference point. 1 over our arbitrary state is just minus 1 over r. But 1 over infinity, if we use the initial state as the reference point, 1 over infinity is 0, so that's minus 0. And so what we get is that the potential function is equal to our reference potential plus, actually minus, g m mass of the planet over r for r bigger than our reference. And that is the potential function for the gravitational problem. But now remember, we're choosing that to be our reference point. And so the real conclusion is u of r equals minus g m planet over r with u at infinity equal to 0. Now, let's just finish this by saying in words precisely what this means. So if I start my system at infinity, and I end my system a distance r away from the planet, and I calculate the work done by the gravitational force in going from infinity to a distance r away from the planet, I take a minus that sign, so the negative of the gravitational work, then that's what that number corresponds to.
The total mechanical energy, E sub mech, is defined as the sum of the kinetic energy and the potential energy. So the sum of K plus U, where U is the potential energy function associated with the conservative force, with an appropriate choice of 0 point. If there are multiple conservative forces acting on the system, then U will be the sum of individual potential energy functions for each conservative force, with an appropriate choice of 0 point for each individual function. We've also seen that the change in the kinetic energy plus the change in the potential energy is equal to the change in the total mechanical energy. And that's just basically the derivative of the equation that I wrote above. Right? And this change in the total mechanical energy will be 0 for conservative forces. In addition, we've seen that the change in potential energy is related to the conservative work done in the system, so that W sub c, the conservative work done, is equal to the negative of the change in the potential energy. But we also know that the total work done includes both conservative and non-conservative forces. So the total work done is equal to the sum of W sub c, the conservative work done, plus the non-conservative work done, and that total work is equal to the change in kinetic energy. Now, I can rewrite that equation by rewriting the conservative work in terms of the potential energy. So I can write this now as the non-conservative work minus the change in the potential energy is equal to the change in kinetic energy. This is, again, just a restatement of the work kinetic energy theorem. Now, by rearranging this equation, this means that the non-conservative work is equal to delta K, the change in kinetic energy, plus delta U, the change in potential energy, but that's equal to the change in the total mechanical energy. So the non-conservative work is equal to the change in the total mechanical energy. This is a sufficiently important result that I'm going to write by itself in a box. So the non-conservative work is equal to the change in the total mechanical energy. So what we've shown here is that the result of any non-conservative work on the system is to change the total mechanical energy of the system. Now, if there is no non-conservative work, if the forces acting on the system are all conservative, then the total mechanical energy remains unchanged. Delta E mech is 0, and we say that the total mechanical energy is conserved. Now, if there is a non-conservative force, it turns out that in most cases the work done by a non-conservative force is negative, resulting in a negative change in the total mechanical energy. In other words, in the removal of total mechanical energy from the system. It's lost from the system. Now, we've been talking here only about mechanical energy, which we've defined as the sum of kinetic energy and potential energy, but one can also talk about non-mechanical energy, the most common example of which is loosely referred to as heat. As an example, in the case of friction, which is a non-conservative force, we know that the action of friction generates heat. What's happening is that the non-conservative work done by friction is negative, and therefore is reducing the mechanical energy, the total mechanical energy, according to this expression. But where does that energy go? We said that it's removed from the system in terms of mechanical energy. That's true, but we can think of it as at the same time causing an increase in the non-mechanical energy or the heat energy of the system. So if one were to keep track of both mechanical and non-mechanical energy, then it turns out that the total energy, mechanical and non-mechanical, the total energy of a system is conserved even if non-conservative forces are acting. However, it's difficult to recover the non-mechanical energy and change it back into mechanical energy. These non-conservative processes are not reversible. This is a complicated topic, and it's the province of more advanced courses in thermodynamics or statistical mechanics, which you may encounter later. In this course, we will confine our attention to mechanical energy, the sum of kinetic energy and potential energy, and we'll treat non-conservative force as removing or adding mechanical energy to the system.
In problem solving, when we're working with problems with potential and kinetic energy, remember we have our main concept that the non-conservative work causes potential energy and kinetic energy to change. K final minus K initial plus U final minus U initial. Now, how are we going to apply this in problem solving? Well, what we'd like to introduce is a tool which we're going to refer to as our energy state diagrams. So the way this works is let's have an example to think about. Suppose you have a dome. So here's some dome. We can think of this as the MIT dome. And you have an object that is initially at the top of the dome, and then this object is sliding down the dome, and at a later time, it's at a point somewhere along the dome. Now, eventually it's going to fall off the dome, but that's a separate question. So how can we use our energy ideas to analyze this situation? And the way we do it is that we choose first initial and final states that we're considering. Because our first idea in the energy diagram is to compare the change in energy, kinetic energy between initial and change of potential energy between initial and final states. So in our dome problem, we would choose our initial state. Let's draw our object at the top. And in our final state, separately, let's draw the object over here. And then we want to parameterize these states by some type of coordinate system. So here we're going to have some type of coordinate system that we use for both. Energy is a scalar, so we don't have to worry about it. And what I'll do is I'll define an angle theta final here from the vertical. Here theta initial is 0. And I've now parameterized my initial and final states. Now, the important thing that we'll do in the energy diagram is to choose our 0 potential energy. Where are we going to choose this? So we could say either a surface, we'll call that potential energy. And in this diagram, I can choose my 0 for potential energy anywhere I want, but I want to draw it on my initial and my final states. So I'm going to choose it right here, and I'll denote this as U equals 0. And now I can now make a list of, I want to identify, so step 3 is to identify the K and U for each state. So here we have K initial, it's at rest, 0, and U initial, well, I didn't introduce parameter R. It's U initial is how high the gravitational potential energy, so in this particular case, mg times R. Now over here, K final is 1/2 mv final squared, and U final, we can denote it here. If I plot this out, and that's R, then you can see that this is R cosine theta final, so that's mg R cosine theta final. Now the fourth step is to identify W non-conservative. Is there any non-conservative work? Now here, let's assume the dome is frictionless. And that means that W non-conservative is 0. And our last step 5 is we can apply the energy principle, which is W non-conservative equals delta K. Let's write it out, everything explicit now that we've defined K final minus K initial plus U final minus U initial. And you see the power of these diagrams is, and this methodology is we've now defined very explicitly every single term that appears in the energy principle, and so we can write out our result. That's 0, K final, 1/2 mv final squared, K initial, 0, plus U final, mg R cosine theta final, minus U initial, mg R And there we have applied the energy principle using the tool of energy diagrams. Let's consider an example of motion in which we want to use our energy concepts. So suppose we have a ramp, which is circular, radius r, and we have an object here. And now here's a surface, a certain distance d, that has friction, where the coefficient of friction is non-uniform. So we'll write it as mu naught, and we'll write it as mu1 x. We'll take x equals 0. And then here, there's a spring and a wall, and here there's no friction. Now, as we drop, assuming we have enough height here, h, so that this block will slide across the friction, make it all the way across, and start compressing its spring, what I'd like to find is how much the spring has been compressed. Okay, now how do we analyze this? Well, the key is to use our energy principle, where we have W external equals the change in mechanical energy. And the key is to, what we're going to do is the tool that we're going to use is what we call energy diagrams for the initial. So what does this mean? We want to first identify the initial and final states that we're referring to. So in our picture, here's our initial state. And I'll draw the final state in when the spring has been compressed a distance x final. So I drew it on my diagram. So we have initial and final states. And now what we want to do is choose reference points, 0 point for each potential function, and show that on our diagram. So for the potential energy of gravity, here, if we chose this to be y, then this is y equals 0, and u at y equals 0 is 0. And we'll call that the 0 point for gravity. And the 0 point for the spring is when this x, now I'm going to call here x equals 0, so let's call this a variable. I can call it anything I want. I'll call it u final. And this is where u is 0. So u final just measures the stretch of the spring. And so at y equals 0 is 0, and u spring at little u equals 0, 0. So now I can identify my energies. So let's talk about the initial energy is all gravitational potential. That's mgy. It's starting at rest. And E final, well, here, this is the distance where it comes to rest also. So there's no final kinetic energy. There's no gravitational potential energy because we're on the surface at y equals 0. But our spring has been compressed by 1/2 k little u final squared. Now, in terms of our external work equals the change in mechanical energy, we have now identified the right-hand side using these tools of the energy diagrams, and I can write my description, u final squared minus mgy. Now what I have to do is think about the friction force, F kinetic friction, as the object moves. This friction force is non-uniform. If we were to draw N and mg, then our friction force here is equal to the integral minus the integral from x equals 0 to x equals d, x equals 0 to x equals d, of the friction force, which is equal to the coefficient of friction, mu k n dx. Now that 0 to d, notice that our coefficient of friction is varying, and I chose that intentionally to show you that friction is really an integral. So we have mu naught plus mu1 x mg dx. Let's put our integration variable in there. And these are just two separate integrals. The first one is easy. It's minus mu naught mg d. And the second one is minus mu1 mg. And we're just integrating x prime dx prime between 0 and d. So that's simply d squared over 2. And that's equal to k u final squared minus mg y. Let's write that as y initial. And we're starting at y initial equals h. And so even though this is complicated, I can now solve for how much the spring has been compressed with a little bit of algebra. And so I'm just going to bring a bunch of terms over to the other side and take the square root of 2 divided by k of mg y initial minus mu naught mg d minus mu1 mg d squared over 2. And that's how much the spring is compressed. Notice what I did not do was divide this up into a bunch of different motions. I picked an initial state, I picked a final state. I drew my energy diagrams with my 0 points. I described the key parameters of the initial and final states, yi and u final. I defined the initial mechanical energy, the final mechanical energy, and then applied the work mechanical energy principle. I had to integrate the friction force because it was non-trivial, and solve for how much the spring has been compressed. When solving physics problems, we have fundamental principles. For instance, we have Newton's second law, and we also have an energy principle. Work non-conservative equals the change in kinetic energy plus the change in potential energy. And many times students are challenged by, do I use this law? Do I use that law? Why do I use one or the other? Do I use both at the same time? Can I get the same answers, etc.? Now, I want to illustrate a particular category of problems where we have some type of circular motion and why we need to use both of these laws. So let's go back to our dome example at MIT. And let's say we have an object that's on the dome. And now let's write out a free body diagram for this object. So we have our gravitational force. We have a normal force. And here, let's just assume that our dome is frictionless for simplicity. So what you see here is that the object is displacing in a direction. Now here, if I choose r hat and theta hat, and if I choose a coordinate system where I take my positive angle theta this way, that the normal force and the displacement are perpendicular. Now what that means is that the work done by the normal force, F normal dot ds, is 0 because, well, we're calling F normal equal to the normal force, and that the normal force is perpendicular to the displacement. So what that means is all information about the normal force is not included in the energy principle. In fact, the energy principle is the work that's that's done is just the amount, this is angle theta, so this is angle theta. So the actual work done by the gravitational force G is the component of G, mg sine theta, times the displacement ds. So the only work that's appearing here, and this is conservative, and so when we integrated this work and got that the work done by the gravitational force is minus the change in potential energy, that's showing up here. So the part of the force that's in the direction of the motion is giving us the energy condition, but we're losing all information about the forces in the radial direction. So we also, because also what we need is Newton's second law in the direction perpendicular to the displacement. Displacement is in the theta hat direction, so we need Newton's second law in the radial direction. And that we have, r hat, is we have a normal force minus mg cosine theta, and the object is undergoing circular motion, so it's equal to minus mv squared over r, where r is the radius of the dome. This equation is not at all included in the energy condition. You may say, well, what about the tangential Newton's second law, which is mg sine theta equals m r d squared theta dt squared? But it's precisely this equation that's integrated with respect to the displacement, and that gives us our energy principle. So in summary, the energy principle is the integration of Newton's second law in the direction of motion, and we're completely missing the application of Newton's second law in the direction perpendicular to motion. Energy does not account for that, and that's why we needed separately to apply both of the principles of energy and Newton's second law in the radial direction in order to figure out how to solve this problem. Now, this idea is true in general. When you have circular motion, you need the energy equation, which is the tangentially integrated Newton's second law in the tangential direction, and you need Newton's second law in the direction perpendicular to that circular motion. Now that we've introduced mechanical energy and our potential energy functions, we're describing our systems differently. We talk about states, we talk about the potential energy of that state, we talk about mechanical energy of that state. Remember, we're always referring to a reference state for our reference potential. But in one dimension, what we have is that the potential energy, say in some final state, minus the change of potential energy from some initial state, was that integral x final of the x component of our, I'm going to put C up there for conservative force, dx. And now we can, so the potential energy difference is the integral of the force with a minus sign. Now let's look at a fundamental theorem of calculus, which tells us that any time you take the difference of a function between two endpoints, then by definition, that's the derivative integrated with respect to the x. So when we compare these two pictures, this is a math here, this is our physics, how we define them, that when we compare these two pictures, we see that we can recover the conservative force by taking the derivative minus the derivative of the potential function. Here, force does not depend on any reference point, and when we differentiate a constant, that's 0, so this is independent of the reference point. And this enables us to, when we think about the potential function and its first derivative, then this tells us about forces. Let's look at an example. Suppose again, we look at our spring potential, where we're talking about the potential energy function of a spring, where at our 0 point, where it was unstretched, was our reference point. And if we plotted this function, so let's plot that function. So here's u of x versus x. Now we can talk about at any given point. So suppose we're at a point here. Maybe our energy has some fixed value. Then the slope at this point is equal to du dx, and the force is minus that slope. So here you can see that the slope is positive. So the force is negative, so I can write fx like that. So here fx is negative, so our actual force is pointing inward. When we're on this side of the potential function, my slope is negative, so the x component of the force is positive, so my force is pointing everywhere on this side back to the unstretched length. So knowledge of the potential function, also by knowledge of its first derivative, gives us information about the force at any point, any state that the system is in. So when we talk about potential, implicitly, we also know what the force is. And the potential function is enough to tell us what the force is at any point, and let's just check for this simple case. This is minus du dx. When you differentiate that, you get minus kx, and we know that's the spring force. So this is why we're subtly shifting our focus to our state, our function u of x, and its first derivative. Let's consider a system in which there is no non-conservative work, and there's a potential energy associated with forces in the system. And for an example, let's write our potential energy like the following. We'll model some system by the following function, bx cubed. And we know that our definition of force is that it's minus the change in potential energy. So if we differentiate this, our force is a function of x, and because of that minus sign, you always have to be careful when you take that type of derivative, we get, as far as the force goes, 2ax minus 3bx squared. Now, we ask ourselves, where does this force vanish? So if we look at the 0 points for the force, we can see immediately that there's one x equals 0. The other one, if we set 2ax equal to 3bx squared, tells us that we have another 0 point at 2/3 over 2/3 a over b. Now, let's also, for our example, just put some numbers in for some simplicity. Let's write this as 4 joules per meter squared for a. Why do we have meter squared? Well, the units of potential energy are joules, and we're multiplying by x squared. And so you can see that b, also, we're going to write as 2 joules meter to the minus 3. And if we put those numbers in, we can see that we'll get 8 over 6, and 8 over 6 is just 4/3, and that will be in meters, where the other 0 point is. So that's nice, but we'd like to know some properties of these 0 points. If we had a particle that we started with some energy at one 0 point, where would it go? What would it do at the other point? So in order to understand a little bit more detail about these 0 points, let's make a plot of our potential energy, u of x versus x. Now, to begin with, we want to ask ourselves, how does this function behave? And for big values of x, the x cubed piece will dominate. And if we're positive x, we dominate with a negative value for potential energy. So our potential energy function goes off into negative infinity as x goes to infinity. Now, on the other side of the scale, the x cubed term will dominate for negative values of x, but this term is negative and that's negative, so up here it will go off to infinity in the positive direction. Now, where are the zeros of the potential function? There's one, obviously one, at x equals 0. And with these values, it's not 100% obvious immediately, but 4x squared minus 2b x cubed, if you set x equal to 2, 4 times 2 is 8, b 2 times 2, 4 times 4 is 16. If b is 2 and x is 2, that's 16, so we get a cancellation at x equals 2, and so we have a point up here. I'm sorry, that's our 0 point at x equals 2. Now, we said that the force at x equals 4/3 had a 0, and so if we plot this function, it's going to look something like that. Now, let's focus on these 2 points right here, where our force is 0. Remember that this is minus the slope, and so we can see immediately that these 2 points have 0 slope, and so the force is 0 there. Notice, potential energy always depends on a reference point, so whether the potential energy is 0 or not is not crucial. But the physical fact that the force is 0 there has physical meaning. So here, this is one of our points, xx, f of x is 0. Now, what is the property of this point? Well, suppose we ask ourselves, if the particle were just displaced slightly from this position where the force is 0, which way would the force point? Well, in order to answer a question like that, we can look at the slopes on either side of the 0. So over here, the slope is negative, but the force is minus the slope, so f of x is positive on this side. And so if a particle is displaced a little bit from this 0 point, it moves off to the right, and it will continue to feel a force in this direction, and so it will move away from this 0 point of the force. Now, on the other side, we do the same type of argument, and over here, the slope is positive, but the force is negative. So again, what we see on this side, the particle will move away from this 0 point, and so if our particle just started there and had a little bit of kinetic energy, it would move one way or the other away from that point, and so we call this an unstable equilibrium point, and that's an abbreviation for equilibrium. Now, what about this 0 point over here? Well, we already know that if a particle is on this side of the 0, it feels a force this way, but what if our particle were on this side? Well, once again, we analyze the slope. The slope is negative, force is minus the slope, so it's positive. So everywhere on this side, the particle is getting a restoring force back to equilibrium. And so if we displace this particle just on either side, if it doesn't have enough energy to get over this point, then the particle will stay around this area, and that is why we give this point the name of stable equilibrium point. There's even a little bit more that we can learn about our energy diagram, and I like to just clean this diagram up for a little second because I want to work in this area. Suppose our system, because the work non-conservative is 0, tells us that the mechanical energy is constant. Now, we don't know how much mechanical energy our system is. That's a constant of the system, but let's just suppose that our mechanical energy is written like that. And we'll just clean up a little, give ourselves a little space. So here's the mechanical energy of the system, and that's a constant. And now we can talk about 2 more special points. A point over here, and at this point, let's just think about what our mechanical energy tells us. This is a special point, but let's begin with one right here. If our particle is at this location, then this represents the potential energy, and the difference between the energy and the potential energy is the kinetic energy. So this here represents the kinetic energy. And now we can ask ourselves, what would happen to the energies as our particle is moving? So if we start right here, the kinetic energy is 0 because all the energy is potential. And as a particle starts to move, let's say it has a little bit of energy, it starts to move in this direction, then the kinetic energy starts to increase until we get to this point where the kinetic energy is maximum at the stable equilibrium point, where the force is 0. Now the kinetic energy decreases because remember, it's now going against the force. This side, the force was pointing in that direction here, it was in the other direction. And until we finally get to this point where, again, the energy of the system is equal to all potential energy, and so there is no kinetic energy. So I'll call this point A, and I'll refer to this point over here. The diagram is getting a little crowded as B. And those points A and B are what we call the turnaround points. And they represent the places where the kinetic energy at XA is equal to the kinetic energy at XB, which is 0. Now, the last thing that we'd like to, there's a lot of information, as you can see, contained in these energy diagrams. And the last bit of information that we'd like to ask ourselves is what would happen if instead of confining our system to this area, we increased our mechanical energy so we're up here. And let's just follow qualitatively the motion of a particle that begins, say, over here with a little bit of kinetic energy and potential energy. And if a particle starts off with a velocity in the positive x direction, then it's going to move in this direction, and you can see the kinetic energy is increasing. Here we have a maximum amount of kinetic energy, but notice that over here, the particle still has some positive kinetic energy, and so it can get over this hill, and when it gets to the other side, the force was in the positive direction, it increases its kinetic energy, and it goes off to what we're referring to as infinity. So one analogy that people like to make is to understand the motion, think of a marble that's rolling down a hill, and this is just a metaphor for this potential energy function. As the marble rolls down the hill, it gains kinetic energy, it loses potential energy, it comes maximum at the bottom of the hill. As it goes up the hill, it still has enough kinetic energy to get over the top of the hill and to start to come down the other side. And of course, our particle can never get to the speed of light. So our model has to break off at one point.
This week, we will use the concepts of momentum and energy to examine an application of great importance, collisions. A collision is an event where two or more objects exert forces on each other over a short time interval, and where the interaction forces dominate over any external forces. Common examples are collisions involving projectiles, collisions of motor vehicles, collisions in sports, and collisions between atomic or subatomic particles. It is worth noting that the colliding objects need not actually touch each other in the collision, as long as the interaction force does not require contact. For example, two positively charged protons shot towards each other will repel each other due to the Coulomb electric force. Their interaction can be treated as a collision, even if they never actually touch. We will see that momentum is always conserved in a collision as long as external forces can be entirely neglected. However, energy is not necessarily conserved. This leads to the distinction between elastic collisions, where energy is conserved, and inelastic collisions, where energy is not conserved. We will also derive a simple but powerful principle in the case of elastic collisions in one dimension, that the relative velocity of one particle with respect to the other is simply reversed by the collision.
Let's consider our one-dimensional collision again. Object 1 moving with velocity v1 initial, and object 2 moving with v2 initial. Let's call this our i-hat direction. And this is our initial state. And our final state, after the collision, we have object 1, we'll say it's moving this way, v1 final, and object 2 moving that way, v2 final. Now, recall our principle of impulse and momentum. We said that if there's an external force during the time of a collision delta t, then physically that will cause the momentum of the system final minus the momentum of the system initial. Now, when we do this analysis, this side was a description, and this side is physics. Now, for our one-dimensional collision, we need to look at this collision and ask ourselves, are there any external forces acting on the system, which is consisting of particle 1 and particle 2? So what we're going to identify here is that the surface is frictionless, and we'll ignore all air resistance. And so by our assumptions, that there are no F external is 0, and therefore the momentum of the system remains constant. So here our statement is, many people call this conservation of momentum, but we're saying in this example, based on our assumptions, that the momentum of the system is constant. Now, how do we actually write that down? Well, let's now write it first as vector expressions. So we have the initial momentum, v1 of the system, m1, m2, v2 initial, is equal to the final momentum of the system, v1 final plus m2, v2 final. Now, how do we represent these equations? Well, you could treat them as vectors if you wanted, but what we're going to do is express them as components. So if we wrote this as components, we would have m1 vx initial I hat plus m2 v2x initial I hat equals m1 v1 x final I hat plus m2 v2 x final I hat. So that's the vector expression expressed in terms of components. The advantage of this is that we really don't know the signs of these two final components. That's our target quantities. But we could just write this equation, instead of writing it as a vector equation, let's just now write this as a component equation. And when we write this equation in terms of components, we have m1 v1x initial plus m2 v2x initial equals m1 v1 x final plus m2 v2x final. And this equation here is the equation that we'll use to express the constancy of the momentum of the system. We'll call this equation 1. Now, our next approach is to ask, are there any other quantities in the system which are constant? So we analyzed our one-dimensional collision where we had an object 1 moving with some initial velocity, object 2 also moving with some initial velocity, and after the collision we just arbitrarily said object 1 is moving this way and object 2 was moving that way, and we called that our i-hat direction. In this collision we assumed that it was a frictionless surface and there were no external forces, so momentum was constant. Now, what about energy? Well, we know that if there's no external forces, then in principle there could be no external work. However, during the collision we've established different types of collisions. We said elastic collision is when we are assuming that the kinetic energy of the system, that's k system final minus k system initial, is 0. The statement that the kinetic energy is constant. We have an inelastic collision in which delta k system has decreased, and that can come from some deformation of the objects during the collision. Heat is generated, some sound, some other source of energy, in which energy is always constant, but the kinetic energy of the system could diminish. And we also talk about a super elastic collision. And in this type of collision, the kinetic energy of the system has increased. Now, that's a little bit tricky in terms of what we're calling our system, but imagine that when these two objects collided, there was some type of chemicals on it that exploded, and so that there was some chemical energy that was converted into excessive extra kinetic energy. So in order to make a model of our problem, we have to beforehand make some assumptions about the nature of the collision. Now, for our particular collision, let's assume that the collision is elastic. So we have two conservation principles. We have that the kinetic energy of the system is constant, and we've already said that because there's no external forces, the momentum of the system is constant. So now we can write down our kinetic energy condition. We have m1 v1. Now here, this can be a little bit tricky how we're going to write this, because remember, kinetic energy is a magnitude squared plus 1/2 m2 v2 initial squared equals 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Now, because a component, although it can be positive or negative, in one dimension, if you square the component, you get the magnitude. So I can also write this equation, and I'm going to divide through by the halves, cancel all those, as 1x initial squared equal to the magnitude squared plus m2 v2x initial squared equals m1 v1 x final squared plus 1/2 m2 v2 x final squared. And we've already canceled all the halves, so we have no half there. Now, given this equation, we'll call this equation 1. We can also have our momentum equation, which I'm going to write down as 2 m1 bx initial plus m2 b2x initial equals m1 b1x final plus m2 b2x final, reminding us of our condition of constancy of momentum. So now, if you look at this, if we're given the masses, all the mi's, and we're also given the initial state of the system, v2x initial, then we have two equations and two unknowns, and we can solve algebraically for v1x final and v2x final. And by determining out the signs of these components, we can figure out the actual final state of the system. So this is going to end up involving a quadratic equation. Let's analyze a one-dimensional collision where we're in the laboratory reference frame and we have v1 initial and v2 initial is 0. It's a frictionless surface, but there's a collision here. And now we're going to make this collision totally inelastic. Now, what that means is that the two particles stick together. So if this is our initial state, and let's again choose a direction I hat, then our final state will just stick those two particles together, and they're going to move. We only need one velocity for the final state, I hat. Now, again, let's assume that there's no external forces. There are clearly internal forces that are acting between the two particles as they collide, but remember, we know that internal forces cancel in pairs, and if there's no external forces, the momentum of the system is constant. So we can write down our momentum condition very simply, and we'll write it again in terms of components. We have some incoming momentum into the system, and all of that incoming momentum is going out. And now, is energy constant? Well, a totally inelastic collision, energy cannot be constant. And the reason is that these internal forces will cause deformations that are irreversible. So the objects might be deformed, which is a loss of some of that kinetic energy will go into deformation. There could be noise, there could be heat generated in the collision, lots of sources. When objects stick together, kinetic energy is not constant. In fact, we can even figure out the change in kinetic energy because we can see here that Vx final is m1 over m1 plus m2 v1x initial. And now let's ask ourselves, in a totally inelastic collision, what is the change in the kinetic energy? So our final kinetic energy is 1/2 m1 plus m2 v. Here we can again write it in terms of components, Vx final because the component squared, there's no problem, and we just have this initial kinetic energy coming in. Now we have a solution for our problem, so let's just put that in, m1 plus m2 times m1 over m1 plus m2 times v1x initial squared minus 1/2 m1 v1x initial squared. And now let's pull out the 1/2 m1 v1x initial squared, 1/2, one factor of m1 v1x initial squared. But what we're left with here is another factor of m1, and downstairs we have an m1 plus m2 outside, but m1 plus m2, now remember we didn't square that, we have an m1 plus m2 inside, so there's an m1 plus m2 minus 1. Now, this is the initial kinetic energy, and when we subtract these terms, we have negative m2 over m1 plus m2. And so what we see here is, I'm just going to rewrite this again, that the kinetic energy, the change in kinetic energy, just depends on the initial kinetic energy and this mass ratio. In fact, if we asked ourselves, what is the ratio of the loss of kinetic energy to the initial kinetic energy, that just depends on the mass ratio of our two objects. In particular, it should be a minus sign because the kinetic energy is decreasing. And so this is the fact, it's very transparent now, that in a totally inelastic collision, the kinetic energy is not constant. Where did that energy go? It went into other forms of energy. Let's look at some examples of one-dimensional elastic collisions with no external forces between two particles. So suppose I have particle 1 and particle 2, and we have them moving on a frictionless surface. And let's choose a reference frame, which we'll call the laboratory frame, in which the initial velocity of particle 2 is 0. So our frame is called the laboratory frame. And in this frame, we're thinking of particle 2 as our target, and the target is at rest, and particle 1 is moving in with some initial velocity. And so here's our initial picture. And in our final state, both the target and the particles can be moving, so we'll just indicate v1 final, and we'll have target is also moving with v2 final, and we have I hat. So let's now look at some examples where we're analyzing this type of collision in which both energy and momentum are constant. And for a particular example that we want to look at, we'll have m2 is twice m1. Now, for our two equations that we're going to write about, we'll choose components, and we'll write our energy equation as 1/2 m1 v1x initial squared plus 1/2 m2. So now we're going to write 2 m1. But the object 2 is at rest, so we don't have to worry about that one yet. And so our initial kinetic energy is just equal to the final kinetic energy, 1/2 m1 v1x final squared. And now I'm going to substitute in 2 m1 for the mass of m2, v2x final squared. And that's our energy condition. And then our momentum condition is that the incoming momentum, 1/2 x initial, is equal to the outgoing momentum, m1 v1x final. And again, I'm going to substitute for m2, that's 2 m1 v2x final. And these two equations represent a system of two equations with two unknowns. We'll treat this as givens along with the initial velocity of particle 1. And our target here is to solve for the 1x final and the 2x final. So we have two equations and two unknowns. Now it's a quadratic equation, so we have to identify from a problem-solving strategy, we have to identify which quantity we're going to solve first. And so let's solve for v1x final, which means we need to eliminate v2x final. And the way I'll eliminate v2x final is I'll use the momentum equation, and notice that the m's will cancel in the momentum equation. And so if I divide through by 2m in the momentum equation and bring this term over to the other side, equation 2a becomes v2x final. equals, I'm dividing through by 2, 1 half v1 x initial minus 1 half v1 x final. So this gives me a target, v2 x final. I can substitute into there. This equation again can be cleaned up. Let's clean it up before. We can get rid of the halves, we can get rid of the m1s. And so the quadratic equation that we're going to be working with is v1 x initial squared equals v1 x final squared. And I'm dividing through by 2, so I have a factor 2 plus 2 v2 x final squared. Now that's our energy equation, and here's our momentum equation. So if we substitute this in and square it, we can now substitute, and we get v1 x initial squared equals v1 x final squared plus 2. Now we make our substitution. So that's 1 half v1 x initial minus 1 half v1 x final quantity squared. So let's now expand this, and we have to be careful not to make any mistakes. v1 x initial squared equals v1 x final squared. Now, if I pull the 2 out, I get a quarter in front, and divide that by half. So I get 1 half v1 x initial squared plus another one plus a 1 half v1 x final squared. Those represent the squaring out those two terms. Now the cross term will have a factor of half in the front, but a factor of 2. So we have a simple cross term of v1 x initial, v1 x final. Now, let's collect terms. Let's bring everything over to the side. So we have a 0 equals 3 halves v1 x final squared minus 1 half v1 x initial squared and minus v1 x initial, v1 x final. Now, I always like to just write this up in a simple way to use the quadratic formula. So I'm going to divide through by 2/3, and I get minus 1/3 v1 x initial squared minus 2/3 v1 x initial, v1 x final. And this is now a simple application of the quadratic formula. Negative b is plus 2/3 v1 x initial, plus or minus, and we're going to interpret those two roots in a moment. We have a factor of 2/3 v1 x initial squared minus 4ac. So that's another minus sign with a plus. So that's plus 4/3 v1 x initial squared, all to the square root, and everything divided by 2. Now here, let's just look at this factor. This is 4/9 plus 4/3. 4/3 is 12/9, so that's 16/9, which is very convenient because when you take the square root, that's 4/3. So we get equal to 2/3 v1 x initial plus or minus 4/3 v1 x initial divided by 2. Now we see that there's two different roots. So when you add them, you get 2 v1 x initial divided by 2. So there's one solution. And when you subtract them, you're getting 2/3 minus 4/3. That's negative 2/3 divided by 2. So that is another solution, v1 x final equals negative 1/3 v1 x initial. Now, let's think about the meaning of these two possible solutions. This solution has v1 x final equals v1 x initial. So that's the initial conditions. Just repeat it, and that will always be the case. One solution will describe the initial state, and the other solution will define the final state. You can check for yourself that if you just put vx1 final into this equal to vx1 initial into this momentum equation, then v2x final is 0, which just repeats the initial conditions. So this solution is the initial state, and this solution here is the final state. Now, just to complete the picture, v2x final, well, that's equal to 1 half v1x initial minus 1 half times v1x final, but v1x final is negative 1/3. So we have a half minus 1 half times minus 1/3, so that's a half plus a sixth, which is 4/6, or 2/3 the x initial. So that's 2/3 the 1x initial. And that represents the solution to this particular problem. Now, of course, what you want to do is you want to check. We know the momentum condition is already satisfied, but just as a check, you would like to put it into the energy condition just to make sure that when you square these things out, you get the right terms. However, we're very confident of our result because we've already reproduced the initial conditions, and that wouldn't happen if we made some algebraic mistake. So that by itself is a sufficient check that this is the correct solution. One thing we should sit back and think about is that when we use the energy and momentum, that we're inevitably dealing with quadratics, and so we expect to solve a quadratic equation at one point, and here it was right here. Now we're going to find another way to do this by linearizing the system, which will be a lot easier.
Okay. Let me see. I think we're gonna stop here. What the hell is happening? Where is my please course? Sorry.
Let's consider a system in which there is no non-conservative order, and there's a potential energy associated with forces. Let's consider a system in which there is no non-conservative order, and there's a potential energy associated with forces in the system. And for an example, let's write our potential energy like the following. We'll model some system by the following function, Vx cubed.
Next time we're gonna finish it.
For one-dimensional collisions, let's talk about.
Next time we are finishing it. We have 27 to 37 to two gyroscopes. Right. That's it. That's pretty much it. 60 more, and then we're gonna do some primitive examples, and that's gonna be it. Thank you for watching and commenting.